Hi, it's Mr. Anderson, and this is Chemistry Essentials video 39. It's activation energy. Imagine if I try to roll a ball up a hill. If I get enough energy into that system, the ball is going to roll down the other side. In other words, there was a certain amount of energy that ball had at the beginning. We'll call that potential energy, and then we've lost some of that potential energy. But the ball just didn't go there on its own. I had to put a certain amount of energy into it. And in chemistry, we call that activation energy. Now, it's not only balls rolling up a hill and down the other side, it's chemical reactions. You can think of this as the reactants on this side, and this as products on the other side. And so we're only netting this amount of energy between here and here, but there's energy that you have to put into the system. Let's say we have an endergonic reaction like this, one that requires energy. Well, I'm going to put more energy in. I'm going to get some of that back. If we were to look at the energy change, then everything above that is going to be the activation energy. What if I don't have enough activation energy? Well, I can put some energy in, but if I don't have enough, then it's going to go back to where it was before. And so activation energy is how much energy you have to put into a system to have a chemical reaction occur, and it's based on collisions between molecules. Most of those are unsuccessful collisions, and that's because they maybe don't have enough energy or they don't have proper orientation. But if they are successful, which again is incredibly rare, then we can have chemical reactions fire off. In a unimolecular reaction, that's mostly going to be interactions between the molecule and the solvent or background molecules. But if it's a bimolecular or termolecular reaction, it's going to be with other molecules or reactions with other molecules. In either case, it's going to be based on the Maxwell-Boltzmann distribution, how often this is going to occur. And again, that's where we can determine activation energy. And so let's say we have two molecules. We'll call this A and B. And I were to launch A at B. What we'll find is that if I don't give it enough energy, then there's not going to be a chemical reaction in this one simple collision. In other words, you require a certain amount of energy for that reaction to occur. So it's kind of based on temperature. If I increase temperature, I can have more reactions. Also, if I fire it off center like that, then they're not lined up properly and there's not going to be a reaction as well. And so with each of these collisions between all the molecules, you have to make sure that you have proper energy and you also have proper orientation. But if you do, then we can fire off that reaction. In other words, we've exceeded that activation energy. And so this could be in a unimolecular when we have just one molecule turning into products. It could be bimolecular where they're running into each other, or it could even be termolecular. We have three things coming together at once. And so all of these are based on the number of collisions that we could possibly have. And so the Maxwell-Boltzmann distribution explains how much energy we have to put into a system for that chemical reaction to actually occur. And so the curve looks like this. And so let me explain it to you. If you think of this curve representing all the molecules that have a potential to interact, well, we'd say the mode is going to be right here. This is the number that have this amount of energy, and this is the number of particles that we have. If we look on the left side right down here, there are going to be no particles who have no energy. And then as we move to the right side, the mean is going to be a little bit to the right of that because there's going to be a lot of particles way out here that have a huge amount of energy. Now, there's not many of those particles out there, but there's a lot of particles out there that have quite a bit of energy. And so if we look at that area under the curve, that represents all the molecules that we have or have the potential to have interactions with. And so we're going to set E sub A right here. That's going to be that activation energy. And so all of these out here have the proper amount of energy to actually have a chemical reaction occur. And so what happens if we increase the temperature? Well, if we increase the temperature, we just get a different curve. It's going to be the same number of particles, but it's shifting everything to the right. Notice what happened to the activation energy. The activation energy still is the same. It still requires a certain amount of energy for that reaction to occur, but by shifting it to higher temperature, we have more particles that have more energy, and so that area out here is going to be greater. And so again, did you learn to explain the difference between successful and unsuccessful reactions? Again, it's based on the energy they have and the orientation they have, and we can use the Maxwell-Boltzmann distribution to figure that out, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 68. It's on acid-base equilibrium. At Harvard University, they have this wonderful Chinese statue that was donated on their 300th anniversary, and it has this inscription that talks about the importance of knowledge to civilization. Sadly, during the winter, they have to cover it up, and that's due to acid rain. Seems like a confusing solution. And acid-base chemistry is sometimes confusing to students and teachers, but you just have to understand that it's a reversible reaction. What does that mean? It'll eventually achieve equilibrium. And we've learned that you can measure the equilibrium constant, and that gives us a better understanding of really what's going on in acid-base chemistry. Remember that equilibrium constant is simply the products, or the concentration of the products, divided by the concentration of the reactants. Now, what is an acid or a base? Remember, it all relates to proton exchange. And so if you're donating a proton, you're going to be an acid, and if you donate or you accept a proton, then you're going to be a base. And so we can measure the equilibrium constants of acids and bases and determine if they're strong, in other words, they're favoring the products, or if they're weak. We can also combine acids together, and we have what's called a neutralization reaction, and we can measure those using titration and titration curves. And so the first thing that you should understand is the importance of water. All acid-base chemistry takes place in the presence of water, and so we can think of an infinite amount of water surrounding every acid or base. It's something that we can simply ignore. There's always going to be water present. Water is also important because it is amphoteric, and what that means is it can serve as both an acid or a proton donor, or a base, a proton acceptor. And so if we were to look at a simple reaction, here we have acetic acid and water, what's going to happen is that the acetic acid is going to be the acid and the water is going to serve as the base. It's going to accept protons from acetic acid. Now, as it does that, it's essentially forming an acid, and since this is a reversible reaction, it can push back towards the base. And so we have these two pairs. We have these acid-base pairs. And to keep it straight, we'll call everything on the left side an acid and a base, and every on the right side a conjugate acid or a conjugate base. If we were to look at another reaction, in this case we've got ammonia. Ammonia is going to serve as the base, and so the water, since it's amphoteric, in this case is actually donating a proton, and it's forming that ammonium ion, which is the conjugate acid, and then we have the hydroxide, which is going to be the conjugate base. What's cool about water is it can auto-ionize. That means it can serve as both an acid and a base. And so what we're doing is essentially donating a proton to another water molecule. And so if we look at that, what we're forming is something called hydronium, and then the one that loses the proton is going to be a hydroxide. And we can measure the K value of this. We can measure the equilibrium constant of that. And it ends up being 1 times 10 to the negative 14th, which is going to be a really, really small value. Now, what is equilibrium constant? Remember, it's going to be the concentration of the two products divided by the concentration of the two reactants. Why do we have a 2 here? Remember, it's because we're going to have 2 moles of water on the left side. Now, as I said earlier, there's always water present, and so in this equilibrium constant of water, we can essentially ignore water. And so this is going to be our Kw value. Since it's 1 times 10 to the negative 14th, then we can just figure out that the concentration of hydronium and hydroxide, therefore, must be 1 times 10 to the negative 7th. Therefore, pH, which is the negative log of the hydronium, is 7. It's easier to deal with it that way than these really, really ridiculously small numbers. Likewise, pOH is going to be 7 as well. So if we add pH and pOH, it'll always add up to 14. Now, what's the difference between a strong or a weak acid or a base? Well, the equilibrium constant is going to help there as well. So if we look at acetic acid, in this case, it's donating a proton to water, and so we can figure out its acid ionization constant, which is essentially an equilibrium constant. So if we were to write it out, it's going to be the concentration of the two products divided by the concentration of only one of the reactants, Y. Again, we're simply ignoring water. If we were to measure that, we find it's a ridiculously small number. What does that mean? Since the equilibrium constant is so small, it's actually favoring the reactants. That means most of it is not actually donating its proton. And we call something like that a weak acid. If the Ka value is ever less than 1, in other words, it's favoring the reactants, then we're going to call that a weak acid. And carboxylic acids are notorious for being weak acids. Those are acids that have this carboxyl group in it. Now, sometimes it's hard to measure Ka or deal with those numbers, and so you'll see pKa, which is simply the negative log of Ka. If we were to look at a strong acid now, this is hydrochloric acid combining with water, and figure out its Ka value, it's an incredibly large number. What does that mean? If we have a hydrochloric acid, it's essentially all donating its protons. It's all shifting towards the right. And so if our Ka value is ever greater than 1, that means we've got ourselves a strong acid. And there are simply 6 strong acids that in AP chemistry you should memorize. Hydrochloric acid, sulfuric acid, simply memorize those. And there's a cool YouTube video that shows you how to do that. We also have what are called polyprotic acid. What are those going to be? Those are going to be acids that actually have 2 protons, and so they're going to donate that proton in 2 steps. Now, if we were to look at the general equation then for a acid, it's donating a proton and forming hydronium. We could write it like this. And if we were to look at the general equation for a base, it would look like this. And so we could also use the equilibrium constant of the base. If it's ever going to be less than 1, what does that mean? It's actually favoring the reactants, and it's going to be a weak base. There are 4 groups of those. And if it's ever greater than 1, then it's favoring the products, and these are going to be all of the strong bases that we have. You can see that they're all going to be hydroxides formed by combining with atoms from group 1 and group 2. And so what's a neutralization reaction? That's when we're getting a reaction between an acid and a base. And there are really 3 groups that we could have. We could have a strong acid and a strong base. And what happens there? They all are forming water. We could have a weak acid and a strong base. What's going on there? Well, basically we're going to take that conjugate acid and it's going to form a conjugate base. But remember, it doesn't form all of that right away. And then likewise with a strong acid and a weak base, we're going to have that weak base forming a conjugate acid, and so it's not going to all transfer those protons. And so we can use acid-base titrations to look at that. So what would it look like if we're doing a strong acid and a strong base? Well, let's set this up with a burette. What we're going to do is be adding sodium hydroxide to hydrochloric acid. You can see down here in the Erlenmeyer flask that we have a pH that must be less than 7. We're using phenolphthalein as an indicator. And so if we add some of that sodium hydroxide, eventually it turns pink. So that tells us that at some point it went towards a greater than 7 value. If we were to actually graph the pH over time, it would look something like this when we add a strong base to a strong acid. And so what's going on here? Well, at this point, we're adding a lot of this base. It's converting that acid into water, but the pH isn't changing very much because we have lots of this strong acid still in the container down at the bottom. Eventually what happens is we reach equilibrium or the equivalence point, and then all that base that we're adding is simply going to pump it up towards a more positive pH value. It's going to become basic. And so we have the smooth curve. We simply split the difference. When we're adding a strong base to a strong acid, that equivalence point is going to be right at 7. Now, what happens if we add a strong base to a weak acid? And so in this case, we're going to have acetic acid in the bottom, and then we're going to add a strong base, so that's sodium hydroxide. And you might think, since we're adding this strong base, it's simply going to turn quickly like that. We're going to add the base, it's quickly going to get rid of all of that conjugate acid, but if we were to do the titration, we get a curve that looks more like this. And so what's going on is it starts to increase like that, but eventually what we're doing is we're creating a bunch of this conjugate base, this acetate ion over here. And so this whole period of time right in here, what we've essentially created is a buffer solution. And we'll talk more about that in the next video, but what it's going to do is it's going to stabilize the pH. It's not going to change very much. And then eventually what happens is it's going to go towards the base. We're going to reach an equivalence point, but look at the equivalence point right here. That equivalence point is going to be much greater than 7. So it looks like it's somewhere about 8.2 in this case. Now what's causing that buffer solution, remember, is Le Chatelier's principle. What we're doing is we're adding more of the base, which is forcing more of that acid to be converted into a conjugate base, which is stabilizing that pH. Likewise, if we were to look at a strong acid and a weak base, so we're starting at a really high pH right here. As we add the acid, it starts to drop down really quickly, but now we've created a buffer solution right here, and the equivalence point is going to be lower than 7 in this case. So you should understand what those titration curves look like in each of those 3 different situations. And so did you learn the difference between a strong and weak acid and base? Remember, that's based on the equilibrium constant. Did you learn how strong and weak acids behave in these titration reactions? Did you learn that neutrality, in other words, a pH of 7, requires the concentration of the hydronium and the hydroxide ions to be equal. And then did you understand in each of those three situations what happens during a titration? I hope so, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 8. It's on atomic models. What is a model? A model is essentially a theoretical construct, and so it exists in our brain, and we use it to explain how phenomena works. And so phenomena, let's say gravity, for example, is almost like a black box. We don't get to touch it, but we get to essentially develop models that help to predict it. And so let me find a scientist that's a little brighter than me, and how would Albert Einstein look at gravity? Well, what he was doing, he was looking at the constructs, the models already developed by Sir Isaac Newton, but then he was able to improve on that based on data that he had received. So why does an apple fall to Earth? It's not that there's some magical force pulling it there. What Einstein said is that they're both warping space-time, and then these objects are traveling the closest path. And so light would travel along the same path. And he was able to confirm that using data. And so if we look at the atom is very similar. Atoms are so small. I think in a human body, we have 10 to the 14th cells. And then if we were to look inside the cells, we have 10 to the 14th atoms in every cell. And so it's incomprehensible how small atoms are and how many of them we have. And so we can use data to predict what an atom looked like. So the Dalton model, that they were just these spheres that would connect, was a model. As we discovered the nucleus, we came up with the Rutherford model, and then we used spectra to come up with a Bohr model, and then quantum physics gave us more of this quantum mechanical model developed by Erwin Schrödinger. And so we're improving this theoretical construct of what an atom is like. And so we've got an atom, which is phenomena, and then we have an atomic model, which is just a construct of what we think that looks like. And what we're able to do is gather data from the phenomena. And as long as that fits our model, then everything is good. But once we start to conflict with that model, then we have to develop a new atomic model. And we play that against the data. As long as everything fits, we use that model. But if it doesn't, then we develop a new atomic model. And that's really how science works. And so an example, if we're looking at the atom, they used to, once they had discovered the nucleus and the electrons, this was our model. It's our theoretical construct of what an atom was like. But once the data didn't fit, once we got spectral data that said that these electrons aren't just moving everywhere, that they're confined to orbits, then we came up with the Bohr model. And that worked until we started to look at ionization energy, learn more about quantum mechanics, and then we developed the model that we have today. And so as long as that works, as long as it fits the data, that's the model that we're going to use. And so let's look at that one transition. How did we go from this Bohr model to more of a quantum mechanical model? Well, let's look at ionization energy. Remember, ionization energy is the amount of energy it takes to pull an electron away. And so if this is our model, you've got 2 electrons in the first shell, then we'd go 8 in the next shell, and then we move out like that. Ionization energy should be like this. Hydrogen to helium, that works great. That would be the first subshell, but it should be really smooth as we move all the way from lithium to neon, but it simply isn't. And so we had to develop a new model, and that model consists of shells and now subshells, and then those subshells are further divided into orbitals. In other words, why would the ionization increase and then drop down again? It's because of the shielding effect of this 2s orbital. And why would it change here? It has to do with electron-electron repulsion. And so again, a model is simply a theoretical construct, and what we can do is as long as the data fits, we'll use it, but once the data changes, we have to adopt a new model. And so what you should have learned is how to determine that evidence is consistent with the model. And so I would point you back to this. The data coming in from ionization energy didn't fit the model, that Bohr model that we had, so we had to modify it. And we'll probably modify our current model in the future as well, and it'll give us a better and better and better understanding of an atom and what an atom is like. But I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 44. It's on catalysts. Catalysts can speed up a reaction, but they're not consumed in the reaction. One of the greatest chemistry demonstrations is elephant toothpaste. And I'm going to put a link right here to a video. This is from Brian Swarthout, a friend of mine, and his son Sam is doing the elephant toothpaste demonstration. Essentially, you add a catalyst to it, and then you have this reaction go really, really quickly. And so please give that a watch. Brian makes some wonderful videos in chemistry and physics. I'll put a link to some of his stuff down below. But how do catalysts work? Well, essentially they speed up a reaction. Some catalysts will actually slow down reactions, but in general they're going to speed it up by lowering the activation energy, the amount of energy we have to put in a system before we can stress those bonds, break them, and form new bonds. And so it has to go through this transition state, but a catalyst can stabilize that transition state, and therefore it can lower the activation energy and it can speed that reaction up. Now, some catalysts will actually add new intermediates. In other words, they're going to add new steps in this overall reaction mechanism. And so if we look at the energy profile of a reaction, remember we've got reactants on one side and products on the other. This would be an exothermic or an exergonic reaction. And so essentially we've got reactants, we've got products, but if we want to move between the two, we have to add a little bit of stress to those bonds. In other words, we have to achieve this transitional state. Eventually we can break those bonds and we can form new bonds. And so let me show you a catalyst at work. This is catalase, which is an enzyme found in almost all living cells. So what I'm doing is adding a little bit of hydrogen peroxide to a bag that's got yeast in it, and you could try this at home. Shake it up a little bit and you can see I'm producing a huge amount of oxygen gas right there. And so hydrogen peroxide would do this on its own, but if we add an enzyme to it, we can speed that whole process along. So how does it do that? If we look at the reactants on the left, that's going to be hydrogen peroxide, and the water and oxygen on the right, we see that we have to get through a large activation energy. And so what does catalase do? Well, scientists think there's a heme group in the middle of it, and that means just it's a number of atoms, but it's got iron right in the middle. And what that iron's acting to do is to pull one of those oxygens away. So it's stressing that bond on the hydrogen peroxide, and it's stabilizing this transition state. So it's more likely to fall into that just water and oxygen. Again, it's going to release energy, but if we look at the energy here, and if we look at the energy here, the net amount of energy that we're getting out is going to be the same. That catalyst is just acting to lower the activation energy. Now, sometimes it works by creating new intermediates and new steps in the reaction. And so in this elephant toothpaste experiment, you're taking concentrated hydrogen peroxide and soap, and then we're adding potassium iodide to that, and that's simply going to act as the catalyst. Now, what's it doing? That iodine is going to grab one of the oxygens, so it's going to make this intermediate, which will then bond with the other hydrogen peroxide, and that's going to create water and oxygen. And so we're really breaking a one-step reaction into two steps, and then we've got a new intermediate here. Well, what does that look like on an energy profile? This would be our original energy profile. We got reactants on one side, products on the other. But if we look at this two-step process, what we're doing is we're actually lowering the overall activation energy by doing two steps. In the first step, we're freeing up that oxygen, then we're bonding it to the other hydrogen peroxide to make water. And so we've lowered the overall activation energy of that reaction. And so did you learn to translate energy profiles? That's what this is right here. Particulate representations, and then even symbolic representations for chemical reactions with and without a catalyst. I hope you did, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 45. It's on catalyst classes, or the three different types of catalysts that we use. Catalysts are important in manufacturing, in refining, in life in general. And they come in three different forms. We have acid-base catalysts, so the sulfuric acid is going to be an example of that. We have surface catalysts, and so this would be similar to the catalyst you're going to find in a catalytic converter in your car. It's able to take carbon monoxide, this dangerous gas, and convert it into carbon dioxide. And then enzymes are going to be another group of catalysts, and those are going to run every chemical reaction inside a living body. And so catalysts can be broken into three classes. We've got acid-base, surface, and then finally we have enzymes. How does an acid-base catalyst work? Well, essentially it's going to take one reactant and we're either going to add a proton to it or we're going to pull a proton away. And as we do that, that's going to speed up the reaction. A surface catalyst is generally going to be made of metal, and if we can increase the surface area, it's going to work better. What it does is it increases the number of successful collisions in a reaction, and it also can create new reaction intermediates or new steps in this overall reaction mechanism. And then finally we have enzymes. Those are the biological catalysts, and what they can do is also produce new intermediates, or they can simply tug on a molecule and they can lower its activation energy. So let's start with an acid-base catalyst. What these are doing, remember, is adding a proton or taking a proton away from one of those reactants. And here's an example of a reaction that is catalyzed by an acid-base catalyst. We've got isobutane and we've got propene. So these are going to be found in just regular gasoline, fossil fuels. But what we're doing in this step of refining is we're actually making isooctane. And so we're making another hydrocarbon. And so if you ever fill up for gas and you see that there are different levels of octane, what that really is a measure of the percent of octane that we have, or isooctane that we have in our gasoline. Well, the higher that number is, it doesn't give us more energy, but what it does is it allows our combustion in our internal combustion engine to be more consistent. And so if we have really low isooctane levels, you can eventually experience what's called knocking in your engine. And it would work better in a diesel engine, for example, if we have low octane fuels. And so what is the role of this sulfuric acid? Sulfuric acid is going to donate a proton. So it's protonating this propene, and as it does that, it allows us to form this isooctane that won't normally form on its own. How does a surface catalyst work? Well, generally surface catalysts are going to be made of metal. And if you remember, metal, if we have a big chunk of metal, they're going to share their electrons in a delocalized cloud around all of the atoms. But as we approach the surface of that metal, we're going to find that there are going to be unpaired electrons. And so what you get are what are called active sites on the surface of that metal. And so that allows the catalyzing of a reaction. In this case, we have hydrogen gas and ethylene. And what they'll do is they'll dock with a surface, or the surface of that surface catalyst. And that process is called adsorption. What does that mean? It's not absorbing into the metal, it's adsorbing on the metal. And what it's doing is it's sharing and then pulling electrons from one place to another. And so what you can get is these, in this case, these hydrogen atoms can move around on its surface, and they're more likely to find a correct collision with that original molecule. Same thing right here. And so what we can do on that surface is we can catalyze the reaction. We're more likely to successfully produce that ethane. And so the increase in surface area, if we make it a real fine powder or a fine dust or a fine mesh, we can actually increase these collisions even more. What's a great example of a process that's catalyzed this way is the Haber process. So Fritz Haber is notorious scientist, but he came up with this Haber process. And in it, what you're really doing is taking nitrogen out of the air and we're making ammonia out of it. Now, in life, bacteria can do this. They can take nitrogen out of the air, put it into the soil. But without the Haber process, we couldn't do this on our own. And it's estimated that 1/3 of all the people on our planet are eating food that's produced through this process. And if you look at it, we've got a number of different catalysts and a number of different containers. And you can see if we look at all the elementary steps of this reaction, there's a lot of adsorbing of the gases, adsorbing of the nitrogen. And so eventually over time, what we're doing is we're creating ammonia. And here's the energy profile of that whole reaction. Last type is going to be an enzyme catalyst. And so this is going to be a biological catalyst. It's found inside our body. And so a great example would be the enzyme that breaks down sucrose. Sucrose is simply going to be table sugar. And so if we look at it, it is a disaccharide. We have 2 sugar molecules attached together. If we represent it like that, then an enzyme that breaks that down would be called sucrase. And what's going to happen is the sucrase will hold the sucrose. And what it does is that you have this fit where the enzyme kind of wraps around it and tugs on that. And as it does that, we can break that disaccharide apart into its 2 monosaccharides. And everything in our body is going to be mediated through enzyme catalysts like this. If you have a hard time breaking down lactose, it's because you don't have lactase, that enzyme that can break it up. And so how do we control everything in our body? It's through these biological catalysts that are made of proteins. And so did you learn to explain changes in reactions arising from Acid base, remember that's transfer of a proton. Surface catalyst, remember that's allowing those collisions to occur. Or enzyme catalyst. Well, if you did, you learned what I wanted you to, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 51. It's on calorimetry. And like anything in chemistry, a lot of this can go back to Antoine Lavoisier, that brilliant chemist who started a lot of modern chemistry. And so calorimetry, if we just break down that word, it means the measuring of heat. And the first calorimeter that was created by Lavoisier was an ice calorimeter. And basically what you had was a chamber that had ice on the inside, and then an insulating chamber of ice around the outside of that. And then you would put something inside the calorimeter, a candle for example, and what would happen is it would generate heat as it's doing combustion. It would melt the ice around it. That ice would turn into a liquid which he could measure. So you could measure the amount of energy that's being released from the candle. He then put something living inside there. He used a guinea pig to start, and what he found is that it occurred in the same way. In other words, that guinea pig is doing respiration, which is a form of combustion. It's using oxygen, it's releasing heat, and he showed that this is essentially the same kind of a process. Requires oxygen, gives off carbon dioxide, and so what he's really looking at is the energy given off by this system. And so a calorimeter is pretty simple. It only has two parts. It has a heat bath around the outside, and that generally is made of water because we know specifically how water changes over time. And then you're going to have a chemical system that's placed inside of that. We need a thermometer inside that heat bath so we can measure what's happening as we get changes of energy within it. And so we can measure energy change from that chemical system. And we could use this to measure everything we described in the last video. The specific heat capacity, the enthalpy of fusion and vaporization, and also the enthalpy of the reaction. And so let's start with water. Imagine that we have a beaker of water and we're adding energy to that. Remember, we measure how easily it's heated or cooled using a measurement called specific heat. And so if we break down that equation, specific heat is equal to the quantity of heat transferred, and we're going to measure that in joules, divided by the grams of the substance, in other words, how much we have, times the temperature change. And so let's give you a real example, because we know specifically what the specific heat is of water. It's 4.18 joules per gram Kelvin, and that's been well established. It's going to be important that we understand that as we start to do some calculations related to calorimetry. And so imagine we have 250 milliliters of water. Now what's interesting about water is we know immediately that we have 250 grams of water, and we started at 18 degrees Celsius. And so our mass is 250 grams, and our initial temperature is going to be 18 degrees Celsius. And let's say we heat it up. And so over time it changes, and at the end it's 65 degrees Celsius. And so our final, our T sub F is going to be 65 degrees Celsius. And so what we can do is figure out how much energy was added to that water, and we're going to use specific heat to do it. Again, specific heat is equal to the quantity of heat transferred divided by the grams times the temperature change. And so let's just start working down these values right here. Well, we know specific heat of water is going to be 4.18. We now know what the mass is. That's 250 grams, so I'm just going to plug that right here. We also know the temperature change. So we're going from 18 to 65, and so we just take our final temperature minus our initial, and so that's going to be 65 minus 18. That's going to be 47 degrees Celsius. We do some simple algebra. In other words, I'm just going to multiply both sides by this, and so I'm going to move it to there. And now I just simplify, and I'm going to find that the quantity of heat that was transferred is 4.91 times 10 to the fourth joules. And so where did that energy come from? It came from the heating of that water. And so if we know how much the water changes in its temperature and we know its mass, then we can figure out how much energy is released. And that's really how a calorimeter works. All you have is you're going to have a vessel where we're going to have that reaction or that heating or that phase change occur, and then we're just going to have it sitting inside this heat bath. We can measure the changes in temperature, and by measuring the changes in temperature of the water, we know how much energy is being released from that vessel or being consumed by that vessel. And so if we heat up that material in there, let's say it's a chemical reaction, and we see changes in the temperature, we know how much of that is coming from the reaction inside that vessel. And so this is what this would be a bomb calorimeter, and what it's doing is we're putting whatever we want to study inside this vessel. We're enclosing it inside water. We have a really detailed thermometer on the inside. Lots of times they'll have a stirrer so that we're moving that water around, and we can measure energy changes. We could use that to measure specific heat capacity, enthalpy of fusion. That's when we're going, remember, from a solid to a liquid or backwards. We can measure enthalpy of vaporization as we're going from a liquid to a gas, or we can just measure that enthalpy of reaction. We can measure endothermic and exothermic reactions. And so that's the role of a calorimeter. And so could you design or interpret the results of an experiment? Again, what we're looking at is changes in the water, and then we can work backwards to figure out how are those changes coming from that vessel, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 52. It's on bond length and bond energy. Some of the first bond lengths ever measured were measured by scientist Kathleen Lonsdale, who was an X-ray crystallographer. She would put a solid crystal in front of X-rays, measure the diffraction. It told her a lot about the structure of that molecule, and she could even measure the distance between atoms. And that allowed her to unlock the structure of hexamethylbenzene, that famous benzene ring. She was able to determine that it was a hexagon, that it was flat, and she even measured the aromatic bonds. In other words, the single-double, single-double, single-double bonds between the carbons. And by measuring the length of that eventually led to this whole idea of resonance. So not only was she an amazing chemist, but she broke down a lot of walls. She was one of the first 2 females fellows elected to the Royal Society, first tenured professor. She was an amazing scientist, but she really got us down this road of bond length and bond energy. And so if we have 2 atoms, they're both going to be attracted to one another. And where does that attraction come from? It's the electrons of one atom being attracted to the protons of another. And so that's going to pull atoms together. But if they get too close to one another, then there's going to be repulsion. And we can measure these forces just using an energy distance graph, where we've got the energy that's pulling those or pushing those apart, and then how far they are physically separated. And using a graph like that, we're able to determine the bond energy, the energy holding them together, and also measure the bond length, how far those atoms are going to be apart. And so the bond energy, if we were to define it, is simply the energy required to break those atoms apart. Now, likewise, when we form a bond between the two, we're going to release energy, and that's just simply the negative bond energy. Now, the strength of that bond, or the bond strength, is going to be built upon the charges of the atoms themselves. The bigger the charges are, the greater that bond energy is going to be. And as we increase the number of electrons in a bond, so as we move from a single to a double to a triple bond, we're actually increasing the charges and therefore increasing that bond strength. And one interesting thing that you should know is that as we increase that strength, we're going to pull those atoms together and we're going to actually decrease the bond length. And so if we look at these 2 representative atoms right here, as we bring them close together, there's going to be attraction. In other words, as we shorten the distance between the atoms, as they get closer and closer together, there's going to be a greater attractive force. Now, as they start to get really close together, there's actually going to be repulsion between those 2 atoms that's going to push them apart. And so we can find what's called that Goldilocks, the point where they're not too close, not too far away, and we're going to have the highest amount of energy right here. And they're just going to kind of vibrate at that space. So if we were to look at 2 atoms, like 2 atoms of hydrogen, we would find that energy to distance graph would look something like this. There's going to be attractive force between these two hydrogen atoms out here, but as we bring them closer and closer together, that energy of attraction is going to get greater. As we move them even closer, then we're going to move into this whole idea of repulsion. And so this is going to be that Goldilocks area right here. And so what we can measure then is the bond energy, the energy holding those atoms together. And likewise, since we've got distance here on the x-axis, we can measure the bond length, how far those atoms are apart. And so if we define what is bond energy, it's just two atoms connected together. And so bond energy is the energy absorbed when we break those atoms apart. Now likewise, there's going to be energy that's released as we bond those together, and that's going to be the negative bond energy. It's going to be exactly the same. The amount of energy to break it apart is the same amount of energy that we get when those two atoms are going to be attracted together. Now what contributes to that bond energy? It's going to be the electronegativity of all the atoms involved in that molecule. And so let's say we were to look at boron. Boron is going to have an atomic radius of 83 picometers. What does that mean? The distance from the center of that nucleus to the outside is going to be 83 picometers. And so if we were to connect a boron to a boron, we would anticipate that that bond length, the distance between the two atoms, is going to be twice that. It's going to be 166 picometers. But if we were to measure the actual bond length in a molecule, let's throw one up here, and it ends up being 175 picometers. In other words, they're farther apart than we would expect. That means that we're going to have a very weak bond between these two atoms. And so basically, as we increase that bond length, that distance between the atoms, we're decreasing the bond strength. Now, if we were to use another example, let's say we're looking at rhenium, which has a radius of 137.5. If we had two rhenium atoms, we would expect that that bond length is going to be 275 picometers. If we actually measure it in a molecule like this, and it's less than that, that means that they're really overlapping. There's greater charges holding it together, and so we would call that a strong bond. Again, the higher your bond energy is, the closer those atoms are going to be, and the shorter that bond length is going to be. Now, what happens as we increase the bond number? Let's say we're looking at two molecules that look essentially the same. We've got ethane, which is carbon attached to carbon, and then hydrogen around the outside, and then acetylene. And so this is the same thing, carbon attached to carbon with hydrogen around the outside, but in this case, we've got a triple bond right here. How is that going to affect the bond strength and the bond length? And so if we look at these two carbons, we've got one that's a single bond and one that's a triple bond. If we were to measure their bond length, we would find that as we increase the number of bonds, we're actually decreasing that bond length. They're getting closer and closer together. Well, what does that tell us about the bond energy? The bond energy is increasing over time. So again, the more electrons that we're sharing, the more charges there are, the greater that bond energy, and therefore the shorter the bond length is. If we were to measure the same thing with nitrogen, single, double, triple bond, we'd find that we're decreasing the bond length again. So what's going to happen to our bond energy over here? It's going to increase over time. And so did you learn to describe the energies involved in both breaking and forming chemical bonds? I hope so, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 55. It's on chemical and physical processes. If I were to take this table salt and break it apart into sodium metal and chlorine gas, I'd be breaking those ionic bonds. And so this would be a chemical process or a chemical change. However, if I were to take water and simply boil it, I wouldn't be breaking those covalent bonds in the water molecule itself. I'd simply be pulling on those intermolecular forces, pulling on it enough so that I could get it to change from a liquid to a gas. And so that would be a physical process. But there's a gray area in the middle. If I were to add the salt to the water, it could either be a physical process as we dissolve it or a chemical process. And so before we get to that, we really have to understand the difference between intermolecular and intramolecular forces. Intermolecular, remember, are going to be between molecules. So between the yellow and the yellow would be an intermolecular force. Those are going to be things like dipole-dipole forces, induced dipole forces. What are intramolecular forces? Those are going to be within the molecule itself. Those are going to be the bonds, the covalent and those ionic bonds. And so if we're looking at processes, we can put it in one of two categories. In a physical process, what we're doing is we're breaking and forming those intermolecular forces between the molecules. And so that usually ends up in a change of state from a solid to a liquid to a gas. In a chemical process, however, what we're doing is breaking and forming those bonds. And so that's how we tell the difference between these two processes. But there's a gray area in the middle. And in that gray area, if we take an ionic compound and dissolve it in water, those ions will be separated. And as they're doing that, we're not actually breaking those bonds. They're staying as an ion. We're just moving those apart. And so you could argue that this is a physical process or this is a chemical process. And so let's start with a chemical process. In a chemical process, we're breaking those bonds. And so in the combustion of methane, we're combining with oxygen, and you can see here that we're breaking those covalent bonds. We're breaking the bonds between the carbon and the hydrogen and oxygen itself. And so that's going to usually end up in producing changes in color, odor, gas, heat, maybe precipitate. This is a bunch of iron 3 reactions, and you can just see the remnants of all of these in these reactions itself. You can see that we're breaking those bonds and then reforming those bonds again. That's a chemical process. In a physical process, however, what we're doing is simply pulling on those intermolecular forces that are holding the molecules together. And that's just going to give us a change in state. Like when we boil that water, we're heating up those water molecules, we're breaking those hydrogen bonds between the two, and then we're starting to change it into a gas. And so in the gray area, however, we can take something like water, which is a dipole, and we can start to separate all the ions in sodium chloride. So when you put salt in water, it simply dissolves. Now, are we technically breaking these ionic bonds? No, we're not converting it back into sodium, metal, and chlorine gas. What we're doing is just ushering them away. And so if we take that water, what it really does is it surrounds the chlorine ions like this. And so what do we have? We have all this chlorine ion, and it's attracted to the positive part of the water molecule, or the hydrogen portion of that partial charge. Likewise, if we take that sodium ion, it's going to be the negative portion of the dipole that's actually going to usher that away. And so you could argue that since these are intermolecular forces, that this is simply a physical process. But if you were to measure those bonds that you're breaking, they're much harder than most covalent bonds. And so you could argue that this is a chemical process. And so again, did you learn to determine if a process is a chemical change, a chemical process, a physical process, or could be classified as both? I hope so, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 56. It's on biological and polymer systems. If we were to look inside your blood, we would find that it's filled with hemoglobin, and that hemoglobin is made in a ribosome. And it looks just like this when it comes out. What we have are a series of amino acids that are attached together through covalent bonds. And the amino acids themselves are held together with covalent bonds, but it comes out real linear like this. The moment it comes out of the ribosome, however, intermolecular forces take over. So hydrogen bonds are going to weave this into an alpha helix or a beta pleated sheet. These alpha helices and beta pleated sheets then are going to fold on top of each other, where we have hydrophobic regions moving to the inside, hydrophilic on the outside. We have all these dispersion forces that are holding different parts of that molecule together. And so eventually we're going to have this multi-polypeptide protein form that does its specific job. And so it's not just the covalent bonds that are important, it's going to be these non-covalent interactions. And so in a big molecule, the structure, in other words, how it's put together, is going to fit its function, what it does. If the structure is not correct, then the function is not going to be correct as well. That structure is made up of covalent bonds holding that molecule together, but we also have all these intermolecular interactions, these non-covalent interactions. Things like hydrogen bonds, things like dispersion forces, and all of these are going to work together to give it that specific structure to do a job. So for example, an enzyme has to have that perfect shape so the substrate can fit exactly in it and we can break that down. Now, as we start to make polymers of our own, it's important that we understand how their structure fits their function as well. And so a lot of these biomolecules are polymers. What that means is they're made up of a number of different monomers, just like this word is made up of letters. And so let me show you an example of a monomer. So this monomer right here, we have ethylene terephthalate. What's going to be the polymer if we attach this together? That's going to be polyester, like a nice polyester leisure suit. Or if we were to take this monomer, glucose, and we were to put that together in a polymer, what would we get? We would get a polysaccharide, like starch. Or if we were to take this amino acid, that monomer, and we were to attach it together, what would we get? We would get a polypeptide. So we're going to get this massive protein. But what's holding it together is going to be all these intermolecular forces between different parts of the molecule itself. So when we look at a molecule like DNA, what we're really seeing are the covalent bonds between all of those atoms that give us this structure. But what you don't see are all those non-covalent interactions. And so let me put some of those in with stars here. We're going to have all those hydrogen bonds in the middle that hold those two helices together. And then we're going to have those hydrogen bonds on the outside that give it the stable double helix kind of a structure. And so again, if we don't have both covalent and non-covalent interactions, we're not going to have a molecule that works. Likewise, if we were to take this simple polypeptide as all these amino acids come out and just look at the covalent bonds, it doesn't give us that structure of that overall protein. And again, that structure of that protein is incredibly important. So if we're looking at a biological molecule like an enzyme, which is simply a catalyst, which is made of a protein, how does that work? We're going to have an active site where the substrate will fit in. And so that substrate will fit in, and then it's going to kind of hug it. We're going to have this induced fit where the molecule is going to interact with that substrate. And as it does, it's putting tension on it, and then it's going to break it apart. It's going to lower that activation energy. And so if we don't have the correct structure, if we don't have these intermolecular forces between the enzyme and the substrate, it's simply not going to work. Now, as we start to create polymers of our own, if we understand how their structure fits their function, then we can start to design polymers that do wonderful jobs. So for example, Teflon, the structure of Teflon, which is going to be a polymer, gives us its function, which is going to be that nice non-stick pan. If we were to look at Kevlar, for example, its structure is going to give us that rigid function that's going to create that protective helmet or that Kevlar vest. Or if we were to look at nylon, if you look at nylon right here, these are all going to be intermolecular forces between adjacent strands of the nylon, and so that's going to give us its function as well. So did you learn to identify both the covalent and non-covalent interactions? I hope so, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 25. It's on covalent network solids, which are solids made of these vast networks of interconnected atoms, and those connections are made with covalent bonds. Now, what's interesting is the three-dimensional structure tells us a lot about the properties. And so a great example would be this, diamond and graphite. In other words, graphite that you write with a pencil are made of the same thing. They're just made of elemental carbon. But depending on how those carbon atoms are hooked together, we can have one of the hardest things on our planet, a diamond, or we can have something that is going to be broken by the paper that you're writing on. And so covalent network solids are made up of either one nonmetal or two nonmetals. So an example of one nonmetal could be graphite or silicon that we use to make computer chips. An example of two nonmetals might be silicon oxide that's going to make up quartz or silicon dioxide. Generally, these covalent network solids are made from the carbon group. And the reason why is that they have 4 valence electrons, and it allows them to make all of these vast number of bonds. Their structure can either be two-dimensional, so graphite will have these two-dimensional sheets, or it can be these vast three-dimensional lattices. And depending on what kind of structure they have, it's going to give them different properties. So for example, graphite is going to be incredibly soft. That's because it's going to have these soft layers, but it's going to have a high melting point because you're going to have these covalent bonds. Silicon is going to have a pretty good structure. It's going to have a higher melting point, but as we increase the temperature, we start to vibrate those atoms, and it can actually become a conductor. So it's something we call a semiconductor, and so we can vary the amount of electricity that is conducted through it. And one ways we can do this is we can dope it. We can add different elements to it, different other atoms. We can either N-type or P-type dope it, and we can add either electrons or the lack of electrons. And so it allows us to create things like transistors. And so this is an example of a covalent network. This is silicon dioxide. These are the crystals in quartz, and you can see that it has this regular structure. Now the picture that I'm showing you right here doesn't show that three-dimensional structure. We're just looking at one layer. But in general, they'll form these massive crystals. And so you can't really say that it's a molecule per se, because it's going to be more of a ratio of all the atoms that we have in this giant network. It's almost like an ionic solid in that sense. They're going to be made from the carbon group, and so carbon, silicon, germanium, and the reason why, remember, is they have 4 valence electrons, so you can make these vast connections. They could have a 2-dimensional shape or 3-dimensional, and as a result of all the covalent bonding, they're going to have a really high melting point. So here's a picture of graphite. This is what it looks like if we were to zoom down to the level of the atoms, and what you see is that there are going to be covalent bonds that are connecting all the carbon in each of these different layers of graphite. But what's missing is that 4th bond. In other words, I can only see 1, 2, 3 bonds to each of those carbons. That means that there are free electrons, and what those electrons are going to do are interacting with electrons from the next layer. And so you get these London dispersion forces that are holding those layers together. And so those are going to be relatively weak, and so it's easy for these layers to slide past one another. And that's why we could make pencil lead out of graphite. Silicon is going to have a much more regular kind of a 3-dimensional shape, this diamond lattice. And what's amazing, this is what silicon would look like if we could model it. You can see that there are 4 bonds now around each of those silicon. What we get is one massive crystal of silicon. That's all it is silicon in here. And what we can do is we can cut chips out of this. And so we can make the chips that are in your phone or in your computer. And so what's interesting about it is as we increase the temperature, we increase conductivity. So as we make it hotter, more electrons can flow through it. Now that's not the only way that we can regulate the amount of electron flow. We can also dope it. And what does doping mean? Well, if you look right here, we've got carbon and silicon, so they're each going to have 4 valence electrons. But what we can do is we can take atoms from the next group or the group below it, and we can either increase the number of electrons or decrease. And so let me show you what that looks like. We could dope it with phosphorus. That's called N-type doping. And the reason it's N-type doping is now phosphorus fits right into the lattice. It's going to bond to these 1, 2, 3, 4 atoms around it, but it's going to bring with it an extra electron. And the reason we call it N-type doping is it's increasing the negative charge that's going to be in that silicon. So it's easier for that to flow. So let me put that back for a second. We could also grab boron. So if we grab boron, it's going to have 3 valence electrons. It's going to bond to these 3 atoms around it, but it's going to bring with it a lack of an electron. And in electronics, we call that a hole. And so that's a lack of an electron, and it's an area where electrons could flow into that. And really, they talk about the holes actually moving around. And so P-type doping stands for this positive or a lack of that negative charge. And so where would we ever apply this? One of the greatest inventions of the 20th century is the transistor. And I'll put a link down below to a Veritasium video that explains how transistors work. It's totally fascinating. But the 3 parts of any transistor, they used to be much bigger than they are today. There are going to be 3 leads that go to it. And so essentially you're going to have a source where electricity can flow in, a drain where electricity can flow out, and then we're going to have a gate. And what you have is N-type on either side. So this is N-type silicon on either side, and then you're going to have P-type in the middle. And there's going to be no electrical flow. And so what we can do is we can add a little bit of voltage at the gate, and what you get is now electrons are able to flow. So we've got all these excess electrons here, flows through the holes out the drain on the other side. And so what's amazing is we can make these things incredibly small. We call them solid state transistors because they're made of solids. And so on a typical integrated circuit like you might have in a computer, there might be billions of transistors just on that one circuit. And so this is just application of that covalent network solid. So did you learn the following? To create a covalent network solid representation, remember it's going to be these 3-dimensional lattices of either 1 or 2 elements, non-metals. And then could you relate that structure to its properties? Remember, if it's 2-dimensional, if they're not connected, it's going to be really soft. If it's 3-dimensional, it's going to be really rigid. And also, since there's covalent bonds in here, they're going to have a high melting point, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 4. It's on Coulomb's law, which is a physics law, but also has huge ramifications when it comes to chemistry. And so if we look at a simple atom, this right here is helium. It's going to have 2 protons, 2 neutrons, and 2 electrons. What's holding those electrons around that nucleus is going to be Coulomb's law. And so if we were to look at the charges, the positive protons are going to have a positive charge, and the negative electrons are going to have a negative charge, and those opposites attract. That's Coulomb's law. And so that's the first thing that he discovered. If we have opposite charges, there's going to be an attraction between the two. Now, the other thing he learned is that you have 2 like charges. They're going to repel each other. And so those 2 protons don't want to be next to each other. They're going to be really unstable, and the neutrons and the strong nuclear force actually hold them together. Now, did you see what happened to the arrows? The arrows got larger when we looked at the protons. And that's because, according to Coulomb's law, as those charges get closer and closer and closer, then the forces get larger and larger and larger. And so it's sometimes referred to as the inverse square rule. And so let's get to Coulomb's law. And why is it important? Well, again, it shows us that positive and negative attract. And it also tells us that if we have 2 like charges, they're going to repel. But the closer they get, the bigger that charge is going to be. And so Coulomb's law tells us the force between charged particles is proportional to their charges. So all you do is just multiply the 2 charges, and that's going to give you the magnitude. It also tells us that it's inversely proportional to the square of their radius. In other words, how far they are apart. So if things are far apart, it's going to be less charge. As they get closer and closer and closer, that charge is going to get greater. It's very similar to the gravitational, Newton's law of universal gravitation. This just deals on the small level with charges. Now, in chemistry, it's important because we can use Coulomb's law to predict ionization energy. Ionization energy is the amount of energy it's required to create an ion. And so what's an ion? It's when you're either losing or gaining an electron. And so ionization is the energy required to remove an electron. And in chemistry, in science, we can actually measure ionization energy using something called photoelectron spectroscopy, or PES. Now that seems confusing, but it's actually a really simple concept and has huge implications when it comes to understanding what an atom actually looks like. So we can use the data to predict the shell structure. So how do we know that we have these shells and orbitals? A lot of that is predicted through Coulomb's law, but it's also verified through PES. So who was Coulomb? He was a French physicist, and what he was doing was studying charges. A lot of people thought there was some law that was could be applied to charges, and he was the first one to really quantify that. So essentially, if we have 2 like charges, they repel. And if we have 2 unlike charges, there's going to be an attraction. And here's the equation right here. You have a Coulomb's coefficient, and then we're going to have multiplying the charges, and then we're going to take the radius squared. Now, how did he discover this before we had electronics and even electricity had really been discovered? He used something called a torsion balance, and this is one of his sketches of a torsion balance. It looks a little complex, but it's really simple. All he would do is he would take a sphere and he would charge that sphere. And so we're talking about static electrical energy. And so that was suspended by a fiber that went all the way down here in the torsion balance. So he'd give this a positive charge, and he would give this a positive charge as well. And so if we have 2 like charges, what's going to happen when I bring this one? We can see it right here. As I bring this closer, what's it going to do? You can see that it's going to push it away. It's going to repel. And so it would twist this fiber, and he could measure it. You can kind of see the scale on the side. He could measure how far it went. He would then move it away, and he would touch this sphere to another sphere that didn't have a charge. And what it would do is it would transfer half of its charge to that uncharged sphere. He would then bring it back again, and it wouldn't move as far. And so he was able to quantify Coulomb's law using a not super sophisticated torsion balance. And so why is this important in chemistry? We can use it to measure ionization energy. And so what's ionization energy again? It's the amount of energy required to remove an electron. And so think of it as just a little hand that has to come in and grab this electron and pull it off. So that's the ionization energy. And so it's going to depend on Coulomb's law how big that ionization energy is going to be, because that proton wants to hold it in place. And so let's say we were to look at something that's a little larger. So this is lithium. And so lithium is going to have this outer electron out here. And since the distance is greater, in other words, that radius is larger, you're going to require a smaller amount of ionization energy to pull it off. And so that Nobel Prize was awarded to Albert Einstein for his discovery of the photoelectric effect. And what that means is if you hit metal with photons or hit metal with light, what it'll do is it'll eject these electrons, and we call those photoelectrons. And so hold on to that idea. It's going to become really important in just a second. But let's build an atom for a second. And this is a simulation from PHET. What you can do, you could go to the website right down here. What you can do is you can just start dragging things in, and then it'll actually build that atom for you. So let's do that. So let's say I drag a proton in. I've now created hydrogen. You can see on the periodic table, that's going to be H. It's got one atomic number. But let me just throw an electron in there, and where does it go? It goes right there. What's holding it in place is going to be Coulomb's law. They're opposite in charge, and so they're going to be held together. Well, what happens if I throw another proton in? Now we've got helium, but look how unstable it is. Why is it so unstable? It's because those are like charges, and so they want to repel each other. Luckily, and it would never exist like that. Luckily, if we add some neutrons to it, then we can stabilize it, and so that's not going to decay. Now let's add another electron. It's going to sit in this shell. And so we've got 2 electrons in this first shell. Let's make it from helium. Let's move up, make it a little bit of unstable lithium. We'll stabilize that with a neutron. Now let's add another electron. What happens? Well, it sits right there. In other words, it's in the outer shell. And this is in the outer shell, and this is in the outer shell. So why is it that those first 2 electrons are going to be on the inside shell, and the outer electrons are going to carry, or excuse me, those additional electrons that we add are all going to be thrown to the outside? That has to do with quantum mechanics and quantum physics. And so it's quantum numbers that are determining that. But how did physicists figure this out? How did chemists figure out that there's going to be a 2 in the first, and then we're going to have 8 in the next, and we're going to have all these orbitals? Well, we owe it to the photoelectric effect. And so going back to that again, that's Einstein's theory that if you hit matter with light, it's going to eject these photoelectrons. And so let me show you photoelectron spectroscopy. And so what is that? You basically have a photon source on one side. And so you're going to have a source of light on one side. And so that could be infrared light, it could be UV light, it could be X-rays. The energy of those photons is determined according to the equation where energy is equal to hv, where h is Planck's constant and v is going to be the frequency of the light. So basically in this machine, you can vary the energy of those photons that are coming out. They'll strike the matter that you want to study that's sitting inside a vacuum, and that's going to eject electrons, so photoelectrons, and those photoelectrons will be captured up above so we can measure them. And so this is a pretty simple setup. What are you doing? You're hitting matter with light, and then you're measuring the electrons that come out of it. And so let's look at hydrogen. If we're looking at a sample of hydrogen, we're going to create a spectrum or a photoelectron spectrum. And so we're going to have energy across the bottom. That's the amount of energy that we're introducing with the light. And then we're going to have the number of electrons on the side. And so what happens when you turn on the machine is you can just vary the energy, and eventually you'll hit a point where you get a bunch of electrons coming out. So why is that? Well, what we're doing is we're changing the amount of energy to the point where we hit ionization energy, and then boom, we're going to release all of those electrons from hydrogen. And so we're going to get a peak at, we'll just call this 1.3 and think of it as an amount of energy. Now let's go to helium. What do you think that's going to look like? Well, helium has 2 protons on the inside, so it's going to have a different amount of ionization energy. And so if we hit that with light, watch what happens. Okay, it's different amount of energy. You can see that we need more energy to eject those electrons, but look how big the peak is. Now let's compare that back to hydrogen. Hydrogen had a peak like this. Helium had a peak like that. Why is this twice as high as this one? It's because it has twice as many electrons. It's because we're ejecting 2 electrons when we tune that frequency to the right ionization energy. Okay, you think you got that? Let's go to the next one. What do you think will happen with lithium then? If we hit lithium with energy, well, we'd already talked about this outer one is going to have a low amount of ionization energy. So let me show you the spectrum for lithium. Wow, what do we get here? Well, we get one peak that's going to be 1 electron that's going to have low ionization energy, and that's going to be this one right here. But then we're going to have a double peak, in other words, 2 electrons, that's going to be way more energy. Why is that? Lithium's going to have way more protons. And so what's cool about photoelectron spectroscopy is we can actually verify the predictions that we made with Coulomb's law. So could you fill in this concept, Matt? Coulomb's law is the force between charged particles. And how is that related to their magnitude and radius squared? Could you fill in those 2 blanks? And what is that technology, do you remember, that measures ionization energy? And then what is ionization energy? It's the energy required to do what? Let's see. So it's the force between charged particles is proportional to the magnitude. In other words, just multiply the charges, inversely proportional to the radius squared. That technology is called photoelectron spectroscopy, and then ionization energy, remember, is the amount of energy required to remove an electron. So what did you learn? You should have learned that we can explain the distribution of electrons in an atom or ion based on data. And so we can predict data using Coulomb's law, and we can also verify it using PES. We can analyze the data, and we can look for patterns and relationships. And we're going to get more into those patterns and relationships in the next video, but I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 2. It's on chemical analysis. One of the first early chemists, Jöns Jakob Berzelius, who was Swedish, came up with the way that we write out chemical formulas. And I love this picture here. It's one of those where no matter where I move, he seems to be watching me. But, so when we write out CH2O, which is actually going to be the empirical formula or the simplest formula of a sugar, let's say glucose, we owe it to him for that. But if we look at the actual structure, this is what glucose looks like. So it's going to have 6 carbon, 12 hydrogen, and 6 oxygen. But chemical analysis is simply looking at a compound like glucose, for example, figuring out what's in there, how much of that what, and then how it's all connected together. And so in chemical analysis, we're looking at compounds. And remember, compounds are going to be made up of atoms, and each of those atoms have a specific mass. And so what we can do is look at the percent mass. In other words, how much of that mass of that compound is made up by each of those different atoms. And that tells us what the composition is. It also can help us figure out the empirical formula. That's that simplest chemical formula. And it also can be used to test the purity of a substance. In other words, is it just that, or are there other things that are added inside there? And so let me give you an example, and we'll come back to this at the end of the video. Let's say we take vitamin C and we put it in a mass spectrometer, which is going to tell us the percent mass of all of the atoms that are found inside it. And then we get this spit out. So we've got carbon, hydrogen, and oxygen, and it tells us the percent mass of each. In other words, it tells us how many grams are going to be made up of each. Could we figure out the empirical formula? Well, we will, and we're going to get back to that in just a second. And so let me use an analogy to begin with. So just like matter is made up of atoms, we could talk about something like a big Lego structure being made up of Legos. And so let's say we had this base unit, and it weighed 2.5 grams. It doesn't matter if we have a larger or even a larger unit made up of those smaller blocks, it's all going to have the same average mass. In other words, if we divide by the number of bricks, we're still going to have an average mass no matter how big the sample of those Legos is. But now let's get to solving it the other way. In other words, if I give you a big structure that weighed 320 grams, could you work backwards to figure out how many bricks are in that structure? Well, you'd use factor label to figure that out. In other words, if each brick weighs 2.5 grams, I can write it out like this. Now we can cancel off those grams. And so what I get is 128 bricks in that structure. And so what we can do is we can work backwards from that mass, and we can figure how much stuff is inside there. Now, when we're working with chemistry, we don't deal with bricks. What we're going to work with is something called a mole. And so let me use gold as an example. Let's say I had 1 mole of gold, or 4, or 32. It's all going to be the same mass. And what is a mole? I'll talk more about that in the next video. It's essentially a usable amount of an element, a usable amount of a compound. And so all of these are going to have the same average mass, 197 grams per mole. Now, where am I getting that 197? Just like 1 Lego piece weighs about 2.5 grams, 1 mole is going to weigh around 197 grams. And so where do we find that? On the periodic table. And you should get used to just opening up that periodic table. And so if we look at gold, its atomic mass number is going to be around 197. In other words, it's 197 atomic mass units, or if we have 1 mole of it, it's going to be 197 grams. So it's going to have the same average mass. And so what we can do is we can convert to moles. We can, just like we converted to bricks, we could convert to moles. And let's say I have a 2-ounce chunk of gold. which is around 56.7 grams. And so what I could do is, since I know that 1 mole is going to be 197 grams, I could cancel off those grams again. And what I could come up with is about 0.288 mole. And so a mole is going to tell us how much of that element is going to be found. So let's go back to that problem again. Let's say we're given some vitamin C, we put it in a mass spec, and we get this data out of it. What is that telling us? It's telling us the percent of each of those inside there. And so what we could do, let's throw that data out here, is we can convert it to moles. And once we have it in moles, we could figure out the empirical formula. So just like we did with the gold, how do we convert this to moles? Well, we'd have to get out the periodic table. And so since carbon has an atomic mass of 12.01, we could write out this conversion. We're going to cancel off the grams of carbon, and that would be 5.11 moles of carbon. Likewise, if we were to convert the hydrogen, again, it's going to have a different atomic mass number. We can convert those grams of hydrogen and it'd be 6.8 moles. So that doesn't tell us much yet. Let's go to oxygen. Oxygen's atomic mass, remember, is 16, so I could cancel this off, and now we get 5.11 moles. Well, that's weird that these are the exact same. Not really. It just is our first piece of evidence that there's the same amount of carbon as there is oxygen. Let's simplify that a little bit. So since we divide them each by 5.11, we get 1 of the carbon to 1 of the oxygen to 1.33 of the hydrogen. Now, should we write it out like that? You've never seen a chemical formula written with any kind of anything aside from whole numbers down here. And so what we could do is multiply the whole thing times 3, and now we get the empirical formula of vitamin C, or ascorbic acid. Now, is that really what it looks like? No, and we'll get to that later. This is what it looks like. So it's actually going to have 6 carbons, it's going to have 8 hydrogens, and it's going to have 6 oxygens. But you can see how we can use the mass to figure out what's in there, and then how much of that what is going to be found in there as well. We could also use a mass spec to figure out the purity. So if we were to throw that vitamin C in there and we get kind of evidence like this, well, that tells us there's a lot of carbon, hydrogen, and oxygen, but we also have some impurities in there. We have some mercury and palladium, which is something that you don't want in your vitamins as well. So could you fill out this concept map? Could you fill out the spaces? Could you pause the video right here? Okay, let's go through it. So chemical analysis is used on compounds, which are made of atoms, which each of those atoms have a specific mass. Remember, we can therefore use the mass percent to figure out the composition, in other words, what is in the compound. We could use that to figure out the empirical formula, which is the simplest whole number formula. And then we could also use that to figure out the purity of that substance. And so did you learn the following? This is what I was hoping you would learn. Number 1, you can use mass data to identify or infer the composition of pure substances and or mixtures. So again, we just look at the mass percent of everything that's inside there. And then the second thing, could you use mass data in order to justify a claim regarding the identity or estimated purity of a substance? And so those are the 2 things that you should be able to do. We learned how to figure out the empirical formula, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 49. It's on the conservation of energy. If you've ever done any calculations or reading on energy, you've noticed that there's a unit named the joule, and that's named after this guy right here, James Prescott Joule. And he came up with this really innovative way to look at energy transfer. And so in this apparatus right here, what we have is a weight, and that weight is lifted off the ground. So there's a string attached to it. We have to crank this string all the way up like that. And then we eventually have this weight at a given height. And so what it has at this point is potential energy, gravitational potential energy. And so what Joule is looking at is how can we convert that to changes in temperature, or how do we get that energy transfer through heat? And so what happens is as this weight falls, what it's doing is it's spinning these blades that are in water, and the friction of that spinning of those blades in the water is increasing the temperature. And so what he was able to do is make measurements as to how that mechanical energy or that work of that falling weight is actually transferred into temperature changes. And so if we're ever talking about conservation, a good way to think about that is a teeter-totter. And so we've got before and an after. And so if we've got two systems, so system 1 and system 2, the amount of energy that they have before interacting with each other has to be exactly the same as the energy that they have after. And so in a closed system, in other words, if we're looking in just isolation at these two systems, system 1 and system 2, if system 1 has more energy than system 2, then we're going to transfer that energy from 1 to 2. And so the energy is going to be conserved. Now that energy could be energy transferred through heat, or it could be energy transferred through work. So the amount of energy we have before and after has to be equal, or it has to be conserved. So before and after that interaction, the amount of energy has to be conserved. So again, system 1 had more energy to begin with than system 2. There was energy being transferred, but the overall energy that we had to stay the same. And so where could we apply this? Well, look no farther than driving a car. And so where is most of the energy in a car that drives that car? Well, that energy is going to be in chemical energy of the gasoline. So in those bonds, we have a certain amount of stored energy. And as we release that through combustion, what we're going to do is transfer that energy into different forms. And so it's all chemical energy to begin with. But as that car moves, where are we transferring that energy into? Well, we're transferring a lot of it into mechanical energy. Mechanical energy is driving the piston in that internal combustion engine, driving the crankshaft, driving the drivetrain, it's moving the wheels, and it's moving that car. Now, if you've ever put your hand on an engine, you'll notice that it's really hot. So we're also converting a lot of energy into heat. There's also probably electrical energy inside there. We have light energy perhaps that's being transferred. And so that amount of energy that we had before and the amount of energy that we have at the end has to be conserved. We don't either create nor destroy energy. And so if we go back to our teeter-totter again, the amount of energy we had before was mostly chemical energy. But it's being converted into mechanical work. So we're driving that drivetrain, driving that car, moving that car. We're also transferring a lot of that energy through heat. We're also producing maybe electrical and light energy. But if we look on either side, before and after, the amount of energy that we have has to be conserved. And so did you learn to relate the magnitude, how big it is, the type and the direction of that energy transfer? Remember, when I'm talking about type, I'm either talking about energy transfer through heat or energy transfer through work. And then have you learned this idea of conservation, that the amount of energy that we have before and after have to be exactly the same? I hope so, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 19 on covalent bonding. When you look at these three crystals over here, they look somewhat similar, but the bonds that hold them together are going to be really different. We've got metallic bonding up here, ionic bonding here, and then we have covalent bonding here. And so what's going on with the electrons is the best way to tell each of these apart. And when we start with covalent bonding, you really have to start by talking about electronegativity, which is how much an atom wants an electron. And it's going to increase as we go up and across on the periodic table. And the reason why, it's based on the shell model and Coulomb's law. And so as we decrease the size of an atom, as they get smaller, it's going to be closer to the protons that are found in the nucleus. And then as we move over to the right, those positive values are going to increase, and we're also going to increase that attractive value. And so based on those electronegativities, we can look at the atoms inside a molecule, and we can figure out, is it a covalent bond? And if so, what type of covalent bond is it? Now, if those electronegativities are exactly the same, then we call that a nonpolar covalent bond. An example would be oxygen that you're breathing right now. It's two oxygen atoms. They have the same electronegativity, so they're going to share the electrons equally. Also, you should know this. If it's a carbon and a hydrogen that are attached together, carbon is really good at sharing its electrons, and so we generally call that a nonpolar covalent bond. We can look at these bonds using a graph where we graph the potential energy on one side and then the distance between the atoms on the other side. And so what becomes apparent is going to be the bond length, how far those atoms are apart, and then the bond energy. How much energy would we have to put in to break those atoms apart? Now, if the electronegativity is different, then we call that a polar covalent bond. And so when we do that, we have something called a dipole, where there's a partial positive and a partial negative charge. Whichever one has the highest electronegativity is going to have that negative charge. But even though we may have differences in charge, we still have conservation of charge over that whole molecule itself. Also, as we move from covalent bond to more and more electronegativity, we start to move into what are called ionic bonds. And it's a gradient, it's a continuum. And so we can measure these to tell the difference between them. And so a covalent bond, remember, is going to be sharing of the electrons. So a great example would be hydrogen gas. Hydrogen has one electron in its outer shell. It'd like to have two, and so it can share that one electron with another hydrogen atom, and now we have the sharing of these two electrons, and so we have a covalent bond between the two. Carbon, for example, has 4 valence electrons. According to the octet rule, it would like to have 8, and so what it can do is it can share each of those 4 electrons with another hydrogen atom, and now we have methane, which is going to be a nonpolar covalent bond. And so here's that electronegativity. Remember, as we go up on the periodic table, it's going to increase, and then as we go across, it's going to increase as well. Now, why is it increasing when we go up? It's because the atoms are becoming smaller, and as the atoms become smaller, those electrons are closer to the nucleus, and so there's going to be a greater charge. And as we move across, you can see the electronegativity is increasing as well because we're increasing the amount of positive charges on the inside, and so we're increasing that pull. And so you can see that fluorine is going to have the highest electronegativity on the periodic table. That means it wants electrons more than any other atom. And so if we have 2 atoms that are sharing electrons and the electronegativity differences are 0, we call that nonpolar. So oxygen, for example, if we look at oxygen, its electronegativity is 3.44. So if we compare it to itself, it's going to be no difference between the two. So that'd be a nonpolar bond. Same thing with nitrogen. Remember, if we're ever connecting carbon and hydrogen, they're going to share the electrons equally. And so we'd also call that a nonpolar covalent bond, like in methane. Now we can study these using a graph like this, where we put potential energy on one side and then we put internuclear distance between the two. So let's start with hydrogen, or H2. If we have 2 hydrogen atoms together, as we move them really close together, they're going to want to push on each other. In other words, there's going to be repulsion. As we move them farther apart, eventually they're going to get into an area where there's this sweet spot between attraction. And then as we move them really far apart, they're going to be so far apart that Coulomb's law says there's not going to be a great enough force to pull them together. And so if we're below this line, it's attraction. But what we'll find is when we have the perfect distance apart, we're going to reach what is the bond energy and the bond length of those 2 atoms. In other words, bond length is going to be how far generally hydrogen atoms are going to stay apart, and bond energy is how much energy would we have to put in to actually break that hydrogen apart. And so this graph is incredibly important. When we're looking at non-polar covalent bonds, what we're going to find is that their electronegativities are different. So this right here would be hydrochloric acid. If we look at chlorine, 3.16, and hydrogen, 2.20, there's a difference between those electronegativities. And so the chlorine is actually going to be a negative charge, and the hydrogen is going to have a positive partial charge. Or if we look at water, oxygen at 3.44, hydrogen at 2.20, and so the oxygen is going to pull those electrons closer to it, so you're going to have a partial negative charge here and then a positive charge out here. And that really allows us to have water attracting to hydrochloric acid. There's going to be a dipolar charge, and the connection between those two would be intermolecular at this point. And so how do you figure out what type of bond it is? Well, there's one quick way to do it. You could just look at their electronegativity differences on that chart. And if it's less than 0.5, it's generally going to be nonpolar. If it's between 0.5 and 1.7, it's going to be polar covalent. And if it's greater than that, generally it's going to be ionic, and we'll talk about that in the next video. That's not a great way to do it. Better ways are to look at what's being connected. Generally in covalent bonds, it's going to be 2 nonmetals. In ionic, it's going to be metal and nonmetal. And then more important than that, we should look at the properties. And so if we're looking at covalent bonds, generally we're going to have gases, liquids, solids, low melting and boiling point, and they're going to be poor conductors. But as we move to ionic, it's going to be a crystalline solid, high melting boiling points, and we're going to be good conductors, especially when we dissolve them in water. And so did you learn the following to rank polarity based on location of atoms in the periodic table? Remember, as we go up and to the right, we're going to increase electronegativity based on Coulomb's law in the shell model. And I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 32. It's on chemical change. If you were to take your mass every night before you go to bed and when you wake up, you'd find that on average you're going to lose about a half a pound of mass every night. Where does that mass go? Well, you're going to lose some of it physically. You're going to evaporate some of that water off the surface of your skin, and so we're going to just change that water that's a liquid into a water that's a gas. So that'd be a physical change. But we're also going to have a lot of chemical changes going on. In other words, you're taking in food and oxygen. There's going to be a series of chemical reactions going on called cellular respiration, and then you're going to breathe out water and carbon dioxide. And so you're losing mass every time you breathe out. And so there's an excellent Veritasium video that talks about this, and I'll put a link in the video description down below. But this video is about chemical change. And so change that we see in the laboratory, remember, is change that we're observing at the macroscopic level or at the very big level. So we can't really see the particulates. We can't see the atoms and the bonds as they break and reform. And so we kind of have to infer that through laboratory work. And so changes can either be chemical or physical in nature. If we have a chemical change, what we're doing is forming a new substance. In other words, we're breaking bonds, forming new bonds, and so we're creating something that wasn't there before. In other words, at the particulate level, we're creating a new substance. In a physical change, we still have the same substance we had before, it's simply just in a new form. And so example of a chemical change would be converting that food into carbon dioxide and water. A physical change might be taking that water and turning it into water vapor. And so what's some evidence that we can collect that would show that a chemical change is occurring? In other words, macroscopic evidence. Well, we might start to see a change in the odor, or we might see a change in the color. Perhaps we could have production of a gas. We might have change in heat, or we might have a change in the precipitate or the formation of a solid. What kind of evidence are we going to see that a physical change has occurred? It's simply going to be a change in the state. And so in the laboratory, what we're going to do is collect macroscopic data and then try to take that to interpret what's going on at the particulate level. And it's hard. We have to gather a lot of evidence, and sometimes we'll figure out it's chemical, sometimes it's physical change, and sometimes we don't know. It's just ambiguous. And so again, chemical change, this is going to be our evidence. If we see an increase in the gas or odor or heat or color or precipitate, we know a chemical change has occurred, but if it's simply a change of state, it's physical. And so let me give you these examples. You may want to pause the video at this point and try to figure out which of these are going to be chemical changes and which of these are going to be physical changes. So let's start with rotting fruit. Rotting fruit, do we have production of gas? Maybe. Do we get a change of color? For sure. Is it easy to go from rotting fruit back to fruit? Not really. And so what would we call that? That would be a chemical change. Let's say we're rusting iron or rusting a metal. What's that going to be? We would call that a chemical change. What's some evidence? I would see a change in color. When you rust things, you're actually going to see a change in heat as well. And it's hard to reverse that, so that'd be a chemical change. Let's say we take a pill of aspirin and we crush it up. Would that be chemical or physical? Well, I don't see change in color or heat or odor, no gas being produced. And so that's going to be a physical change. What about burning paper? What are we doing? We're actually combining it with oxygen. It'd be hard to go back to paper again. And so I would call that a chemical change. What about boiling water? We're adding heat to it, but the reaction is not generating heat. And so we would call that a physical change. This is a hard one. What about dissolving sugar in water? Well, when we dissolve the sugar in the water, it's still sugar inside the water. It's simply separated all those sugar molecules, and so we call that a physical change. What about melting butter? That would also be a physical change. It's still butter, we're just changing the form. It's now in a liquid. If we were to burn it, it's combining with oxygen, so we'd call it a chemical. And so what are some chemical changes that you should get used to measuring in the laboratory? One would be acid-base changes. And so this is a wonderful picture here. What we're doing is taking just cabbage juice, red cabbage juice, and we're adding different pH of a substance to it, and you can get color change here. And so that's color change is going to indicate that we'd have chemical change as well. What would be another one? Formation of a precipitate or formation of a solid would be indication that we have a chemical change. And then redox reactions. This right here is going to be a titration or a redox titration. There's going to be other changes that we can see. It could either be an acid-base titration where we're seeing a color change based on an indicator, or it could just be the reduction of a substance that's causing that color change. And so again, did you learn the following to evaluate macroscopic, in other words, at the large level changes, and then classify them as physical, chemical, or I don't know? Well, the big things are to look at evidence for chemical change, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 60. It's on driving non-spontaneous processes. Again, those are processes that don't occur without external energy. We also call them thermodynamically non-favorable. Sometimes we call them endergonic. But if we were to look at a free energy diagram like that, we're essentially looking at an uphill reaction where we have a positive delta G. If we shove on it, it's just going to return to where it was before. And so how do we lift that? In other words, how do we lift that when the reactants actually have less free energy than the products do? Well, there's two ways that we can do that. First of all, we could add energy from the outside. So this is just a model, but if we add energy from the outside, then we can lift those reactants and eventually have the energy of the products. Where's that energy coming from? It could externally come from electricity. For example, when we're charging a rechargeable battery, or it might even come from the sun. And so that's how a solar panel works or how a leaf works if we're looking at photosynthesis. Another way we can do it is we can couple it to a spontaneous process. And so if we were to look at an exergonic or an energy releasing process like this, where a delta G is less than 0, that's going to be a downhill reaction. So you could imagine if we were to couple those two together, and again, this is just a model, then we could take some of that energy released in that spontaneous reaction and use it in the non-spontaneous reaction. So again, in a non-spontaneous process, our delta G is a positive value. So our goal is to make it a negative value. In other words, make this spontaneous. And we can do that in one of two ways. We can take energy in from the surroundings. So for example, if we use electricity, like when we're charging a battery, then we can change that delta G to a negative value. Likewise, if we were to take in light, for example, in photosynthesis, we can turn that upside down as well. We can also couple it to another reaction or to another process. So for example, in our body, we constantly do this using a molecule called ATP. Every time we convert ATP into ADP, we release a little bit of energy, and we use that to do things like think and move and talk. And so let's start with the electricity. So if we're looking at a battery like this, why does a battery eventually run out? It's because our reactants had more energy than our products do. And so we're losing that energy. Now we're using that to do work, we're using it and losing it as thermal energy, but eventually you have a battery that doesn't work. And so how am I going to recharge it? I have to connect it to electricity. And what that electricity can do is it can actually turn those products into reactants and then add energy to them, and we can recharge that battery so we can use it over and over again. Likewise, if we look at life on our planet, most of us are heterotrophs. What does that mean? We take energy in our food. So we take energy in our food, for example, like in glucose, we combine it with oxygen, we make carbon dioxide and water. But when we do that, the reactants, in other words, our food and our oxygen, have a higher amount of free energy than the products that we produce. And so we would be stuck if it weren't for the autotrophs, if it weren't for plants. What they can do is turn that backwards. In other words, they can take that carbon dioxide and water and they can add energy to it. Now, where are they getting the energy from? They're getting it from the sun. And so how does photosynthesis work? Well, inside a leaf, you have chloroplasts, and inside the chloroplast, you have a membrane like this. And what it's doing is it's taking in energy from the light. What's it doing with that energy? It's getting its electrons excited. It's passing those electrons down an electron transport chain, and eventually those high energy electrons go back into your food. Now, who are they making that food for? Themselves, because they're going to do that same process of respiration. Now, whereas a lot of that energy goes to this where does it go? A lot of that energy goes to this molecule right here, ATP, which is used in energy coupling inside our body. And so again, we're using external energy to turn that endergonic reaction upside down. Now that's one of only two ways that we can do this. We can also energy couple. And so what's going on there, we're taking an endergonic reaction and coupling it to an exergonic reaction, or pairing a non-spontaneous with a spontaneous reaction. So inside our body, the molecule that we use over and over and over again is going to be ATP, or adenosine triphosphate. And on the end, it has these 3 phosphate molecules. And as this last phosphate pops off, it releases energy with it. And so that's going to be a spontaneous reaction. It's releasing energy, but then we can break our food down. And as we do that, that releases energy, which we can use non-spontaneously to create more ATP. And it's said that you go through your whole body weight in ATP every day. Now, what do we use that ATP to do? We use it to couple to non-spontaneous reactions inside our body. So for example, how do your nerves work? If we look at the lining of a nerve or the membrane of a nerve, we have the spontaneous release of the phosphate as we break down ATP, but we're using that for a non-spontaneous movement of ions inside and outside. If we look at a muscle, what we're doing is that spontaneous release of the phosphate is coupled to a non-spontaneous contraction of that muscle fiber. And so again, it's not like we're using electricity, it's not like we're using light, we're storing energy in molecules and then we're simply coupling that to exergonic reactions. So did you learn to explain how external energy and energy coupling can be used to drive endergonic reactions? I hope so, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 17. It's on dipole forces. Before we talk about dipole forces, we should probably identify what a dipole is. Water is a great example of one. We have 1 oxygen and 2 hydrogens, and since oxygen is highly electronegative, it's going to pull the electrons towards it. And so it's going to have partial positive charges where the hydrogen is and partial negative charges where the oxygen is. And so it's a dipole. What does that mean? If we ever have separation between the positive and negative charges, we've created a dipole from the positive to the negative. And so dipole forces are going to usually occur when we have at least one polar molecule. And so that's called a dipole. It's going to have partial charges, positive and negative. And so we can have a dipole force between a dipole and a dipole. So it's called a dipole-dipole force. We can use diagrams to figure out how they're going to orient themselves, and the most famous one is called hydrogen bonds. Hydrogen bonds are going to form when we have hydrogen bonded to either oxygen, nitrogen, or fluorine, and it creates a dipole. It's going to hold molecules together. We could also have an attraction between a dipole and an induced dipole. This is something that's not polar but can be for just a second. The strength of this force between the two is going to be based on the polarizability, in other words, how much we can make that turn into a dipole, and then the magnitude of the original dipole. And then finally, we can have a force between a dipole and an ion. This is going to be really important when we're using dipoles to break down solutions. An example would be water breaking down salt. And so before we get into dipoles, make sure you understand the difference between intermolecular and intramolecular. Intermolecular is going to be between molecules, like interstate goes between states. And so the force between this one molecule of hydrochloric acid and this one is going to be an intermolecular. Intramolecular is going to be the covalent bond between the chlorine and the hydrogen. Likewise, we could have water around salt. They're going to have an ionic bond between the chlorine and the sodium ions, but it would be an intermolecular between the water and the ions themselves. Also, this helps explain the difference between real and ideal gases. Remember, ideal gases are just theoretical, but as the gases become closer to a liquid, as they start to condense, we're going to start to have attractive forces, and some of these are going to be dipole-dipole forces. So let's look at a specific dipole. Let's say we have hydrochloric acid. Hydrochloric acid is going to have 1 atom of hydrogen and 1 of chlorine. Chlorine is going to pull that electron towards itself, and so it's going to have a partial positive and negative charge. Positive is going to be where the hydrogen is, negative is going to be where the chlorine is. And so if we have 2 of these, what we'll get is a dipole-dipole force. It's simply a force between the 2 dipoles, and it's going to hold hydrochloric acid together. So if I had a bunch of hydrochloric acid molecules and I put them like this, they could never exist like this, but let's say I put them like that, with all their negatives on the inside and positives on the outside, how do you think they would orient themselves? Well, it would be something like this. They're going to orient themselves so we have a negative to a positive to a negative to a positive to a negative to a positive. So imagine in hydrochloric acid we have all these interconnections going on. Now, a specific type of dipole is going to be a hydrogen bond. Hydrogen bonds are going to occur, lots of people think it's between hydrogen and something else. It's not that. So a hydrogen bond is going to occur when we have hydrogen bonded to either a nitrogen, oxygen, or a fluorine. And so in water, we have hydrogen bonded to oxygen. So when it does that, we're going to have unequal sharing, and so we're going to have a dipole. We're going to have negative side where the oxygen is and a positive side where the hydrogen is. Now let me show you where the hydrogen bond is. This is how water would really orient itself. This is going to be a hydrogen bond right here between the hydrogen and the oxygen of an adjacent molecule, or between this hydrogen and this oxygen of this adjacent molecule. And hydrogen bonds are incredibly important, and they allow small molecules like water to have pretty good bonds that hold them together. In fact, that's why it's really hard to change the temperature of water. It has a high specific heat. It's due to these hydrogen bonds. But we could find it in larger molecules as well. So if we're looking at the nitrogenous bases, these are the bases on the inside of DNA, this ladder. What's holding them together are going to be these hydrogen bonds. Hydrogen bonds are holding it. It's between the hydrogen and oxygen, or hydrogen and nitrogen of another molecule. And so hydrogen bonds are incredibly important. But again, they're dipole-dipole. We could also have a dipole-induced dipole force. Okay, what's this going to be? It's going to be between a polar molecule and something that has no charge at all. Well, it's something that has no charge, and noble gas is an example of that. So let's say we have hydrochloric acid molecule next to argon. Argon, remember, is going to have no charge. All the electrons are equally distributed. Well, as it comes closer, watch what happens as argon approaches hydrochloric acid. Some of those electrons on its surface are going to be attracted towards this positive charge of the hydrogen. And as a result, what we're going to create is a temporary dipole, or an instantaneous dipole. So it just happens for a fraction in time, but now we have this force holding them together, a force between the dipole and an induced dipole. Now, what's going to increase the ability to be induced? Well, it's going to be the strength of this dipole. The more strength there is in that polarity, the more likely we are to induce dipoles. And then the other thing is going to be the polarizability of that other atom or other molecule. The more electrons it has, the more likely those electrons can be tugged on, and we can make these instantaneous dipoles. And then finally, we could have an attraction between a dipole and an ion. And so a great example of this is how water dissolves salt. There are going to be huge bonds intermolecular between the chloride and the sodium ions, and that's why salt has this beautiful crystalline structure. But you know, if we add it to water, we can quickly break it down and can form a solution. Well, what's going on there? We have a chlorine ion, and then we have a sodium ion, and what's going to happen is the water will orient like this around that chloride ion. And so we're going to have the positive ends of the water attracted to the negative ends of the ion. If we look at the sodium, we're going to have the negative parts of the water attracted to the positive parts of the sodium. And so what they're really doing is kind of ushering these ions away from that original ionic compound. What happens if we remove the water? Then those ionic compounds come back again and we get that sodium chloride. So did you learn the following? That we could relate the real gas behavior to some of these intermolecular. Remember, as a gas gets closer to condensation, we're going to have more of these attractive intermolecular forces. Did you learn to relate the feature of a polar molecule to the attraction between them? Remember, this diagram shows that. You've got two dipoles, and you could probably turn it so you could orient it the correct way. And then finally, could we use Coulomb's law to explain why dipoles are attracted to ions? Remember, all it has to do is those partial charges of the dipole, in this case water, are attracted to the ionic charges, or the ions. And so that's going to allow them to dissolve it. And it's simply Coulomb's law, that attraction between positive and negative. And I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 48. It's on energy transfer, or how energy gets from one place to another. And a great example of that is in a four-stroke engine, so in an internal combustion engine. So if we start it plain, what really is going on is that we're taking in gasoline and air into a combustion chamber. There's an explosion which drives the piston down, turns a crankshaft. We're also getting rid of that exhaust. And what it's really doing is transferring the energy in that gasoline into mechanical energy of the movement of your car. Now we lose a lot of that energy to heat, but what we're really doing is moving energy from one place to another. And so imagine we have two systems, and that system 1 has more energy than system 2. If they're ever connected, we can transfer energy from one to another. Now the one we talked about in the last video was thermal energy, or energy transfer through what's called heat. But we can also do work, which is really applying a force over a certain amount of distance. And so that could be mechanical in nature, electrical, light, or it could even be chemical in nature. And so what we're really talking about is how we can move energy from one place to another and transfer that energy. Now in this chemistry class, you're really only going to do calculations related to volume change. And that's why I started with that internal combustion engine. As we change the volume inside that combustion chamber, we can do work based on that. To show that energy transfer, I want to start with a PHET simulation. And so in this simulation, on the left side is going to be the source of that energy. Then we're going to convert the energy in the middle, and then you can think of this as system 2 over on the other side. And so for the first parts of the simulation, we're just going to be heating up water. You'll see increases in temperature, but what you're really going to be able to see is how energy is being transferred from one form to another. And so we're going to have 5 different forms of energy, from mechanical all the way down to chemical. And remember that heat, or that transfer energy through heat, is going to be thermal energy. And so let me start it plain. So what we're doing is releasing mechanical energy from the water, which is turning a turbine and converting that mechanical energy into electrical energy. It's running a heater, which is heating up that water. Now let's say we change that source of energy to solar energy. Well, it doesn't do anything until I add a solar panel. And now it's going to convert that light energy into electrical energy. And that electrical energy, again, is going to heat up the water. And you can see that the amount of energy that we have is being conserved. Now let me add a little bit of steam, so we're getting the mechanical energy of the flow of that water molecules, a lot of thermal energy, and now that's turning a turbine again, which is creating electrical energy, and that electrical energy again is heating up that water. We're getting higher kinetic energy in the water, and we're transferring the energy in heat as heat. Now let's put this girl on a bike, and what she's doing is converting chemical energy inside her body into mechanical energy. We're giving off some of that energy as heat, but that again is turning a turbine again. Oops, we got to feed her and give her a little more chemical energy, and we can make that water boil, or we could transfer it into a light bulb where we're heating up that filament. You can see thermal energy, and then we're giving light energy back again. As long as we keep feeding her, everything is going to be good. And so through this simulation, you can see that we're transferring energy. We're transferring that energy either as work, or a force applied over a distance, or we're releasing some of that energy as thermal energy or heat. And so in thermodynamics, which is really what this unit is about, what we're dealing with is transformations that involve work, heat, and the transfer of energy. And that's really what thermodynamics is. And so if we were to look at that piston again in that internal combustion engine, what's going on? Well, we're changing that chemical energy that's found in the gas and the compressed air inside that combustion chamber, and we're transferring that into mechanical energy or work. And so what really happens in that piston is we have an explosion. And what that does is convert that chemical energy into the energy of the expansion of those molecules. And so what it's really doing is work on that piston, and it's driving that piston down. And then this occurs over and over and over again. And so did you learn to relate the magnitude, how big it is, the type, and the direction of energy transfer? Now what do we mean by type? Remember that type could be energy transfer through heat, or it could be energy transfer through work. And also, did you learn that the energy is going to be conserved? Well, I hope so, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 38. It's on elementary reactions. In other words, one step in an overall reaction mechanism. And so in this demonstration right here, what I'm doing is combining A and B. So A is going to be yellow, B is going to be this purple-gray molecule up here. And so you can see if I launch A at B, there's no reaction that takes place. And the reason there's no reaction is that there's not enough energy. In other words, as these molecules are colliding, there's not enough energy contained within the molecules to actually have that reaction go. So let me pull it back a little bit more and angle the shot. And I'm going to angle the shot of molecule A at B, and we'll find that, again, no reaction takes place. And so we have to have enough energy in a collision, and also it has to be oriented correctly. So now I'm going to pull it way back, hit it right on, and you can see that A is reacting now with B to make C, and then this is proceeding over and over and over again like that. And so in an elementary reaction, remember, we have to be looking specifically at the collision of those molecules. And so an elementary reaction is based on collisions. Again, collisions could just be made of one molecule, and you may want to think about that for a second. How do we have a collision just with one molecule? If we do, that's a unimolecular elementary reaction, and it's going to simply be A turning into products. A great example of this would be radioactive decay, when, for example, we have carbon-14 just decaying, and as it does that, that would be a unimolecular. It's just that one molecule with itself. This would be the rate law for that, and so it'd just be a first order reaction. If we look at two molecules combining together, then we get a bimolecular elementary reaction. So A, for example, combining with A to make products would be bimolecular. This is the rate law for that. So you can see that this is going to be a second order reaction. Or if we have A combining with B, like we did at that animation at the beginning, the rate law would then just be K times the concentration of each of those reactants, but both of these together are second order reactions. Now, can you imagine three molecules coming together at the same point in the same time? If they do, we call that a termolecular elementary reaction. It's incredibly rare, but when it does occur, then it would be a third order reaction. Again, collisions are going to create reactions between molecules, and so they have to have enough energy. If they have enough energy, we can start to stress those bonds and form new ones, and they have to be oriented correctly. In other words, they have to hit right on for us to have a collision. And so this is something I've talked about a lot, but really haven't explained it in detail. If we're looking at an equation like this, the stoichiometry, in other words, we're measuring how much we have on one side, and that could be in moles or grams, and predicting how much we should get on the other side is totally predictable. You can just look at the equation, make sure it's a balanced equation, and so there's huge predictability about that. But how fast it occurs, or that rate law, is not predictable. It's measurable. We have to measure it for each reaction. And you might have always been thinking, why is that? Well, the reason why is that every reaction as we write it doesn't show the whole picture. In other words, what we're really showing is the reaction mechanism. So it's all the steps that we have in that reaction. In other words, we're forming intermediates that are not even found in that overall reaction. And since it's much more complex than we might see, then we can't predict it. We have to measure it. But if we can break it down to these elementary reactions or elementary steps, and we know exactly how many molecules are hitting one another, then it becomes totally predictable. And so let's look at a unimolecular elementary reaction. So this is simply A breaking down into products. It would be a first order reaction, and a great example would be radioactive decay. So it's simply carbon-14 decaying over time. And so watch it during this animation. Look at how many of those reactions we have. And at the beginning, I just have a few carbon-14, so there's just a few reactions, and then again it slows down over time. Now let's add way more carbon-14. You can see that we're going to have a way quicker reaction at the beginning because we have more of those molecules. Or if we even have more, look at all those starbursts that are showing that radioactive decay. And so again, these are just molecules by themselves, and so this one step would be a unimolecular elementary reaction. As we move towards a bimolecular, these are going to be two molecules hitting each other. So let's say A hits A. And in this animation, I'm not going to show you the actual reaction occurring, but what I want you to do is kind of count the number of collisions, if you can, in your head. So let's watch with 5 molecules. There's 1, 2, 3, 4. Now as I increase it, look how many collisions we're having, way more collisions. And then as we increase it to 20 molecules, way more collisions. So you can see why a second order reaction occurs the way it does, because we have so many more molecules, there's so many potential collisions that we could have. Now, we could also have different reactants, A hitting B, and let's say it starts to form C over time. Well, we're going to do the same thing here. Now we've got 5 of each of the molecules, so we can see the collisions. But again, not enough energy to start breaking them up. Now let's break it to 10 and 10. Now we're starting to see reactions occurring. And now let's do 20 of each, and you can see we have tons of reactions going because now we have more collisions, more energy at that point. That would be bimolecular second order. And then finally we can have termolecular elementary steps or elementary reactions. Let's say A plus B plus C forms a new product. So you could imagine, what are the odds of that ever happening? It's incredibly rare. They all have to come together at the same time, have enough energy, and then be oriented correctly and make a product. It does occur, and when it does, it would be a third order reaction. In other words, it's the concentrations of A times B times C. And so did you learn that elementary reactions are simply steps in an overall reaction? And if we know what that elementary step is and we know how many molecules are colliding, then we can make predictions about the rate law. And I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 50. It's on energy changing processes. This is a picture right here of Seattle, and this is a picture of where I live. This is Bozeman, Montana, and both of these have about the same latitude. In other words, they're each about the same distance from the equator. But if we look at their average high temperatures throughout the year, we'll find that Bozeman's is going to fluctuate. And so in January, it's going to be relatively low, and it's going to get pretty warm in the summer. But if you look at Seattle, it's going to be more temperate. In other words, its high is not as high, and its low is not as low. Now, what's causing that is the ocean. The Pacific Ocean is, during the winter, it's actually releasing heat into the surroundings, and during the summer, it's consuming that heat. And water has a really high specific heat, and so it's good at moderating temperature in a city and also inside your body. And so in a chemical system, energy can move into a system or it can move out, or we can see energy changes. And so if we're heating or cooling a system, or if we're transitioning from one phase to another, or if we're going through a chemical reaction, we can have energy go in or energy come out. And so if we're heating, we're obviously adding energy to a system. If we're cooling, we're removing energy from that system. And we can measure the amount of energy that's consumed or released in different materials using a term called specific heat capacity. If we look at phase transitions, in other words, going from a solid to a liquid, or from a liquid to a gas, we're adding energy to a system. And likewise, when we remove that energy, we can condense or we can freeze that material. Now, we measure that in different materials using something called the enthalpy of fusion or the enthalpy of vaporization, depending on which phase we're actually switching between. And then in a chemical reaction, we can add energy to the system, and that would be an endothermic reaction, or we can release energy from that chemical reaction, and that would be exothermic. We measure the amount of energy in different materials or different reactions using the enthalpy of reaction. And so let's start with a little simulation here. So what we have is some iron, and we're heating it up. And so when we heat it up, we're adding energy to the iron. That's kinetic energy of those molecules, and a lot of that energy is eventually going to be released to the environment. Likewise, when we cool something down like water, then we're removing energy from it. It has a lower amount of energy. If I take a warmer object like iron and put it in that colder water, you can see that energy is now flowing out from the iron into the water. And we'll talk more about this process in the next video on calorimetry and how we can measure that. But know this, if we heat something up, that means that we're adding energy to it. And so if I have two beakers and they have the same amount of water in each one, and one is 1 degree and one is 25 degrees, which one has more energy? Well, it's going to be the one that's warmer. We've added more energy to that. And so we're going to represent that as these little cubes. And so what were to happen if we were to put this warm object next to this cold object? Over time, we're going to see energy flowing from the warm to the cold. And so we're going to start to approach thermodynamic equilibrium. And so I have a time lapse here, and this is simply a glass of ice that's going to melt over time. And so what happens as it melts is it's adding energy to that ice. It's speeding up the molecules, and it's going to change from one phase to another. And then likewise, as we cool it down, we're going to remove energy from that system. And so if we let it run like this, we can see over about an hour and a half, that's changing from ice to water. And so what's happening is energy from the surroundings is flowing into that system. And so if we were to look at the energy around the glass, it's actually decreasing. Now if we were to run that backwards and freeze that again, what would be happening? Well, we're removing energy from that system, and that energy is going to move to the surroundings. A freezer does this, and if you ever put your hand behind a freezer, what you'll find is there's heat there, and that's because we're removing heat from that system. And so a way that we measure the different amounts of energy added or released as we heat something up is using a term called specific heat capacity, and it's going to be different in each of the different materials that we have. So you can see here in gold it's going to be a relatively low number, and we measure that in joules. That's the amount of energy or the heat divided by the grams degrees Kelvin. And so the matter, or the amount we have there, is important, and the temperature that we're increasing is going to be important as well. So as we heat this up, we'll find that the one that has the highest specific heat capacity, that is water, its temperature is going to change the least amount. And so we can measure how different things are heated or cooled at different rates using specific heat capacity. And so as we move phases from solid to liquid to gas, obviously we're increasing the temperature of that. But as we switch between one phase and another phase, we find something kind of interesting. If we look at the heating curve of water, what we'll find is as we add heat to it, we're going to see an increase in the temperature. In other words, the ice is going to be cold, and as we add temperature to it, it's going to increase. But what's interesting is it'll flatline for a while. And why is it doing that? Well, it's making this transition from either ice to water or water to water vapor. And so during that solid liquid transition, as we switch from one phase to another, we're actually adding energy to it, but we're not increasing the temperature for a while. Likewise, as we move from water to vapor, the same thing is going to occur. And that's because we require a certain amount of energy to switch from one phase to another. And so if we look at that same kind of a diagram, to go from solid to liquid, we have to add energy, and that's called the molar enthalpy of fusion to switch from one to another. It's going to be different in any material or substance that we have. You can see in water and iron it's going to be a different amount. The molar enthalpy is simply measured in the kilojoules per mole, so it's going to depend on the amount of material that we have. Likewise, as we move from liquid to a gas, we're going to add that molar enthalpy of vaporization, and so that's going to be a positive value. We have to put energy into that system to get that phase change to occur. Now likewise, if we go in the other direction, as we go from a gas to a liquid, then we're going to have a negative molar enthalpy of vaporization. It's the same thing, but in this case it's actually releasing energy to the surroundings. And likewise, as we go from a liquid to a solid, we're going to see a release of energy as well. The values are exactly the same, it's just going to be negative in value. We also have chemical reactions, remember, and those can either be exothermic or endothermic. Those can be releasing energy or they can be consuming energy. And so, for example, the thermite reaction, when we're taking iron oxide and aluminum and then we're reacting that together, if we look at the energy diagram, we find that the reactants have a higher amount of energy than the products do. And so over time, what's happening is we're seeing an enthalpy of reaction. We had a higher amount of energy in the reactants than the products, and so where did that energy go? It came out of the system. It was released out of the system. And so how do we figure that out? Well, there's an equation. We just look for enthalpy of reaction. We look at the amount of energy in the products, and we subtract the amount of energy in the reactants. And so since the products right here is a lower value than the reactants, we'd find that our enthalpy of reaction is going to be a negative value. Again, what does that mean? It's releasing energy into the surroundings. If we were to look at an endothermic reaction, like this ice pack reaction, when we're breaking down ammonia nitrate, what's happening here is the reactants have a lower amount of energy than the products. And so if we calculate that same thing, that enthalpy of reaction, we find now that since the products are greater than the reactants, we now have a positive enthalpy of reaction. So where is that energy going? That energy is being consumed by the system. And so what it's doing is it's really cooling down the surroundings, and that's why it gets very cold around an ice pack like that. And so did you learn to relate energy change to the specific heat capacity? Again, that's just heating or cooling. The enthalpy of fusion and vaporization, again, that's going to be phase changes. And the enthalpy of reaction, I hope you did, and I hope that was helpful. Hi, it's Paul Anderson, and this is video 1 in the Chemistry Essentials series. The history of chemistry goes way back to the alchemists. The alchemists searched for what was called the philosopher's stone. It was this magical stone that they thought could turn something like lead into gold. Now, they never discovered the philosopher's stone, but they did start to discover some unique properties of elements and molecules. And the whole thing eventually led to this atomic theory, this idea that all matter is made up of smaller units, and those are going to be called atoms. And so in this video, I'm going to talk about mostly molecules and elements. And so all matter can be broken down either into mixtures or pure substances. And those pure substances are either elements or molecules. So an example of an element could be pure gold, an example of a molecule could be water, and an example of a mixture could be dirt. And so if we take those elements and molecules, they're each made of atoms. In other words, gold is just going to be made of those gold atoms, and then water is just going to be made up of oxygen and 2 hydrogen atoms. And so if we were to take a pure sample of it, it's only that element, we would find that no matter how big the size of that object is, it's going to have the same average mass. Likewise, if we were to take a pure sample of a molecule like water, we're going to find that there's the same ratio of the average masses. In other words, the average mass of the oxygen and the average mass of the hydrogen. But let's say we find something else that's made of oxygen and hydrogen. A good example could be hydrogen peroxide, which is actually 2 oxygens and 2 hydrogens. We would find since it has a different atom number, it's going to have different ratio of average masses. It's still going to have a consistent ratio through all different sizes of the objects, but it's going to have a different ratio compared to that of water. And so what do we mean by a pure sample again? A pure sample is just going to have those atoms from either that element or molecule inside it. So this is a pure sample of gold. If we were to look at a pure sample of silicon, it's going to look like this, or lead is going to look like this, or uranium. In other words, if we were to dig through it, we would find just uranium atoms in this pure sample. Likewise, if it's a molecule like water, we're just going to find 2 hydrogen and 1 oxygen connected together, and we're just going to find that repeating over and over and over again. Or if we were to look at something like dry ice, which is simply solid carbon dioxide, we're going to find that it's going to be the same atoms in a specific ratio over time. And so again, one of the big points is that the average mass is going to stay the same no matter how big the sample. In other words, the average mass of this, which is the largest gold bar ever created, it'd be worth about $11 million. So it's about 500 and some pounds. If we were to take the average mass of that whole gold bar, or the average mass of a section of it, or a smaller section, or a smaller section, it doesn't matter how small the section is, it's going to have the same average mass. And that's because it's made up of these atoms. And so let me kind of explain that. Let me use an analogy. Imagine I'm building something out of Legos. I'm using that standard 2x4 Lego brick. Well, that weighs about 2.5 grams, one of those Lego bricks. And so let's say I built something that was made up of 4 of them. It's going to weigh 10 grams, or let's say I built something that had 32 of them. It's going to be 80 grams. But if we were to look at the average mass of those objects, we're going to get around 2.5 grams per brick. So it doesn't matter how large or small the sample is. If I had a big structure that was the size of this room made out of these red Lego bricks, it's going to still have the same average mass. And we find the same thing in matter. That's because it's made up of these atoms. And so it doesn't matter if we have 4 atoms of gold or 32 or billions of atoms, it's still going to have that same average mass. Now, this is just elements we're talking about, but the same thing applies to molecules. So if we're looking at water, small, smaller, and smallest sample of water are still going to have the same average mass. And how does that work? Well, imagine we go back to the Lego analogy. If we've got one Lego brick that weighs 2.5, so we can think of that as like the oxygen molecule, and then we had 2 of these little blue bricks, each of those weigh 0.25 grams, then we're going to have a total mass of 3.00 grams. And so it doesn't matter if we have 1 of those units, or 4 of those units, or 32 of those units, it's still going to have the same average mass if we divide by the number of units like that. So that's an example of water. But let's say we were to try using the same atoms in this analogy, so just the red and the blue, but we were to put it together in a different structure. And so let's say our building blocks look like this. So instead of building with 1 red and 2 blue, what if we were to build with 2 red and 2 blue? This is going to be a lot more like hydrogen peroxide. Well, now we're going to get an average mass that is going to be higher because we're adding more units to it. And so if we were to look at two molecules that have the same atoms, oxygen and hydrogen, but they have them in a different ratio, then we're going to get a different ratio of their average masses. And so let's kind of review. Could you pause the video and fill in these little blanks? What goes here, 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 and here? Well, up at the top, so those are going to be elements and molecules. They're made up of atoms. They're going to make the same ratio of average masses, and then they're going to have a different number of atoms down here on the side. And so this is just an introduction to chemistry. What did you learn? Well, you should have learned, that was my intent, that the ratio of masses in a pure sample is identical on the basis of atomic theory, and that's going to apply for elements and molecules. And I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 33. It's on endothermic and exothermic reactions. If you understand that therm means heat and exo means to exit or to move out, it's pretty easy to break down these reactions. So an exothermic reaction would be one where heat is being released from the reaction. So a thermite reaction right here, you can almost feel how hot that is a reaction where we're releasing energy, releasing heat from the reaction itself. And likewise, if we have an endothermic reaction, that's going to be one where the reaction is taking in heat. And so in a cold pack like this, there's a combination of water and ammonium nitrate. That reaction is consuming heat. It's taking it from the surrounding, and so it's going to feel cold over time. And so you really have to understand what is the system and what are the surroundings. And so in a reaction, the system is going to be where the reaction is taking place, so in the chemicals themselves, and then the surrounding is going to be outside of that. So if we have a change in heat, that's either going to be an exothermic or an endothermic reactions. Now in the lab, we can't really see at the level of the atoms, and so we have to view it macroscopically. And we do that by simply measuring the temperature change. And so in an exothermic reaction, we're going to find that heat is being released from that reaction to the surroundings, and in an endothermic, it's actually being absorbed. Now a really neat way to observe this is to use a model, is to use an energy diagram like this. And so the way it works is that the energy progress will be going along the x-axis, and then the amount of energy in the reactants and products is going to be displayed. And so in an exothermic reaction, what you'll see is a downhill reaction. In other words, the reactants are going to have more energy than the products. Now where is that energy going? Where is that heat going? It's going to the surroundings. And likewise, in an endothermic reaction, the reactants are actually going to have less energy than the products. And so they're consuming that energy. And so let me give you an example of that. Here's that exothermic reaction again. We've got a thermite reaction where we're taking iron oxide and aluminum, and we're making iron and aluminum oxide. Now this is a really intense reaction, and it provides the oxygen in this form of combustion. And so this should be able to work even underwater. But if we were to look at the energy diagram of this over time as it progresses, we'd find that these reactants, the iron oxide and the aluminum, have a higher energy. In other words, there's more energy locked in those bonds than we're going to have in the products. And so we can see this as a downhill reaction. Now, what's going on? Why do we see this increase in energy here? Remember, we have to start pressuring those bonds, put a little bit of pressure on it before we can actually have them break apart, and we get that exothermic reaction. And we call that a activation energy. So you're going to put a little bit of energy into the system, but you can see that we're going to net energy coming out of that. And so that's going to be measured in heat coming off that thermite reaction. Now if we look at an endothermic reaction, again, this would be like solid ammonium nitrate, and we're just combining it with water. So we're going to make ammonium and nitrate ions. In that case, what we're doing is the reactants are actually going to have a lower amount of energy than the products. And so you can see here's our activation energy, but this is an uphill reaction. In other words, it requires energy, it requires heat. Where is it getting that heat? It's getting it from the surroundings. And so when we're measuring ectothermic or exothermic and endothermic reactions in the lab, we're really stuck with the temperature itself. And so if I wanted to measure a reaction like this, let's say I take a chemical and I mix it with water or mix it with another chemical, I can simply use a thermometer to measure what's going on. And so I see a decrease in that temperature. Okay, so what's happening? It's actually consuming heat from the surroundings. And so this would be an endothermic reaction. And so that's pretty simple. What you should be able to do after you're done is to generate a relevant symbolic and or graphical representation of the changes. Remember, we use an energy diagram to do that. It's all about the heat, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 34, which is on electrochemistry. In electrochemistry, what we're doing is generating current. We're actually generating moving electrons in a reaction, or we're requiring those. And so if you don't understand what a redox reaction is, you may want to look at that video. But a great example of electrochemistry could be a lemon battery. All we're doing is inserting two pieces of metal into the lemon, and we're going to generate voltage. Now, you'd have to hook it up to a pretty sensitive voltmeter to measure that voltage, but if we hook a number of lemon batteries up in series, we could actually light a little LED. And so electrochemistry is really the study of redox reactions, and we're separating the reduction and the oxidation portion in space or time. Now, when you do that properly, you've created something called an electrochemical cell. That cell could either be a galvanic cell. It's sometimes also referred to as a voltaic cell. An example could be a battery, and that's going to generate current. Or we could have an electrolytic cell, and that's going to require current. An example could be a rechargeable battery. And so what we're doing, remember, is separating the reduction and the oxidation. In review, reduction is the gaining of electrons, and oxidation is the losing of those electrons. And what we're doing is tapping the flow of those electrons. Now, the metal is either a cathode or an anode. And a quick way to remember that is that reduction always occurs at the cathode and oxidation at the anode. Or a better way to remember that is that the consonants R and C are going to pair, and the vowels, the O and the A, are going to pair as well. And so what we can do is analyze this cell. We can break it down into its two half reactions. We could figure out the potential of those two half reactions and then simply add them together to figure out the standard potential. So how much energy that cell could produce or require if it's electrolytic. Now this would be at STP, standard temperature and pressure. And so if we have variance from that, then we could use Le Chatelier's principle to qualitatively measure what's going on. We can also measure stoichiometry in a cell. So we could use Faraday's laws to qualitatively measure that as well. And so let's start with a simple demonstration. Let's say we take zinc solid and we immerse it in a copper solution. What will happen over time is we're going to get a reaction. And what you're going to find is that zinc is going to start to become an ion dissolved in the solution, and the copper is going to start to form a solid. So you'll actually form the solid copper on the outside. And so that's a redox reaction. It's reduction, it's oxidation. There's electrons flowing there, but we're not tapping any of those electrons. And so this would be that whole redox reaction. Again, we have the zinc, which is losing those electrons, and the copper, which is gaining those electrons. And so if we break it down into its two half reactions, it's going to look like this. Oxidation is where the zinc is losing its electrons, and the copper is gaining those electrons. Those are the two parts. And so in a cell, what we try to do is separate those. But before I actually show you the cell, I want to talk about the reduction potential. In other words, that's the potential energy that can really be released in a reaction like this. And so the zinc being oxidized is like a waterfall. In other words, it has energy up here and it's releasing that energy. And we could measure it as 0.76 volts. And so you could look up standard reduction potentials and you'll find a list of these for a number of different reduction and oxidation reactions. Now the cool thing is if we run it in the other direction, then it would be negative 7.6 volts. In other words, it'd be like trying to move the water up again. It would require that energy. So if we look at the reduction part, this copper gaining of electrons, it's going to have a reduction potential, or an E naught, of 0.34 volts. Okay, now let's actually build that cell. Let's separate the reduction and the oxidation portion. And so over here we have the anode. That's going to be where that oxidation takes place, that oxidation of the zinc. And then we have the cathode, and they're each going to be in a different solution. So right here we've got copper metal in a copper solution, and then over here we have zinc ions in a zinc solid in a zinc solution. And if we just let it sit like this, nothing will happen. In other words, it's not going to generate any voltage if we had a little voltmeter here up at the top. And the reason why is that we haven't completed the circuit. And so to do that, we're actually going to have to add a salt bridge. A salt bridge is going to be filled lots of times with a gel. In this case, we've got sodium nitrate, and what it's going to do is it's going to allow the ions to actually flow. So once we've added the salt bridge, this thing's going to turn on. And electrons are going to flow from the anode to the cathode. In other words, the electrons that are being lost in this zinc metal as the zinc becomes a zinc ion are going to travel through the wire to the cathode, where they're going to actually pick up those electrons. And so let's talk about what's going on over here on the anode. This zinc metal, this zinc solid, is actually moving off into an ion in the solution itself. As it does that, it's losing those electrons. And so it's also losing mass. In other words, this anode is going to lose mass over time. If we look over on the other side, the cathode is actually going to gain mass because that copper that's in solution is going to combine with those electrons that are coming over from the anode, and it's going to form a copper metal. And so we could see that the voltage is 1.1 volts. How did I get that 1.1 volts? I simply added up the reduction potential of those two half reactions. Now, how long is this going to occur? It's going to occur until it reaches some kind of an equilibrium, and so it won't last forever. Now, there's a Nernst equation you could use to analyze what happens if it's not really at standard potential, but that's outside the level of AP chemistry. What you should really use is Le Chatelier's principle. So what would happen, for example, if we increase the amount of zinc on this solution? That would slow this reaction. Or if we were to increase the amount of copper, it's going to speed up this reaction. What happens if we increase the temperature? That's going to speed up the chemistry. It's going to speed up this reaction, and it's going to be quicker. In other words, we're going to generate more volts than we would if it was at a cold temperature. And so you should qualitatively kind of understand how a chemical reaction, or things that would affect a chemical reaction, could convert to things that would affect this cell. Now, what's an electrolytic cell? It's really essentially the opposite of that. In this one, what we're going to do is add current. In this case, we're adding a battery on this side, and we're actually going to cause electrons to flow. Great example of this could be electroplating, when we're actually adding one metal to the other side. Another example could be rechargeable batteries. And so a rechargeable battery works is you hook it up to electricity, and what it does is it acts as an electrolytic cell. It's going to store energy inside the cell. Now you unplug it from electricity, and now it becomes a galvanic cell. It can actually release energy. And so we can also use Faraday's laws to really study stoichiometry. In other words, what's happening to changes in the mass. And there are two laws. The first one is an equivalence between electricity and the mass. In other words, the more electricity that we apply to a cell, it's directly related to the amount of mass that a cathode or an anode is going to gain or lose. We also have an equivalence in Faraday's second law to the mass loss is going to be equivalent to the equivalent weight of that cathode or anode. What does that mean? Well, if we have something like copper and silver as two of our electrodes, what we would find is that silver, since it has a higher molecular weight, is going to actually lose more mass over time. And so that shouldn't seem surprising if you're looking at it as the losing of atoms from either the anode or the cathode. And so you should have learned the following. Did you learn to analyze data from galvanic or electrolytic cells? In other words, can you identify what is the reduction part and what is the oxidation part? And then finally, could you apply half reactions? Again, we did that with reduction potential or Faraday's law to see what's going on in a cell. Well, if you did, you learned what I hoped you would learn, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 53. It's on the enthalpy of reaction, which is the amount of energy taken in or released during a chemical reaction as bonds are broken and new bonds are formed. And look no farther than nitroglycerin for a reaction that creates a huge amount of energy. It was used by Alfred Nobel, a scientist and explosives expert, but it was highly unstable and his brother was killed in one explosion. So he invented dynamite, which essentially stabilizes nitroglycerin by wrapping it in some kind of cellulose. And so it was used not only in mining and construction, but it was also used in war, leading some people to call Alfred Nobel the Merchant of Death, which made him feel a little bit bad. He put all of his money into a trust and then created the Nobel Prizes, which are famous to this day. And so in the enthalpy of reaction, what we're looking at are the reactants and what are called the bond energy, the amount of energy it takes to break the bonds in the reactants, and then the amount of energy that is released in the products, which is essentially the negative bond energy. And you can think of putting these on a balance beam. And if there's more reactant energy consumed, we would call that an endothermic reaction. If there's more released, we'd call that an exothermic reaction. Now remember, these reactions sit in their surroundings, and since energy can neither be created nor destroyed, in an endothermic reaction, thermal energy is going to go from the surroundings into the reaction. That's going to cause that reaction to feel cold. And the opposite if we're looking at an exothermic reaction. Now, if we're looking at the amount of enthalpy reaction there is, Hess's law is something that kind of lays outside of what you should know in AP chemistry, but there's a few ideas that you should really be able to apply. And so if we look at an exothermic reaction like this thermite reaction, we can look at the energy of the reactants and the energy of the products, and we can see that this is a downhill reaction. In other words, we're releasing energy, and that energy is called the enthalpy of reaction. Now, it's given off from that reaction as heat into the surroundings. If we were to actually measure it, that's going to be the change in enthalpy, which is simply the enthalpy of the products minus the enthalpy of the reactants. In this case, it would be negative 850 kilojoules per mole. Now, if I were to show you an enthalpy diagram, it would simply look like this. An enthalpy diagram is different than an energy diagram in that we simply put the enthalpy of the reactants and the enthalpy of the products. Since we're subtracting the reactants from the products, in other words, since the products in this case is lower than the reactants, we're going to get a negative value, negative 850 kilojoules a mole. Now, what does that mean? Where does that energy go? It's going to go as thermal energy to the surroundings. Now, something interesting is that if we actually turn that reaction around and make the reactants the products, look what happens to the change in enthalpy. It stays the same. The only thing that changes is going to be the negative value that was in the front. And if we swap it around again, it's going to be that negative again. And so this is the first of Hess's law ideas that you should understand. That is, if we reverse the reaction, then we have to reverse the sign in that change in enthalpy. If we look at an endothermic reaction, in this case we have an uphill reaction where the products actually have more energy than the reactants. And so this is going to be our enthalpy of reaction. It's moving from the surroundings as thermal energy into that reaction itself. We could measure it and we would find that it is a positive value. Now, how do we measure that? We're going to use a calorimeter, remember. We're going to have the reaction take place surrounded by water. We can measure the change in that heat of the water and we can measure that enthalpy change. It's a positive value or an uphill reaction, and the reason why is that our products have a greater enthalpy than our reactants. Now, we don't have to know what that energy is to begin or at the end. We just have to know what that change is in order to measure enthalpy. Now, what's interesting, if we take a look at a reaction, we find that it's usually made up of a number of smaller reactions. And so in this Born-Haber cycle, what we're doing is taking lithium solid and combining it with fluorine gas, and we're making lithium fluoride. Now, if you look at that change in enthalpy, see, it's very small, and it's going to be an exothermic reaction because it's negative. But if we look at all the steps of this reaction, this would be an endothermic, this would be endothermic, this would be endothermic, and then we have two exothermics. And so this is the next of Hess's law that you should be able to apply. And that is that the enthalpy of the reaction is equal to the sum of all of the reactions that make up that reaction. So lots of times in chemistry, you'll be given a target reaction, and then you're going to have parts of that reaction. And your goal is to figure out the change in enthalpy of that whole reaction. It's pretty simple algebraically to solve this, as long as you remember those two parts of Hess's law, that if we reverse the reaction, we have to reverse the sign, and then the sum of all the parts is equal to the sum of the whole. And so if I look at this equation right up here, I've got my carbon on the left side, and so that's good, but you can see here that I have my carbon monoxide on the left side, and I eventually want it on the right side. You can see here that I have two exothermic reactions, and so the first thing that I could do is I could simply switch this reaction around. That's totally legal. Watch what happened to my delta H. My delta H now is a positive value, and so I can change the reaction around, and then I'm good to go. If you look at this, I've got carbon dioxide on the left, carbon dioxide on the right side, and so I can actually cross those off. And now I'm kind of left with almost just what I want. There's one problem here. I could move my carbon down here. I could move my carbon monoxide here. And I'm left with my oxygens. Well, on the left side, I have one O2. On the right side, I have a half of an O2. And what am I looking for? A half of O2 on the left side. So what I can do is I can simply cross that off. And now I've just got a half O2 on the left side. And so now I've totally got my reaction. All I do now is I simply add these up. So algebraically, I can add these up, and this is going to be the delta H of that whole reaction. Let's try a little bit harder one. Now you could pause the video at this point, and you could try this on your own. That'd be a good thing to do. I'll wait for you. Okay, so let's get at it. So here's our target equation right down here. And so you can see here that I have my NO on the left side, my nitrogen monoxide, and so that's good. I'm going to leave that there. But I really want is my oxygen all by itself on the left side here. So I'm going to take this and I'm going to turn this equation around. You can see that I got a negative value right here. So that helps out a little bit. You can see here that I have two ozones on the left side, and so if I could get those to cancel out, that's going to help me a little bit. So I could switch that around. So these are going to cancel, so that's good. What am I missing then? I got my nitrogen dioxide on the right side. Well, you can see here that I really want just one of these on the left side, and so what I could do is I could take that whole equation times a half. Well, if I take that whole equation times a half, watch what's going to happen to my delta H. I'm going to have to take that times a half as well. Okay, so let's see how we're doing so far. I got my ozones. I can get rid of those. Now if we get to the oxygen, this is really convenient. You'll find this is lots of times very convenient. On the right side now, I've got one O2 plus a half, so that's 3/2 of an O2, which is the same that I have on the left side. So I could cross out all my oxygens. Now I simply add that up. There's my target reaction, and now I simply add up all my delta H's, and that's going to be the overall exothermic reaction that I'm looking at. Okay, so did you learn qualitatively and quantitatively patterns in enthalpy of reaction? Again, it's simply a balancing act. We look at the energy it takes to break the reactants, the energy formed by the products, and whichever way that balance tips, it's going to tell us what kind of a reaction it is, and then we combine reactions to figure out the sum of all the parts. And I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 57. It's on entropy, which is really the dispersal of matter and energy. So imagine I had a little bit of milk in a glass and I were to spill it. I will have increased the entropy of this isolated system. And there's an old saying that you shouldn't cry over spilled milk. I totally disagree with this. You should cry over spilled milk. And the reason why is it's an irreversible process. In other words, it's not just going to magically move back into the glass. You've increased the entropy, and it's going to take a lot of work to put it back where it was. And so entropy in AP chemistry is not something that you'll have to calculate. You have to understand it qualitatively. In other words, you have to look at a system and figure out what's happening to delta S. And so what is delta S? That's simply the change in entropy over time. Now, what does this little degree symbol stand for? That means that we're measuring it at standard temperature and pressure. And so if we were to look at a system, we should be able to make predictions about what's happening to our delta S. And that's what I hope you can do at the end of this. And so if we define it, it's simply dispersal. Dispersal of matter and dispersal of energy. So what are some examples of that? Let's say we were to make some phase changes. We were to go from a solid to a liquid to a gas. What would we be doing? We'd be dispersing or moving that matter away from its center point, and so we'd be increasing the entropy. In other words, our delta S would be a positive value. We'd make that matter dispersed over time. We also could do that by stoichiometry. In other words, if I look at the moles before a chemical reaction and the moles after, if I have more moles after the reaction, I've increased the entropy. And also, if we take a gas and we increase its volume, we're moving those molecules apart, and so we're increasing entropy, or delta S is going to be a positive value. Now, let's say we look at energy. How could we disperse energy? Well, by increasing temperature. If we increase temperature of gas, according to the kinetic molecular theory, we're spreading that energy out and we're increasing entropy. Now, entropy is a term that people really struggle with, and so I wanted to start with a good example. And so I've got two videos here, but they're the same exact video. It's just that one of them is played forward and the other is played backward. And so your goal is to figure out which one is forward. So let me start playing that. It's just going to loop over and over and over again. And so your goal is to figure out which one is forward. Have you decided yet? The right answer is A, but that was kind of hard. Let's look at another one. I've got a little pendulum here, and let me play this video. Again, it's the same video clip. It's just that one of them is played forward, and the other is the same clip. It's just played backward. Have you figured out which one is forward? There's some clues in here, but the right answer is B. Let's look at the next one. It should be a little easier now. So if we look at the next one, I'm going to play this again. So again, same video. One's forward, one is backward. Hopefully you've figured this out. The right answer is B is being played forward, and A seems somewhat magical. It's being played in reverse. Let's look at the milk. So if we look at the milk right here, which one is being played forward? Hopefully you've figured this out. A is being played forward. Okay, and so why did I do that? Well, what we're looking at here are irreversible processes. In other words, if we play it in this direction, it's irreversible. In other words, it's impossible for it to occur in the reverse. Now, it's not totally impossible. That could occur, but it's statistically improbable that it's going to move in the other direction. And so that direction is really important when we start to talk about entropy. Because what happens during an irreversible process is that we're increasing the entropy, or the dispersal, of that system. And it just doesn't move back, and that'll become really important as we talk about the next few videos. And so the second law of thermodynamics says that in an isolated system, or a closed system isolated from the universe, entropy never decreases. In other words, our delta S is always going to be positive. In other words, matter and energy are going to become dispersed over time. In other words, randomness increases over time. Now, you might think to yourself, I know that's not true because I see stuff out there that's not random. In other words, I see trees and cars and DNA, and I know these things have a high amount of order. Well, you're not violating the second law of thermodynamics because remember, we're talking about an isolated system. And so we can decrease entropy in an isolated system, but as we do that, we're increasing entropy of the surroundings or the universe around it. And so again, to define entropy, what is it? It's simply matter dispersal, or matter spreading apart. And so let me give you an example of a certain type of matter dispersal would simply be phase change. So as we move from a solid to a liquid to a gas to a plasma, that matter is moving farther apart. And so as it's doing that, what we're doing as we move from a solid to a liquid to a gas is that matter is spreading apart. And as it does, we're getting a delta S, which is going to be a positive value. Now let's look at stoichiometry. You should be able to look at an equation like this and immediately figure out what's our delta S. Well, how do you do that? So if we've got our reactants on the left side and our products on the right side, we have 2 moles on the right side and only 1 mole on the left side. If we show you a picture of that, it looks like this. So we have dinitrogen tetroxide and we're making 2 moles of nitrogen dioxide. And so what are we doing? We're increasing the entropy. You try the next one. So if this is our equation, so we're taking liquid water and turning it into gas, hydrogen gas and oxygen gas. What's happened to the number of moles? Well, we've increased that. So our delta S is going to be a positive value. We're spreading that matter apart. Now there's another clue here as well. We're going from a liquid to gases, and so we really are increasing the entropy of this system. Now let's look at gas volume. As we increase the volume of a gas, so if we have a known quantity of that gas, as the volume gets larger and larger and larger, the matter is spreading apart, and so we're going to have a delta S that's going to be a positive value. So not only is entropy dispersal of matter, it's also dispersal of energy. So if we were to look at this Maxwell-Boltzmann distribution of a gas, what we would see is a curve that looks like that. In other words, these are going to be the number of molecules on the left. This is going to be their energy. You can see that some of them are going to have a high amount of kinetic energy, some of them are going to be lower. But if we increase the temperature, what does that curve look like? It's shifting everything over to the right side. So we're going to have more molecules that have a higher amount of energy. And so what's that doing to our entropy? It's increasing the entropy because we are increasing the dispersal of that energy. And so did you learn to predict the sign and relative magnitude of entropy changes associated with chemical and physical processes? Could you remember this one right here? I hope so, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 67. It's on equilibrium disturbances. In this reversible reaction, I have two aqueous solutions of cobalt. And so if I push it to the left, in other words, if I have more of these reactants, it's going to be a pink color. If I push it to the right, it's going to be more of the products, and so I'm going to have this blue color. And so what I can do is I can vary which way the reaction goes, to the left, pink, to the right, blue, and I can change color. Now, what's a good way to do that? Temperature, because as I change the temperature, I'm actually changing the equilibrium constant, so I can move it back and forth. And so in a reversible reaction where we have reactants and products, over time it'll eventually establish an equilibrium. And we can measure that using the equilibrium constant, which is essentially the concentration of products divided by the concentration of reactants. And that's going to stay the same over time. Now, before we get there, the reaction is going to be at Q, where we have the products and reactants over time, and eventually those two are going to be the same when we reach equilibrium. But what can happen is you can have disturbances that change our Q, and we have to reestablish K, and some disturbances that actually change that K value, and so Q has to approach a new K. Now let's dig in a little bit deeper and actually look at real K values. And so this is that Haber process. What we have here is our initial equilibrium, and then we have some kind of a disturbance, and then we establish equilibrium at the end. Equilibrium constant, remember, to figure that out, this is going to be our equation for that. We're going to write the concentration of ammonia raised to the second power. Where am I getting that from? Remember, we have 2 moles of that, so that's going to be raised to the second power, over our reactants, which is going to be concentration of nitrogen times the concentration of hydrogen raised to the third power. Why raised to the third power? It's because we have 3 moles right in front of here. And so let's figure out what our K value is going to be initially. Well, to figure that out, all we do is plug in the values. We plug in the concentrations of our H, in this case, is going to be 4, our NH3, which is going to be 3, and then our N, which is going to be 1. So if I plug in those values, I get 9 over 64, it's around 0.14. Now, if we move to that point where the disturbance occurs, let's figure it out there. What's our new hydrogen value? Our new hydrogen value is going to be 6. So I'm going to plug in a 6 here. What's going to be our ammonia and nitrogen values? Those are going to be the same. So if I figure out what my new Q value is, again, there's been some kind of a disturbance, our value is going to be 0.042. So our Q value now is lower than our K. And so where is this reaction going to go? It's going to move towards the right. And so we're going to move it to the right and establish a new equilibrium. So how does that occur? Well, we're going to decrease the amount of hydrogen. And as we decrease the amount of hydrogen, it goes from 6 down to 5. We're going to have to adjust our other values as well. So here is our new value. It's again K equals 0.14, and that reaction moved to the right to reestablish that. Again, that's a Le Chatelier's principle. Since our K value is going to be lower than our Q value, the whole thing moved over to the right. Let's look at temperature now and see how temperature affects K. And so in this reaction, we have colorless dinitrogen tetraoxide, and there's a reversible reaction where that can become nitrogen dioxide, which is going to be reddish brown. Now this is an endothermic reaction. What does that mean? As we move from the left to the right side, it's actually consuming energy. And so let's put that heat over on the right side. So what happens if we increase our temperature? If we increase our temperature, it's really like adding more reactants on the left side. And so it's going to push that reaction over to the right side. And so we're going to get a movement to the right. what's going to happen to our K value? Our K value is actually going to increase because we're going to have more products, and that whole thing is going to shift to the right. Now, what would this appear as we increase temperature? It's going to be darker in color because we're getting more of this reddish brown gas on the right side. And so in an endothermic reaction, what happens as you increase the temperature? You increase your K value. Let's look at what happens if we decrease temperature. As we decrease temperature, we're actually going to shift that to the left side. What's going to happen to our K value? Now our K value is actually going to go down, or it's going to decrease. And so there's a direct relationship between temperature and K as long as it's an endothermic reaction. Now let's look at an exothermic reaction. So in the Haber process, it's an exothermic, so we could put heat on the right side. What happens if we increase temperature now? That's actually going to push it to the left side. What's going to happen to our K value? It's going to go down. Likewise, if we were to increase it, it's going to go in the opposite direction. Here are some actual temperature and equilibrium constants for the Haber process. And you can see as we increase temperature, our K value is actually decreasing in an exothermic reaction. So if you want to increase yield, if we wanted to increase the amount of ammonia, we would actually lower the temperature. It's more complex than that because we want to speed up the reaction as well. And so did you learn to really apply Le Chatelier's principle to values of K and Q? I hope so, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 64. It's on chemical equilibrium, and I wanted to start with a demonstration. What I'm doing is moving water from one jar to another, and so these will represent reactants and products. And you can see that as I move it from the left to the right side, I'm using a larger glass to move that water from the reactant side to the product side, but as I try to move it back to the product side, I can't quite fill that all the way up. Now this would take about 7 minutes to do, so I'm going to speed it up about 1,000 times. And so you can see that the reactants are being converted to products, some of those products back to reactants, and you might say the left side's going to empty out. But I can't quite get all the water out. So what happens is it reaches an equilibrium state, where even though I'm moving water back and forth, the amount of water that I'm moving back and forth is equal. So it's reached equilibrium. And so in a reversible reaction, reactants are converted into products, products into reactants, and over time it'll reach an equilibrium state. And what's going on is that reactants and products are moving back and forth at an equal rate. And so we can measure that constant as the concentration of products divided by the concentration of the reactants. And we learned in the last video that before we reach K, we could also calculate Q, which is going to be the same thing before we've actually reached equilibrium. And so what we can do is we can compare our Q and K values, and we can make predictions about what's going to happen in this reaction. And so an example that I'll use throughout this is the Haber process. That's that process by which we can make ammonia. So we're taking nitrogen and hydrogen gas, converting that together, and we're making ammonia. And so it's a reversible reaction. So if we were to look at the concentrations over time in this process, you get a graph that looks like this. And so we have way more reactants at the beginning than we have products. In fact, for products, we have 0 at the beginning. And so eventually they're going to reach a point where they stay the same over time. And so that would be our equilibrium point. And so now I'm going to show you a different graph where we're going to look at, instead of the concentration of reactants and products, the rate of the reaction, the rate forward and the rate backwards, and we would get a graph that looks like that. Now, why do those two things merge? Remember, going back to that demonstration, the amount that I was moving from the left to the right in the forward direction equals the amount that I'm moving back in the reverse direction. And so we would have reached equilibrium at this point. And so if I were to show you how I calculate K and Q values, let's start real simple. Let's say we're just looking at the total number of reactants and products. I could figure this out at equilibrium. How do I calculate that? I simply take the ratio of products to reactants. How many products do I have right here? We'll say that that's 2. What about reactants? That's 4. And so what's my K value going to be? It's going to be 0.5. Now let's move it further back in equilibrium. What's it going to be? Same thing. What's it going to be here? Same thing, it's going to be 0.5. In other words, that K, or our equilibrium constant, remains the same as long as we're at equilibrium. But let's look at what it looked like before that. So let's calculate our Q values, which is before we reach equilibrium. Let's move it right back to here. What is my products at this point? My products at this point is around 0.5. What are my reactants? It's going to be around 5, and so I'm going to have a value of around 0.1. Or if I move it right here, what's my Q value going to be? It's going to be 0 because I have 0 products. And so what happens if we ever have a Q value lower than our K value? That means it's going to move towards the right. In other words, since our Q value is less than K, the reaction is going to move to the right. In other words, we're going to move from reactants to more products. If we're to look at a reaction like this, let me show you our K values again. They're going to be exactly the same because we have the same number of products and the same reactants. Could you calculate the Q value right here? Well, reactants and products are equal, and so our Q value would be 1. What about right here? It's going to be 5. And so in this case, our Q value is actually greater than our K value, so now it's going to move to the left. We're going to move from products to more reactants. And so again, if you're given values of Q and K, you should immediately be able to figure out, do we go to the right or do we go to the left? And sometimes this is confusing, so just put it on a number line. If I put the K and the Q values on a number line, K is where I want to go, Q is where I'm at. Where am I going to go? I have to move to the left. So I have to move from products to reactants. Now let's actually look at the chemicals that are going on in this reaction. Let's look at the gases that are going on in this Haber process. And this would be a typical equilibrium. So in this case, we're starting with a larger amount of hydrogen gas and no ammonia. And over time, it's going to reach an equilibrium state where the concentration of all of these stay the same. Now we could start with different amounts of each of those. It's also going to reach that same kind of equilibrium state over time. So once the concentrations remain constant over time, we've reached equilibrium. And so when I was showing you those first calculations, I was kind of hiding the difficulty in solving these problems from you by making it very, very simple. We just divided the products by the reactants. Now, when you solve an actual K value, you're going to have to figure out what is that equilibrium constant based on the equation or based on the chemicals that are in that reversible equation. And so this is what that general form looks like to calculate K. And so if we have a reaction where these are our two reactants over here, where the small a and the small b represent the moles of that chemical, this is going to be the form that we write it in. And so if we were to start with the products, remember the products were on top, we're going to have the concentration of C, which is going to be this chemical right here, and it's raised to the power of that mole, which is going to be raised to the power of C. This is going to be the concentration of D raised to the power of small d. And so let me show you an example of that. Might be a little bit easier. So let's say this is our equation right here. How could I write the equation for my equilibrium constant? Well, using this as a model, I'm going to put my products on the top and my reactants on the bottom, and so it's going to look like this. And so this is going to be my nitrogen gas right here, so the concentration of that, multiplied times the concentration of water raised to the second power. Why is it raised to the second power? Because our mole value is going to be 2 right out in front. Now let's look on the reactant side. We're going to have our NO raised to the 2 power, concentration of, times the hydrogen raised to the 2 power as well. Now if I were to give you a problem like this, could you solve that for the Haber process? Could you figure out our equilibrium constant? You may want to pause the video and give this a try. But this is the answer right here. It's going to look like that. So this is a little bit different than the last one. Since we only had one product, we're going to only have one thing on the top of our K. And so that's going to be the ammonia raised to the second power. Our hydrogen is raised to the third power, and then our nitrogen is raised to the first power, essentially. And so let me show you how to calculate K. These are the molar values at equilibrium. Could you figure out K? Well, first we start by writing out the reaction. So it's going to be ammonia raised to the second power, nitrogen times hydrogen raised to the third power, and then you're simply going to plug those values in. So we're going to put 0.157, which is our concentration of the ammonia, in the top. We multiply this out, and I'm going to get a value of 0.0602. And so that's going to have 3 significant digits. So that's calculating K. You should be able to do that. Now let's look at an ICE table. An ICE table is going to show you, remember, the initial concentration, that's where the I comes from, the change, and then the equilibrium concentrations at the end. And so if you were given this equation right up here of a reversible reaction, you should be able to calculate the Q value. The Q value is going to be right here. Now, how did I write this out? Again, it's water raised to the second power because we have 2 moles right here times nitrogen. This is going to be real simple because both of these values are going to be 0. So if I were to plug those values in, I get 0 and I get a Q value of equal to 0. So let's say that that's our initial state. Could you calculate our equilibrium state if I give you those molarities at that point? Well, same kind of a thing. K value is going to be equal to this. If I plug in those values here and then multiply it out, I get a value of around 650. 2 significant digits we should have in this one right here. Okay, so once you get your Q and your K, you should know immediately which way this reaction is going to go. Is it going to go towards the right or it's going to go to the left? Well, this is pretty easy. Since our Q value is less than our K value, it's going to move towards the right. We're going to have to convert our reactants into products. We could actually figure out the rest of our table. We could figure out our change values right here. If this is 1 and this is 0.062, we're actually subtracting 0.038 from that. So I could calculate all my values across right here, my change values. And what you'll see is there's an interesting pattern right there. If we look at all these values, they're essentially the same. We're either subtracting the same amount or we're adding the same amount. Why are those the same? It's because the molarities in the front are going to be the same as well. And so what we've really discovered here is stoichiometry. So if we look at this one, we're adding the nitrogen gas. Why is there only a half as much as this? It's because we only have 1 mole of that. And so stoichiometry is really going to guide this second row in an ICE table. So this would be one thing you might have to do. Calculate the Q value, calculate the K value, and then figure out what's in the middle. But this is a common problem as well. Let's say I only give you my initial state. I only give you my Q value and my K value, and then you have to figure out the rest of the table. Well, how would you solve that? First things first, you can see that our Q value is going to be less than our K value. So is it going to move to the right or to the left? It's going to move, we know it's going to move to the right. And so I can actually fill these in with variables. And so what I'm going to do is I'm going to subtract a given amount. We'll call that X. Now, why am I putting a 2x here? If we go back and look at our equation at the top, there's 2 moles of this and only 1 mole of these other 2 gases. And so I know the ratio between these is going to be a 2 to 1 to 1. Why are these negative and this positive? It's because we're subtracting the amount of reactants that we have. Since that equation is moving from the left to the right, we know that this is a negative value right here. Okay, what do I do next? I could just figure this out. So I'm going to put my 1 minus x. How am I doing that? 1 minus x here, and I'm going to figure out my equilibrium point. Again, I don't know what x is, but now since I know what my k value is, I know that is equal to 16, and I only have 1 variable, I should be able to solve for that. So how would you set that up? First, we're going to write the equation for the equilibrium constant. So how do I do that? Here's my concentration of HI raised to the second power because we have 2 moles up here. And now I'm going to just plug those values in. So what's going to go in here? It's simply going to be 2x. So I'm going to put it in like that. And then I'm going to put my concentrations on the bottom. Since those are both the same thing, we could just square it. Now you might freak out at this point because this is a 16 equal to, oh man, this is going to get ugly. I'm going to have to use the quadratic equation. Lots of times it's much simpler than that. You can see that we're squaring the value on the top and we're squaring the value on the bottom. And so what I could do is I could take the square root of both sides. And if I do that, I get this. I can solve for x as 0.66. And now I just put those x values back in my ICE table before. So this would be my negative x values right here, and this is going to be my 2x value. And so just knowing my equilibrium constant, I can figure out the rest of this table, what's going on. So can you read graphs like this to figure out, based on the concentration of reactants and products, if we've reached equilibrium? And if not, which way do we have to go? And finally, can you use data to predict the direction of the reaction, left to right, right to left, or have we reached K? Could you calculate K? And then could you determine the conditions at equilibrium if I give you K? I hope so, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 12. It's on conservation of atoms. Imagine we were to take 3 brand new nails and we were to get their mass very precisely, and then we were to let those nails rust. and we were to take their mass after they'd rusted, which would weigh more? Well, you might think the rusted nails are going to weigh less, but they'll actually weigh more because we're adding the mass of the atoms in the oxygen when we're making this iron oxide. And so this video is about conservation of atoms, which is going to basically be the idea that matter can neither be created nor destroyed. And this is going to be in chemical processes. So we usually use or chemical change, and we usually use an equation to show a chemical reaction. This one right here is hydrogen and oxygen gas combining to form water. And so in any equation like this, the little subscripts are going to stand for the number of atoms. And so this would be hydrogen gas, which is going to be a molecule of hydrogen. It's 2 atoms combined. And then the 2 in the front is going to be the number of molecules. And so this reaction, for every 2 molecules of hydrogen and 1 molecule of oxygen, we're going to get 2 molecules of water out of it. What's cool about that is the number of molecules is also the number of moles, because remember, it's not just 1, it's sextillions number of molecules that are combining in a chemical reaction. And so what's cool is now that we know this conservation of atoms, we can use the masses in chemical reactions to figure out what's called the analyte. That's going to be an unknown in a reaction. And we can do that in 2 ways. First way is through gravimetric analysis, and that's just going to be using the mass of a product, something that we get out of the reaction. And then a real familiar one in chemistry is the titration. In titration, what we're doing is we're adding a chemical until we reach an equivalence point. A real common one would be a acid-base titration. What we're looking for is a change in color. And so in a chemical reaction like this, which this is a pretty important one, this is the chemical reaction overall for photosynthesis, what we're doing is combining water, carbon dioxide, and we're making glucose and oxygen. And so if we look at that graphically, this is what water looks like. It's going to have 2 hydrogen atoms and 1 oxygen atom. And so this little 2 here stands for the 2 hydrogen. And the oxygen, since there's only 1, we don't write 1 subscript underneath that. If we look at carbon dioxide, for example, this is carbon dioxide. It's 1 carbon, and then we're going to have 2 of the oxygen atoms connected to that. What does the 6 stand for? Remember, the 6 stands for the total number of molecules. And so this reaction, one of the reactants are going to be 6 molecules of water. And so the 6 stands for the total number of molecules. And so let's kind of throw this whole reaction together. So now we've got 6 water and 6 carbon dioxide. We're going to have a reaction, and let's watch what happens. So those are going to break bonds, they're going to reform bonds, and now we're going to have oxygen and glucose. And we're going to have 6 of these oxygen molecules, and we're going to have 1 of these glucose molecules. And so let's go back again and watch what happens to the number of atoms. So as they break and reform these bonds, they don't go away. In other words, we're conserving the total number of atoms. And so that's that conservation of mass. The atoms aren't going anywhere, they're just breaking bonds and then reforming again. And since we know that, we can solve for unknowns. And so if you have the mass, you pretty much have everything in chemistry. Because if you have the mass and a periodic table, what you can do is you can look up the atomic weight of those atoms, and that's going to tell us the total number in 1 mole. And so really, if you know what a mole is, if you don't know that, please watch the video. And if you have a periodic table handy, you can really figure out from mass the number of atoms, the number of molecules, and even the empirical formula, which is that simplest of formulas. And so mass is really what we're looking for in any kind of a reaction. And so the first type is called gravimetric analysis. In gravimetric analysis, what we're doing is we're taking 2 reactants and we're combining those. And so let's throw in the blue. This is going to be our analyte. This is the unknown. We don't know the mass of the solute that's dissolved in this solution. And then let's say we have another solution. We're going to combine those 2 together. There's going to be a reaction, and then we end up with a precipitate, which is going to be a solid, and then another solution. And this is a real common kind of a reaction you're going to see in chemistry. So how do we work backwards? Once we know the precipitate mass, once we know the mass of that solid product, what we can do is we can go from its mass to its moles. We can go from its moles to the moles of the analyte, and then from the moles of the analyte, we can go to the mass of the analyte. So we can kind of work backwards. Let's go through a sample problem of gravimetric analysis. Let's say we have this. We've got silver nitrate. This means that it's in solution. We're going to combine that with calcium chloride, which is also in solution. And then what we're going to get is a solid. You can see a solid here of silver chloride, and then we're going to have another solution, which is going to be calcium nitrate. So let's say that's our reaction. This is what it looks like right here. This is silver nitrate after this reaction has occurred. And so this is going to be our solid product that we've created. And let's say we want to work backwards and find the analyte. So let's just choose our analyte is going to be this calcium chloride up here. So how do we work backwards to figure out how much of that calcium chloride we had to start? Well, let's start with what we do know. We know that the mass of the silver chloride is going to be 5.71 grams. So we've got the mass right here. Now let's work backwards across this kind of flow chart and figure out the mass of that analyte. Well, the first thing we have to do is we have to go to moles of silver chloride. And so we're going to use this conversion here. How am I getting this 143.32? Well, we're using the atomic weight of both the silver and the chlorine, and that's going to add up to 143.32. So I can cross off my units, and I've now converted it to moles of silver chloride. What's next? Well, now we want to go from moles to moles. So we're going to make this jump right here, the precipitate moles to the analyte moles. Where am I getting these values? Well, I'm going to put the mole of silver chloride right here. Why did I put a 2 here and a 1 here? Well, if you look back in your equation, there's 2 moles of that silver chloride, and we're going to make 1 mole of that calcium chloride. So that's going to be where my mole conversion is right there. Now I've got it to moles of calcium chloride. I'm almost on the home stretch, so I can put the moles on the bottom, and then I'm going to put my grams on the top. Where am I getting that? Again, I'm getting that from the atomic weight of both calcium and chlorine. That's going to be on the periodic table. So now I can just cross off my moles calcium chloride, and I've figured out my analyte. I figured out that originally I had 2.21 grams of calcium chloride. Now you try. Let's say I asked you to figure out the amount of silver nitrate to begin with. Could you do that? Well, try to figure that out and put your answer in the comments down below. Let's go to titration then. How does the titration work? I did this all through chemistry, but I really didn't know what I was doing a lot of the time. And so let's say we've got this reaction up here. This is going to be sodium hydroxide, which is a base. It's going to have a pH that's very high. And then let's say we're combining that with oxalic acid. It's going to make sodium oxalate, and then it's going to make a little bit of water when we're done. So let's say this is our reaction right here. Here are the 2 reactants, and here are going to be the 2 products over here. Let's say we start with a 1 molar sodium hydroxide solution. What does 1 molar mean? That means we have 1 mole of sodium hydroxide for every liter of solution. And let's say our analyte is going to be this oxalic acid down here. Let's say we want to do a titration, and then we want to work backwards to figure out how much of this that we have. Well, when you're doing a titration, you have to have some kind of an indicator. And so in an acid-base titration, what we'll use is phenolphthalein. Phenolphthalein is simply a chemical that if the pH is low, in other words, when it's acidic, it's going to be totally clear. But as the pH goes up above around 8, it's going to turn to a pink color. And so it really tells us it's an indicator of when we're going to get a big change in pH. And so let's just let the titration go the first time. So I'm going to let that sodium hydroxide run out. And boom, all of a sudden it turns to a pink color. So let's watch that again. So what's going on? Sodium hydroxide running out, and all of a sudden it turns to that pink color. So why is it doing that? Well, in the beginning, as we add that sodium hydroxide, it's reacting with the oxalic acid, and so it's being consumed. And so the pH down here in the bottom is staying lower than 8. It's staying fairly acidic. It's staying at least in the 7 kind of a range down here. And so what happens when it turns pink? Eventually what happens is as we add that sodium hydroxide, there's too much of it. In other words, we have too much sodium hydroxide. It can't combine with this oxalic acid anymore, and that's because there isn't any more. And so what happened is all of a sudden the pH is going to go really, really high. And why is that? It's just because we're just pouring straight sodium hydroxide in. If we were to look at that on a graph, this is what it looks like. As we add the sodium hydroxide, the pH is going to start to climb gradually, and all of a sudden, bam, you hit an equivalence point. What's going on with that equivalence point here? It's when we've run out, it's when we've run out of that oxalic acid, and now we're just pouring straight sodium hydroxide in there. And so what is that point? Well, let's look, 10, 20, 30. It looks like when we're adding about 30 milliliters of sodium hydroxide, that's when we hit that point. And if you're doing this in the chemistry lab, you'd go really slow right here, slower than my animation, so you can find that exact point. But let's say that exact point is exactly 30.0 milliliters of solution. So let's say I had to add 30 milliliters of that sodium hydroxide solution to hit that exact equivalence point. How could we work backwards to find that analyte, which is going to be this oxalic acid up here? Well, we just kind of work backwards. So what we're going to do is first we have to convert that to liters. And so this is going to be a conversion to liters because molarity, remember, is going to be the moles of anything divided by the liters of the solution. Next, we'll get that molar. This is going to be our molar value right here. Remember, I told you it's a 1 molar sodium hydroxide solution. That's 1 mole of sodium hydroxide for every 1 liter of solution. So now I've already got to moles of sodium hydroxide. So I want to go from here to here. How am I going to do that? We're going to use a mole conversion. So I'm going to put the moles of sodium hydroxide on the bottom and the moles of oxalic acid on the top. I've now got moles of oxalic acid. Now all I have to do, I got to go down to the next line, is I have to get that to the grams of that oxalic acid. Where are we getting those values? Well, we have to add up the hydrogen, the carbon, and the oxygen. We're going to use their atomic weights to do that. And so what do we end up with when we're done? This is the number of grams of oxalic acid that we had to begin with. And so that's how you would do a simple titration to work backwards to find the analyte. How much of that original product or reactant did we have? Now you try. Let's say I change it a little bit. Let's say how much of the analyte, let's say this oxalic acid is present if instead of adding 30 mils of 1 molar sodium hydroxide, let's say we had to add 25 milliliters of a 0.5 molar sodium hydroxide solution. Could you figure that out? If you do, put your answer in the comments down below and see how you're doing. And so hopefully in this, you should have learned the following: to apply the conservation of atoms in various processes. Remember, looking back at that graphically, what an equation looks like, we can figure out what these atoms are and how they're being conserved. Did you figure out how to use gravimetric analysis to determine the concentration of a solution? Remember, in gravimetric analysis, we're using that solid that we produce at the end to work backwards to find that liquid. And then finally, where you're using a titration, to determine the concentration. And in that, remember, we're looking at the amount that we have to add of a certain solution. In this case, it was sodium hydroxide. And then we can work backwards to figure out the analyte. In this case, it was oxalic acid. And I hope that was helpful. Hi, it's Paul Anderson and welcome to Chemistry Essentials Video 5. This is on electron configurations. When I took chemistry, I remembered having to do electron configurations. I remember this chart and these different orbitals and this diagram, and I learned how to do it, but I never really knew what I was doing. And so in this video, I'm going to show you how to do electron configurations. We'll do that at the end, but I also really want to tell you what's going on behind the scenes. And so all electron configuration is simply the distribution of electrons, so where the electrons are found in atoms or in ions. And so a good way to figure that out is to look at their ionization energy, which is going to be the amount of energy it takes to pull an electron away. And so we can quantify that by using Coulomb's law. And so what we can do is we can work our way out from the electrons on the inside to those on the outside. And when we're done, we have a pretty good picture of where all those electrons are. Because in most atoms, they're going to be multi-electron. They have many electrons. And what we'll find is they're going to be organized into shells, subshells, and then orbitals. And all of those are going to have similar ionization energy. And there's a chart on ionization energy that's the most important one. Now, if we look at these orbitals and subshells, what we'll find is that the ones on the inside are going to be, or the inner electrons are going to be called core electrons, and the ones on the outside are going to be called valence electrons. And what's interesting is that those on the inside, once they're filled, will actually shield the valence electrons from the power of the nucleus itself. And so let's look at the first and simplest of electrons. We've got hydrogen right here, 1 proton, 1 electron. And so Coulomb's law allows us to quantify the force between the two. And so it basically comes down to the charges and then the distance between the charges. And so if we were to look at ionization energy, it's the amount of energy it takes to pull that electron away. How do we figure it out? You're simply going to multiply the two charges. So let's say the proton has a positive charge, let's call that +1, and the electron has a negative charge, let's call that -1. And the only other thing we really need is the radius, the distance between the two. And so let me ask you a quick question. Which do you think would have a higher ionization energy? Hydrogen, it's got 1 proton, 1 electron, or helium? It's going to have 2 of each and 2 neutrons as well. So make a guess, and let me show you what helium looks like. Helium, you can see it just got a little bit smaller, and the reason why is since it has 2 protons in the middle, there's going to be more pull, or there's going to be a larger energy of ionization in helium, and that's because there are a greater amount of positive charge on the inside. So we would say helium has a higher ionization energy. What about the next one? What if we were to compare helium then with lithium? What do you think happens to the ionization energy there? Well, you might immediately think it's going to be bigger, but remember the electrons are organized with only 2 electrons in that first shell, and then when I learned it, it was going to be 8 in that next subshell. And so if we look at that lithium, what we'll find is we've increased the number of protons, so there's more of a charge here. But that electron is going to be in the next shell. And so since it's in the next shell, it's shielded from the power of that protons, the protons in the nucleus itself. And so it's going to have a really small ionization energy here, just because of the shielding effect and the fact that we have another shell. And so what do you think about beryllium? Well, hold on to that and we'll take a look at the pattern. And so this is the chart that really allows you to understand what's going on with the electrons. And so let me lay it out for you. We have atomic number across the bottom. So this would be hydrogen at 1, helium at 2, all the way out. And then we're going to have ionization energy, which is the amount of energy it takes to pull that electron away. And what you can see are patterns immediately. And so these big spikes that you can see are ending with these noble gases. Those are going to be those different shells. You can see that they're broken down into subshells, and then we're going to get to orbitals in just a second. And so let's kind of lay this out for just a second. So a shell is going to be, let's look at the first one. So here we've got hydrogen. So hydrogen is going to be right here. And we said it had a high ionization energy, and that's because it's really close to that nucleus. So it's close to the protons inside there. And so what we can do is we can fill out this box. So this is going to be the 1s. We would call that 1 is just going to have a shell, and this is going to be the 1s shell. But the reason we have boxes here is that it was later discovered that electrons will fill what are called orbitals. And those orbitals can only have 2 electrons in each one. So let's look at hydrogen. Hydrogen, we said, has an ionization energy, we'll say, of on this chart around 12. If we go to helium, it's going to have a higher ionization energy. Why is that? It's going to be because, remember, we have those protons on the inside that are holding it in. But let's watch what happens when we go to lithium. What's happened is we've gone into this whole next orbital. And so there's this shielding effect of this filled orbital here. And so we have much less ionization energy there. Let's watch what happens with beryllium. Well, that kind of makes sense. We're increasing the protons, and so that should go up. But then what happens with the next one? Well, when we go to boron, what's happening is it's actually going into a new orbital. And so it's going into an orbital of the second subshell. And so if we didn't have these orbitals, what would happen is it would just be a consistent all the way up to neon, but you can see we kind of have this jag as we move up. If we go to the next one, that makes sense. Carbon's going to have more ionization energy. We're adding more protons. Nitrogen, same way. But now let's look at this. Why does the ionization energy go here after we leave nitrogen? Well, the reason why is that these electrons are added, and they're added one at a time in each orbital, but they'll have a specific spin. And so you can only have 2 electrons each way. But what they'll do is they'll fill them kind of like seats in a bus. And so they're going to all get on 1 seat per bus, but then when we get more electrons, they're going to have to double up. And so what happens is when we go to oxygen, what we're doing is we're making that electron sit in that orbital. It'd rather not be there. There's repulsion between those electrons, and so it lowers the ionization energy. We go to fluorine, we go to neon. Once we have that shield effect, we jump all the way down to sodium again. And so once I really understood what was going on in this chart, then all of these subshells made sense. And so where do they come from? It's quantum mechanics and it's quantum numbers that determine that. But if we're looking at periodicity, in other words, if we're looking at the periodic table, these things would be subshells. And so we're going to have a shell, which is going to be the 1, 2, 3, 4, 5. But we're also going to have subshells, which are smaller. And then within each of those, we're going to have orbitals, if that makes sense, if we go in size. And so let's get to the electron configuration. And so what we have here are the sp, the d, and the f. They come from quantum mechanics. What's interesting about the s is it has only 1 orbital in it. The p has 3 orbitals, so you could have 6 electrons. D has 5 orbitals, so you could have 10 electrons, and F is going to have 7 orbitals, so you could have 14 electrons. So if you want to write this out, you could just write on a chart, start with the 1s and just write all the way down to 7. Then you want to write right to the right of that 1s, or 2s, you're going to write the 2, and then you're just going to write p's all the way down. And then you go down to the 3, we'll write a 3 over here, and then you're going to write d's all the way down. You could go all the way to 7, but we'll never really need that. Then you go to the 4, you write a 4 over here, and then you write f's all the way down. And so once we have that, we can put diagonal lines in like this, and then we can do the electron configuration for anything. So you wouldn't even need a periodic table. You could just do this, and you can figure out electron configurations. Let's start with hydrogen. What's going to be the electron configuration of hydrogen? You're simply going to start at the top, and so it's the 1s shell or orbital or subshell. And so what we would write it as is 1s1, and that 1 represents the 1 electron that we have inside that orbital. If we go to boron then, how are we going to write boron? Well, you're going to start here, go here, go here. Boron's going to be a 1s2 because we can only put 2 electrons in there. We then go to the 2s, it's going to be 2s2 because we can only put 2 electrons in that. And then we're going to go to the 2p, and we only have 1 electron left, so we're going to put it there. So that'd be boron. What about neon? And again, you could pause the video and always try it out. Neon's going to be this, so it's 1s2, 2s2, 2p, remember, can have 6, and so we're going to write 6 there. Let's go to the next one. What about sodium, which is number 11? We've got 11 electrons. Well, we could write it out like this, 1s2, 2s2, 2p6, and then the next one goes in the 3s1, but you can see how long these electron configurations are going to get. And so we can abbreviate that. And so we could just say it's neon, put that in brackets with the 3s1. So that allows us, we just write the noble gas in there, and then we can add what's after the noble gas. And so here's a couple for you to try. Could you try chlorine, which has 17 electrons, or silver, which has 47? I'll put the answers in the video descriptions down below, but give it a try. So what did we learn? We learned that electron configuration is the distribution of what? Again, could you pause the video and figure out what's in the blanks? Distribution of electrons. In atoms or ions, they each have different ionization energy. We could quantify that through Coulomb's law. Remember, most atoms are going to have multi-electrons, and those are organized in subshells. And then this property is important as well. Those inner or core electrons are going to shield the valence or outside electrons from the power of the nucleus. And so what you should have learned is how the energies of electrons vary within shells of atoms. And so I could point you to this ionization energy chart, and as we walk through that, that should help. And then the other thing you should have learned is that we could use Coulomb's law to analyze measured energies of electrons. And that works great, but it doesn't explain orbitals, and so we have to we have to modify our theory a little bit, and I hope that was helpful. Hi, it's Mr. Anderson. This is Chemistry Essentials video 14. It's on gases. When you see a hot air balloon flying, it looks pretty stationary, but if you were to look at the molecules inside it, if we were to look at the heat inside it, we'd see there's going to be way more hot air at the top than at the bottom. It's less dense, and that's why the thing is going to float. So when we're looking at gases, basically a real gas is going to be made up of all these independent particles that are all just shooting around, moving around really, really quickly. They're not connected together at all. And so in science, what we can do is we can model that using what's called an ideal gas. And lots of times we'll use the ideal gas law. And this one, PV equals nRT, is one that you should learn right away and learn how to apply it over and over and over again. It's basically built on two things: the kinetic molecular theory, this idea that molecules are bouncing around and they have a huge amount of energy as we increase the temperature, and then the Maxwell-Boltzmann distribution, which means that even though they might collide every once in a while, the energy that they have is going to remain the same and their state is going to remain the same. We can use the ideal gas law to figure out absolute zero, but there are going to be some deviations. In other words, times where this model just doesn't work, and we have to start looking at real gases. And this usually occurs as we get around condensation, that point at which that gas turns back into a liquid again. And so this is going to be a real gas. Air, what's between me and the camera right now, is going to be a real gas. And an ideal gas is built on these two theories. First one is kinetic molecular theory. It's that all of the molecules are bouncing around, moving off of each other, and as we increase temperature, we're going to increase the molecular speed of those molecules. And so that's a gas. Remember, they're not connected together at all. They're just moving around randomly. And then we have the Maxwell-Boltzmann distribution. That means that even though they might bounce into each other, they're not interacting with each other. They're all going to be independent. And so this graph, what we're looking at are a bunch of noble gases, and we're looking at their speed and the probability of having found molecules at that specific speed. And what we'll find is that real light noble gases like helium are going to have a higher speed than those, for example, like argon. We're going to have a lower speed, but they're all independent of one another. And so when we're looking at an ideal gas, we basically have these 5 properties: volume, temperature, pressure, N, which is the number of moles, and then some kind of a gas constant. So you're going to have to look at your units to figure out what gas constant to use. But if we use this model, which we use it 3 times, V is going to be the volume. So let's say these are a bunch of gas molecules. Volume is going to be the size of the container that they're in. T is going to be the temperature, how warm or cold it is, and that, remember, is tied to the molecular motion. Pressure is going to be how much it's pushing out, and if you push in on a balloon, you can start to feel that pressure pushing out on you. And then N is going to be the number of moles, how much stuff is going to be found inside it. And so if we rearrange this, PV equals nRT. That's the relationship. Now you could learn all the different gas laws, but it's better to just learn the ideal gas law and then apply it in different situations. And so we're going to use this simulation at PHET, and we're going to look at Boyle's law. And so that's the relationship between pressure and volume. And so we're going to keep all those other constant, N, R, and T are all going to remain constant. And what we're going to look at is how are volume and pressure related. So I'm going to keep the temperature constant. And if we look at the pressure, it's around 0.69 atmospheres. Now let me decrease the volume. So I'm making the volume get smaller. And so what's going to happen to the pressure? Well, we have to wait for a little bit. We have to wait for that temperature to go back down to 300 Kelvin again. But once it gets to Kelvin, now look, it was 0.69 atmospheres before, and now it's 1.73. And so as we decrease the volume, pressure went up. Now let's increase the volume. So we're making the volume go up, and then let's look at what's going to happen to the pressure. And so we got to wait for that temperature to come back to 300 Kelvin again. And so now we're going to see that the pressure has decreased. So by increasing the volume, we decrease the pressure. And so there's going to be an inverse relationship between pressure and volume. And you could actually apply this in a problem. Let's say we had a balloon at 1.3 atmospheres. That's going to be the pressure. It has a volume of 3.2 liters. What will the volume be if the pressure is decreased to 0.62 atmospheres and the temperature remains the same? Well, we just have a before and after. So we have our pressure volume before, initial, and after. So we'd put in our values before, our after, and then we're going to solve for this final volume. And so we can make sure our units are correct. And so what's going to happen to the volume? The volume is going to increase as the pressure decreases as long as we keep the temperature the same. And a weather balloon, as you send a weather balloon up, the weather balloon is going to get bigger and bigger and bigger. There may be changes in temperature, but it's related to that relationship. Now let's look at what's called Charles' law. We're just going to look at volume and temperature and what happens to the volume as the temperature changes. Let's use this simulation again. We're going to try to keep the pressure constant and the same number of moles inside there as well. And so now we're going to increase temperature. So we're adding heat, and watch what happens to the volume. As we increase the temperature, the volume got bigger as long as we kept the pressure the same. Why is that? As we're increasing temperature, there's more kinetic movement. Now let's lower the temperature. As we decrease the temperature, those molecules aren't moving as quickly, and what happens? Not pushing out as much, and so the volume's going to go down. So if we increase temperature, volume goes up. If we decrease temperature, volume is going to go down. And so there is a direct relationship between the two. And so hopefully you're learning how to apply ideal gas law. If they're both on the same side, we had an inverse relationship, but now since they're on opposite sides of the equal sign, it's going to be a direct relationship. What's an application of this? Well, you could find absolute zero in a basic chemistry class. And so what we could do is take a balloon and we could measure the volume of the balloon when the gas is around freezing. And so let's say we do that by measuring the circumference around the balloon and then using a little geometry to figure out its volume. If we increase the temperature, so let's say we bring it inside and we really increase the temperature, the volume is going to increase. And if we really lower the temperature, put it in a freezer, then we're going to decrease the temperature. And what you'll find is a linear relationship. And so you could extrapolate that line and we could get to negative 273, which is going to be absolute zero. That's when there's no molecular motion and everything's kind of come to a stop. Now let's look at Avogadro's law. Now we're looking at volume and N. N, remember, is going to be the number of moles of the gas that we put in. So let's look at this simulation right here. Well, there's no temperature and no pressure inside the container, and that's because there's no gas. And so let me squirt a little bit of gas inside there. As we increase that, now those molecules are going to start bouncing around, and so we have a specific volume. What do you think is going to happen as I increase the number of molecules inside there, the number of moles inside there? Well, we're going to try to keep the pressure constant, try to keep the temperature constant, and what's going to happen is, look, the more molecules we put in there, now we're increasing that. we're really increasing the volume. And so we've got a direct relationship. More moles, more volume. And so this is for an ideal gas. Remember, PV equals nRT only works if we have an ideal gas. What is an ideal gas? It's a gas where these things are randomly moving around, and there also is no attraction between those. Those molecules aren't pulling on each other. If they start to pull on each other, then this is going to fall apart. And also an ideal gas only works when we have an infinite number of an infinite volume, which we're not always going to have. But let's say we do have an ideal gas. If I just solve for n, this should always be equal to 1. In other words, PV over RT should always be equal to 1 for any kind of a gas. And so let me just plot that for a specific gas. Let's say we're looking at nitrogen right here. Its ideal gas at different pressures should stay exactly at 1.0. But let me throw up some data. This is what nitrogen looks like at 1,000 Kelvin. This is what it looks like at 500 Kelvin. This is what it looks like at 200 Kelvin. And so these are real gases, ones that have been measured. And so what are we finding is that they don't fit the ideal gas law. And why is that? Well, as we slow everything down, as we make it cooler, we start to get attraction between those molecules. And also, we are going to have a finite volume. In other words, it's in a container when we're measuring it. And so what we have to do is we have to start to look at real gas interactions as we get towards condensation. And what's condensation? Remember, that's point at which the gas becomes a liquid. And so this would be water that was in the air that's becoming liquid water on this cool bottle right here. And as we get closer and closer to condensation, then we have to throw out some of those ideal gas laws and use real gas interactions. And so did you learn the following? To use KMT, that's kinetic molecular theory and force concepts, to make macroscopic predictions of what's going on. Remember, those are the two things that guide ideal gas law. KMT, things are moving around, and then this Maxwell-Boltzmann distribution. They interact with each other, but they're not going to influence each other, even though they might bounce into each other. And the idea that faster molecules are generally going to be lighter in a gas. Also, could you apply ideal gas law, PV equals nRT? We did that in a number of different simulations. And then finally, could you use this to solve some problems? And we did this for a basic pressure volume kind of problem. And so those are gases, they're everywhere, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 66. It's on Le Chatelier's principle, also referred to as equilibrium law, and it's a really elegant principle that you apply to reversible reactions. And it basically says if there's ever a disturbance to equilibrium, the reaction will move to counteract that disturbance. And so let's say, for example, I'm at an equilibrium state between reactants and products, and I all of a sudden get an influx of reactants, way more reactants. It's going to throw my equilibrium out. And so what can I do? Well, since this is a reversible reaction, I can move the reaction from the left to the right according to Le Chatelier's principle. And as I do that, I increase the amount of products and I bring it back into balance. That's essentially Le Chatelier's principle. And so according to that, in any reversible reaction where we have reactants and products and it's established in equilibrium, if we ever have a disturbance, and that disturbance could be adding or removing chemicals, it could be a decrease in volume, an increase in pressure, it could be an increase in temperature, a decrease in temperature, or even dilution, what's going to happen is a new equilibrium is going to be reestablished again. And so let me give you an example of that, a graphical example. If we're looking at the Haber process where we're taking nitrogen and hydrogen gas and converting it into ammonia, this could be our initial equilibrium, where we have given amounts of concentration of each of these. But let's say at this point right here, there's an influx of hydrogen. So we're increasing the amount of hydrogen. So that means we're increasing the reactants on the left side of the reaction. According to Le Chatelier's principle, the reaction simply moves to counteract that additional reactants. And so which way is it going to move? It's going to move to the right. And so what's going to happen to the amount of hydrogen? It's going to decrease. What's going to happen to the amount of ammonia? It's going to increase. What's going to happen to the amount of nitrogen? It's going to decrease because it's a reactant as well. And so a new equilibrium is going to be established. And so if we look at this at the molecular level, so this is all of our gases. Again, they're all mixed in together, but we have varying amounts of that. Let's say we get an increase in the amount of hydrogen gas. How can we get rid of that hydrogen gas? We can simply combine it with nitrogen, make more ammonia, and then we can reestablish that new equilibrium again. This also applies to pressure caused by changes in volume as well. And so let's say we're looking at this reversible reaction where we have dinitrogen tetraoxide, which is a clear gas, which can move reversibly to nitrogen dioxide, which is going to be a reddish brown gas. And let's say we put a mixture of these gases at equilibrium inside this chamber right here, and I were to simply decrease the volume. So if I decrease the volume, it's going to be more concentrated, and so we're going to have a darker color. But if you were to watch it for a given amount of time, it'll turn back to that color. And so it's important that we understand really what's going on, and you can't figure it out looking at it this way. Let's look at it at the molecular level. So originally we had a mixture of those gases that look like that. And why was it reddish, brownish? Because we had enough of those nitrogen dioxides, which are going to be these ones right here, which give it that kind of a color. So what happens when I squeeze it? What happens when I decrease the volume? I'm increasing the pressure of those gases. And so according to Le Chatelier's principle, what's it going to do? It's going to move to counteract that increased pressure. Well, how can it do that? Well, if you look here at the reaction, we've got 2 moles of the nitrogen dioxide on the right side, but only 1 mole on the left side. And so if we could move this reaction from the right to the left, we can decrease the number of moles that we have, and we can alleviate some of that pressure. And that's really what's going on. And it's going to take a little bit of time for that to occur, but that reaction is switching from the right back to the left. This also applies to temperature and energy as well. So let's look at that same reaction. Again, we're taking this colorless dinitrogen tetraoxide and moving it into nitrogen dioxide, which is reddish brown. As we move from the left to the right side, that's going to be an endothermic reaction. What does that mean? It actually takes in heat from the surroundings as we move from the left to the right side. And so I'm simply going to add that heat down on the left side, and we can now treat it as a reactant. And so what happens if we increase the temperature? If we increase the temperature, if we increase that heat, what it's really doing is it's essentially adding more reactants. It's adding more things on the left side. And remember when we added more hydrogen in that Haber process, what happened? It switched to the right side. So we had a shift towards the right side. What's that going to do? It's going to push our reaction to the right. We're going to get a darker color. And so this is the same concentration of gas, but here and here they've heated it up. And so we're seeing that reaction move to the right side to counteract that increased temperatures. Likewise, what happens if we decrease the temperature? It's like decreasing the reactants on the left side, and now it's going to move towards the left side, and we're going to have more of that colorless gas. And so Le Chatelier's principle is wonderful, and we can apply it, for example, to increase yield. And so let's say we're looking at this Haber process where we have nitrogen gas and hydrogen gas making ammonia. This is an exothermic reaction, and so that means we could put heat on the right side. And so let's say I want to increase the amount of ammonia. Well, let's look at the concentration. If I want to increase the amount of ammonia, what would I do? I would simply increase the reactants. If I can increase the concentration of my reactants, it's going to push the reaction to the right side, and I'm going to have more of that ammonia. Let's look at the next one. How could I increase my percent yield by changing the volume and thereby the pressure? Well, if you look on the left side, we have if we look on the left side, we have 4 moles. On the right side, we have 2 moles. And so if I could squeeze this reaction, it's going to convert towards lower moles. It's going to convert towards that ammonia. I'm going to have a greater percent yield as well. Now let's look at temperature. I mean, the temptation is to say just heat it up, and that's going to give us more of the yield. But since this is an exothermic reaction, that means we have more heat on the right side. And so if I increase the temperature, it's actually going to push it back to the left side. And so I would want to decrease this reaction's temperature in order to get more of that percent yield. In actuality, there's a nice balance because we want it to go quickly, and so temperature and pressure are actually balanced out. And so did you learn which way the reaction is going to shift based on disturbances, be it either concentration or pressure or temperature? And then finally, could you, given a reaction, figure out ways by changing temperature, volume, and concentration to increase percent yield? I hope so, and I hope this was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 20. It's on ionic bonding. Remember, ionic bonding differs from covalent bonding. In covalent bonding, they're sharing the electrons. In ionic bonding, what you're doing is you're transferring the electron from one atom to another. And so the quintessential example is sodium chloride. So sodium, here's its electron configuration, has one valence electron, and chlorine is going to have 7. And so if we look at their electron configuration, if we can actually transfer that electron from sodium to chlorine, then we get to this electron configuration that is a noble gas. It's going to be very stable. And so what we get is a sodium ion and a chlorine ion. And so the sodium ion, since it's lost an electron, we call that a cation ion. It has a positive charge, and the chlorine is going to be a negative charge. And the way I remember this, it's a little bit silly, but if you take that sodium ion, a cation ion, if you think of a cat has paws, and that means it's positive. Sorry about that, that's a little bit lame, but it's a good way to remember it. And so ionic bond is going to be between ions. It's a connection between ions. And so we're going to have a cation and an anion. Cations are going to be positive. That means they've lost an electron, and anions are going to be negative. And so what they form is something called an ionic solid. Now, how well that solid is held together is based on Coulomb's law. Remember, if we have a larger charge, there's going to be a larger attraction between those two molecules, or atoms in this case. And then the greater the distance is, the less the force is. And so if we have a really small ion and a large charge, we're going to have a stronger interaction. So it's important to kind of remember those two things. And so here's sodium chloride then. Sodium chloride is going to be all of our sodium ions. Those are going to be purple, which have a positive charge. And they're going to organize themselves in this real crystalline, nice solid. It's really high melting point, high boiling point. A super easy way to break it apart is with water, but it's going to be an incredibly stable kind of a molecule. And so what determines the stability, how well it's held together, is simply Coulomb's law. Coulomb's law, remember, if we have the same charge, there's going to be repulsion. And if we have opposite charges, there's going to be attraction. But if we look at the formula, the bigger those charges are, the greater that attraction is. And the bigger the distance, since this is the radius right here, the less that attraction is going to be. So let's throw sodium chloride up here. Sodium, which is going to be the cation, chlorine, which is going to be the anion. And then there's something called lattice energy, which just is a way to measure how well this lattice is held together. And so if we look at this right here, make a prediction. What do you think is going to happen when we move this from sodium chloride to sodium fluoride? Well, in each of these diagrams here, sodium is going to be this little purple sphere, and I try to keep that about the same size. But let's look at fluorine now. As we move to fluorine, can you see that that fluorine ion is going to be smaller? And since it's smaller, our lattice energy is going to increase because those ions are closer together. So let's go back to sodium chloride. What do you think is going to happen when we make sodium bromide? Well, the purple sodium cation is going to stay the same, but now since we've increased the size of that atom, we've decreased this lattice energy. And same thing as we go to sodium iodide. And so as it gets bigger, that distance between the two, just due to Coulomb's law, we're going to see a decrease in that energy between them. But what's the other thing that can affect it is the charge. And so if we run sodium chloride versus barium oxide, which is going to have a totally different charge, you can see that there's a great difference between those lattice energies. In other words, as we increase the charges, we increase that ionic bond between the two atoms. And so did you learn this to connect the microscopic structure to the macroscopic properties? It's simple. It's Coulomb's law. The greater the charge is and the smaller the distance between the ions, the greater the bond strength, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 10. It's on light and matter. Matter is what we're made of, but I've got some matter on the screen and you can't see it because there's no light. Once I add light, we start to see matter. And so we can see solid, liquid, gas, and plasma. And so until we have light, we really can't probe matter and figure out what it's made up of. And so in this video, I'm going to talk about light and matter. Remember, light travels in these little packets called photons, and we can quantify its light using Planck's equation, where energy is equal to h nu, and h is going to be Planck's constant, and nu is going to be the frequency of the light. But we can use these little photons to probe matter and figure out what it is. Because if you have a molecule and it absorbs a photon, it absorbs a certain amount of that energy. And when it releases a photon, it releases some of that energy as well. And so we can use different types of photons to figure out different things about molecules. And so infrared light is incredibly important at looking at the vibrations within atoms and molecules and figuring out what bonds they have. If we're using ultraviolet or visible light, we can look at the electronic structure. In other words, where the electrons are found, the outer electrons, and what they're doing. And then finally, we can look at solutions using light. And as we shine light through a solution, some of that light is going to be absorbed. And so we can figure out, according to Beer-Lambert law, what is the concentration of those absorbing molecules. And so light, remember, is a wave and a particle. And so if we're looking at it as a wave, we have what's called the electromagnetic spectrum, all the way from radio waves to gamma rays. Radio waves are going to have a really long wavelength and a low frequency. That's how many waves we have per second. Gamma rays are going to have really high frequency, small wavelength. And we're just seeing a small portion of that. When you look at me, you're only seeing visible light. And so light is a wave. Light is also, however, a particle. And what that means is it's quantized, or it comes in these small little quantities. And so you can think of it like this. And let me play some music in the background. This is Rachmaninoff for violin and piano. Vocalize. And so a violin can play any note. You just move your finger up just in incremental amounts, and you can get any note. But a piano is going to be quantized. You're going to have specific quantities. You can only hit a C or a D or an E. And so really, which is light? Light is like a piano. It comes in these small little quantities of photons. And so we can measure that energy using Planck's equation, where h times nu is going to be Planck's constant times the frequency of the light. And so which of these wavelengths are going to have the highest amount of energy? Ones with the highest frequency, and those are going to be the gamma rays right up here. Which ones are going to have really low energy? Those are going to be the radio waves down at the bottom. And so what we can do is we can measure photons and how they're picked up by atoms, and it tells us a lot about what the electrons are doing. And so a spectroscope allows us to see this whole electromagnetic spectrum. One of the first scientists to do this was Newton. If you wanted to build one of your own, all you would need is a prism and then a small slit. So we run light through it, and it's going to split that light into the different colors that we could see. And so this would be a compact fluorescent, and you can see the different colors of light that are coming from it. In a typical chemistry class, you'll just use a cheap spectroscope like this. It's going to have a slit on one side, and then it's going to have diffraction grating on the other side, and then an eyepiece down here. And so when you look at a light, it's going to look like this. But if we were to look at an incandescent light, it's going to look different. We can look at different atoms, and it tells us a lot about their electrons. And so a spectrometer is simply a sophisticated spectroscope. What you're going to have is a source. So we're going to have some light on one side. We're then going to have a grating, and the detector now is going to be a camera. It's just like a digital camera that's picking up more of the light that we can't see. And what you do is you take your sample and then you slide it in like that. And so different spectrometers are going to allow us to see different things. And so in IR spectroscopy, what we're looking at is infrared light. And so what's interesting about atoms is that they're vibrating constantly. There's going to be a vibration between atoms and between molecules as well. And so let me give you some example. This would be a carbon and two hydrogens. And what they have are called degrees of freedom. And so there's going to be a lot of vibration going on within a molecule. And what you can have happen is that when you introduce infrared light, it can actually pick up some of that energy. The bond's going to pick up some of the energy of that infrared light, and it's going to make these vibrate even more. It's kind of like pushing somebody on a swing. If you keep pushing them at the right rate, eventually they go higher and higher and higher. And so what happens to that infrared light? It's absorbed. And so what we can do is we can use an IR spectroscope, and we can look at what frequencies of light are being absorbed, and then we can use a fingerprint or a correlation like this, and it's going to tell us what kind of bonds we're going to find within that molecule. Now, if we wanted to look at more of the electronic structure, then we'd be using UV or visible light. And so what we're doing here, same kind of a thing, spectroscope, where we have light, we have a detector, and this time we're just using UV light or visible light. And what we'll find is instead of vibrating those molecules, what we're figuring out is that the photons are being absorbed by electrons. They're moving up to a higher energy level. And so that's where the energy is going. And so we can use a spectrum like this, and it's going to tell us more what those valence electrons or the electrons on the outside are doing. And then we finally have Beer-Lambert law. And what that is Here's an example right here. We have a dye, and then we're shining a green laser into it. And what we're finding is that laser light isn't making it all the way through. And that's because we have molecules on the inside that are absorbing some of that light. And so here's an application of that. It's just a simulation from PHET. We have a light on this side, and then what we're going to do is we're going to measure the amount of light that's moving through it. So I've turned the light on, and we're going to set that to absorbance. It's the amount of light that gets through, and we're dealing with cobalt chloride. And so what we've got is a solution. You can see as I turn down the concentration, more light goes through, and as I increase the concentration, less light is making its way through. And so this is Beer-Lambert law. Basically, as I increase the concentration, less light makes its way through. And so I can do a quick little experiment here. I could set it at 0, and now at 50, and now at 100. Look what happens as we increase it to now 150. Look what's happening to the absorbance. More of it is being absorbed. Now let's move it to 250. And so here's my data right here, where on the left I have the concentration, on the right I have the absorbance. And you can see it looks like a pretty linear relationship. Let's graph it. So that's perfect. And so what we're finding is as we increase the concentration of the solution, more of that light is being absorbed. And so what you could now use is you could just take a sample. We could measure the absorbance of it, and then we could figure out specifically what is the concentration of that solution. And so what did we learn? That light, and using Planck's equation, travels in these little photons, and we could quantify that. We can use it to probe matter, and that's because molecules are picking up or letting go of these photons. And then remember the three major things. Infrared light allows us to look at the vibrations of molecules and tells us a lot about what their bonds are. Ultraviolet and visible light tell us more about their electronic structure, where the electrons are. And then in solutions, those absorbing materials, remember, will pick up some of that light. And so we can use Beer-Lambert's law to make predictions on the concentration based on the absorbance level. So you should have learned to choose the correct spectroscopy to measure vibrational or electronic motion of molecules. So again, if you're looking at vibrational, you better choose infrared. And if we're looking at electronic structure, then you should choose UV or visible light. And then finally, we could use the absorption of light to determine the concentration of absorbing species in a solution. That's Beer-Lambert law. As we increase the concentration, we increase absorbance, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 23. It's on ionic solids. Over the next 4 videos, we're going to talk about 4 types of solids, and what those solids are depend on where their atoms are coming from. So on the periodic table, if we were to draw a line like this, on the left side we're going to have the metals, and on the right side, including hydrogen, we're going to have the nonmetals. And so if that solid is made up of just atoms from the metals, we call it a metallic solid. If it's only nonmetals, but they're relatively small, we call those molecular solids. If they have large structures of covalently bonded atoms, we're going to call that a covalent network solid. And in this video, we're going to talk about ionic solids, which are a combination of metal and nonmetals. And so ionic solids, remember, are going to be made up of, or their structure is made up of ions, which are atoms that have either gained or lost electrons. They're either cations or anions. And so they're put together based on these almost static charges. And so how big those static charges are going to be based on Coulomb's law. And so if they have large charges, it's going to have a better structure, or lattice energy, we call that. And if they're smaller, it's going to have greater structure. And that's because they're closer together, those charges are. And so what are some of the properties that we observe in ionic solids? Well, they have a high melting point. They have low vapor pressure. They're going to be very brittle, break readily, and also they're going to be poor conductors of electricity in a solid form. However, if we were to melt them, they can actually conduct electricity. And if we were to dissolve them in water and create a solution, they're going to conduct electricity as well. And actually making solutions of ionic solids is relatively easy if we use something that's polar like water. And so what does an ionic solid look like? It looks like this. And so it's going to be this nice lattice, and it's alternating ions. And so we're going to have anions like chlorine ion, and then cations like sodium ion. And what's happened is, remember, where we've transferred an electron from one to another, and then they're held together by almost a static charge. And this is an incredibly hard charge. And the reason why is that these are highly charged, these different ions, and also they're really close together. And based on Coulomb's law, opposites are going to attract. And as we decrease that radius between them, we're going to increase the charge between them. And so that's the structure. It's simply this nice lattice of ions. And so then you should understand the different properties. And so what's one big one? High melting point. Since these are attracted together with a really hard ionic bond, we're going to have high melting point. So this is salt right here. Its melting point is 801 degrees Celsius. If we look at sugar, which looks the same, but it's actually held together with covalent bonds, it's going to have a much lower melting point. They also have a really low vapor pressure. What is vapor pressure? Remember, if we put a liquid in a container, the amount of atoms that jump off and form a gas is going to be the vapor pressure as they exert vapor pressure. And so remember, the greater the forces are in that liquid or in that solid, the lower the vapor pressure is going to be. And that's based on, again, these high attractions in the ionic bonds. It's also going to be incredibly brittle. What does that mean? If we were to attach a ionic solid and just pull it from the sides, it'll break right in half. If we were to do that to a metal, it would stretch. It's ductile. Why is it brittle? Well, all of these ions don't like being next to other ions. You can see that all the chlorine ions are as far away from chlorine as they can get, and as we start to force them towards them, they push back. And so that's why they're going to be incredibly brittle. They can't conduct electricity because we don't have a lot of free electrons around. It's simply locked into this lattice. However, if we were to melt it, and so this is a lithium fluoride, beryllium fluoride melted salt, it actually starts to conduct electricity. And if we add it to water, it's going to quickly break apart, and it's going to be an electrolyte. It's going to allow electrons to flow through it as well. Why is it that we can break down ionic solids using something like water? Remember, water is polar. It's going to have partial negative charges on the oxygen side and partial positive charges on the hydrogen side. And so you can see that all the negative sides of the water are going to be attracted to the sodium. And so they can kind of usher it away from the ionic solid. Likewise, on the chlorine ion, what we're going to have are the positive hydrogen parts are going to be attached to it, and that's going to usher it away as well. Once we remove those water molecules, it goes right back to that ionic solid again. And so did you learn two things? Did you learn to show a representation of what an ionic solid looked like? And remember, it's just going to be ions that are locked together in a lattice. And did you learn the properties? The properties are simply built on the structure. And I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 47. It's on heat exchange. If I were to say, don't touch this iron right here in the middle, it's hot, what does that mean? Well, we know that it has a higher temperature, and therefore it has a higher amount of average kinetic energy. And if you were to touch it, a lot of that energy is going to be transferred to your hand, and that's going to produce quite a bit of pain. And so if we ever have a warmer body and a colder body, the warmer body is going to have more kinetic energy. And again, that energy is in the molecular motion, or those molecules moving around. And we're going to have more energy in that than the colder body. And so a good way to represent that, and I'll use this model over the next few videos, is just using these little cubes that represent the amount of energy. In this case, that's going to be thermal energy. And so if I were to put those two objects in contact with one another, that energy is going to be transferred. In other words, energy is moving from that first object to that second object, and we call that transfer heat. And so what we're really doing is transferring energy as thermal energy or heat. Now heat, if you were to look up heat on the periodic table, you're simply not going to find it there because it's not a substance, it's not a thing, it's just the transfer of energy. And so a good way to think about that, and this should be a sentence that should kind of roll off your tongue, energy is being transferred as heat. That's really what's going on. And so when we're looking at energy being transferred as heat, it's going to vary depending on the substance that we're dealing with. In other words, metals are going to transfer energy through heat more readily than things like wood or brick. So let's look at this PHET simulation. So I've got iron, I've got brick, and then I've got water. And so we can assume that we have the same amount of each of these. And if I were to put the water on top of a heating device and the iron on top of a heating device, and I were to just increase the amount of energy, what I'm going to see is an increase in temperature. Well, what's really going on is that we're speeding up those molecules. That's speeding up the molecules of the thermometer. It's spreading apart. Likewise, when we cool it down, what we're doing is we're cooling down those molecules, cooling down the molecules of the thermometer, and therefore it's going down. But we really don't see that energy transfer as heat. And so now what we're going to do is we're going to click on the energy symbols button. And now we're actually going to see that energy inside those molecules. Now as I'm heating it up, what's really happening is I'm adding energy. I'm adding energy to that iron. Now you can see that some of it is being transferred out to the environment through heat. Likewise, when I cool it down, what I'm doing is I'm actually transferring that energy as heat into the ice cubes. So they have lower kinetic energy. What happens if I take that iron and I just throw it into the water? You can see that since it's hotter, it's transferring some of that energy as heat as well to the surroundings until it eventually reaches what we call equilibrium. And so if you ever have a warmer and a colder body, that warmer body is going to have a higher amount of average kinetic energy. And remember the Maxwell-Boltzmann distribution shows us how that works. If we were to look at it, this would be the cold body and this would be the warm body. Now in each of those bodies, they're going to have low energy particles and really high energy particles. But in the warmer body, that average kinetic energy is going to be greater. And so if we ever put them in contact with another, there's going to be a lot of collisions between these molecules. And as they collide, they're transferring some of that kinetic energy. And so what we're really doing is we're transferring energy from the warmer object to the colder object through heat until they eventually reach what we call thermal equilibrium. In other words, it's the same average kinetic energy on both sides. And that picture I showed you of iron at the beginning, eventually what's going to happen is all of that iron is going to have the same amount of kinetic energy because we've transferred that energy out. Now, it's not the same for every substance. And so we use a term called specific heat capacity to measure that. And so right here, you could imagine we have a kilogram of gold, a kilogram of aluminum, and a kilogram of water. And let's say that they're all in a container. And so if you look at it, they're going to have different amounts of specific heat capacity. If we look at the units, that's joules, which is a way that we measure energy per gram, and then Kelvin or degree Kelvin. And so if you have something that has low specific heat capacity, that means it's going to be changed. The amount of energy it has is going to change more readily than something that has a higher specific heat capacity. So let's add a little bit of heat to this and watch what happens to the thermometers. And so the gold, the aluminum are heating up more readily than the water. Now the energy is going to be the same. It's just that the water has a higher specific heat capacity, and so it's able to absorb more energy before it starts to change its temperature. And so did you learn to explain how heat exchange is due to kinetic energy transfer due to molecular motions? If you did, you learned what I wanted you to, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 22. It's on Lewis diagrams and Vesper models. And it's a powerful model if we can use these two together to make predictions about the structure of something like methane over here. Works great if we're looking at atoms that are bonded covalently and also in ions. And so we could take methane, for example, look at its constituent parts, so carbon and hydrogen. We could figure out their Lewis dot diagrams. If you don't know how to do that, I'll put a little video up here so you can see that. Then you could create a Lewis structure, and finally we can create a Vesper model. And once we have that, we can learn all of these things about a molecule such as methane. And so it works on molecules. We start with Lewis diagrams, and I'll give you a method for drawing Lewis diagrams. What we can do is compare different diagrams that we come up with by looking at their formal charges. We can look alternatives, and lots of times we'll find multiple alternatives, and then we have to show resonance. Another model is to use a Vesper model. Vesper model is simply looking at where the pairs of electrons are, and they're going to repel each other. This is simply going to be Coulomb's law. And so based on that repulsion, we can create these three-dimensional models of what those Lewis diagrams look like. And so these two together is a pretty powerful model that you can use in chemistry. What we can use that to predict geometry, bond angles, bond energy, bond length, and we can even predict polarity based on that as well. Lots of times we're going to have to extend it. It's just a model. It's not actually what the atoms look like, and so we can do extensions on this based on overlap of bonds, and also sometimes it's confusing when we get odd valence electrons. And so I'll present another theory. It's called molecular orbital theory. Won't go into detail, but I'll kind of explain where that would be useful. And so first thing we have to do is to know how to draw Lewis structures. There's lots of different methods on how to do this out there. I couldn't find any good mnemonic devices. And so we're going to use VSEPR twice. VSEPR is going to be our model of repulsion, but it's also an easy way to remember how you draw Lewis structures. And so if we're drawing the Lewis structure, the first thing you want to do is add up all of the valence electrons. Next thing you want to do is just sketch out the skeleton of where the atoms might be connected. Next, you're going to add the electrons. In general, you should add it to the most electronegative atoms first and kind of work from the outside to the inside. After you've done that, we can look for pairs of bonds, and then finally we're going to review the formal charges. Now I know this seems confusing, but we'll work through a number of different molecules and I think it'll make sense. So let's say we're starting with this. This is hydrogen cyanide. If we're going to draw the Lewis structure of it, the first thing we want to do is draw and add up the total number of valence electrons. So to figure out valence electrons, we're ignoring the metals. You can see I've removed that D block right here. But what we've got is if you're in this first column, then you're going to have 1 valence electron, so hydrogen. If you're beryllium, you're going to have 2. If you're carbon, you're going to have 4. And so we go up to this molecule and we're going to add up all the valence electrons. And so that's 1 plus 4 plus 5 is 10. So we start by V, adding the valence electron. Next thing we do is simply sketch out the skeleton. An easy way to do that is to just sketch it out by drawing bonds between each of the atoms as they are in the molecule itself. And so we've done that. Now, since these are pairs of electrons, we had to remove 4 of those electrons, so now we're down to 6. Next thing we do is we're going to add the electrons. And so we should add that to the most electronegative, or generally the one on the outside of the molecule. We'll get to carbon in a second. So I'm going to add that to satisfy the octet rule. Remember, nitrogen wants 8 electrons, so it's going to have 2, 4, 6, and then it's sharing the 1, so it's going to have 2 electrons here. So nitrogen at this point is totally happy. But you should see that carbon's not so happy. And so now we go to P. We're going to look for pairs of bonds to try to make carbon a little bit happier. So what we could do is we could share one of those electrons from nitrogen, or one of those pairs, and now nitrogen still satisfies the octet rule, but carbon's closer. Now it has 6 around it. And so we could try that again, and now we've got a Lewis structure for hydrogen cyanide. What's the last thing we're going to do is review the formal charges. And a lot of people don't know what a formal charge is, so we're going to start and go across from the left to the right with hydrogen. How many electrons does hydrogen have? How many valence electrons does it have? Well, it has 1. How many have I assigned it in this model? Well, I've assigned it 1 electron. Remember, it's sharing one of its electrons with carbon, but one of the electrons is really it. And so we're going to have the 1 valence electron it has minus the 1 assigned, and so it's going to have a formal charge of 0. Let's go to carbon. How many valence electrons? It's going to have 4. How many is it sharing? Well, it's sharing 1 here, 1 here, 1 here, 1 here. So it's sharing 4. So it also has a formal charge of 0. Let's go to nitrogen. Nitrogen has 5 valence electrons. It's got these 2 just to itself, but it's also sharing these 3 over here. So it's got a formal charge of 0. If I got formal charges of 0 all the way across, I'm happy. That means that I've got a pretty good model. So let's go on to another one. Let's look at carbon dioxide. What do I do first? I'm going to add up the valence electrons. So that's 4 for carbon plus 6 for each of the oxygen. So I get 16. Now I'm going to sketch out the skeletons. So this is a quick tip that'll help you. If you have an atom written by itself and then a number of other atoms after that, generally this one's going to be in the middle. And so when I sketch out the skeleton, it's going to look like that with the carbon in the middle. Remember, I've used 4 of my electrons, so now I'm back to 12 valence electrons. So I'm going to add electrons. I'm going to add them to the electronegative oxygen on the outside. So how many have I added? I've added all of my electrons. I'm back down to 0. But you can see that carbon's not happy. So what I can do is I can do that pair switching right here. And now I've got carbon. It looks happier at this point. Now if we look at review the formal charges, let's go from left to the right. If we look at oxygen, oxygen is going to have 6. How many does it have? Well, you can see that it has 6 minus 1. So it's actually going to have a formal charge of -1. So that's kind of not a great sign on my model so far. If we look at carbon, it's 0. And if we look at oxygen, it's going to have a formal charge of +1 because 6 valence electrons minus 1, 2, 3, 4, 5. And so it's going to have +1. And so could you put together this model in a different way so that I would have lower formal charges? For sure. What I could do is I could switch and get a pair on one side. I could switch and get a pair on one side. And now I got formal charges of 0, 0, and 0. And so this is what it looks like. Now I should probably jimmy this a little bit. I should switch these pair of bonds over here and these over here, but this is pretty close. Now let's go to ozone, O3. So I'm going to add the valence electrons, sketch out the skeleton. Let me add those electrons. You can see I've got an extra one compared to when I did carbon dioxide. And so now, if we draw that, I've got one structure like this. Could draw my formal charges. So that's okay, but can you visualize this, that I could kind of invert it the other way? And I could also get those formal charges. Remember, formal charges, the closer they are to zero, the more stable kind of that structure is. But these ones have the exact same formal charges. And so what am I going to draw? I'm going to draw resonance. I'm going to draw this arrow in the middle, this two-way arrow, and that means that this structure or this structure are properly. So we have to show both of those structures. Now let's get to the VSEPR model. So VSEPR model is the valence shell electron pair repulsion. What does that mean? It's very simple. It simply means that when you have a pair of electrons, they have this negative charge and they're going to push on other pairs of electrons and they're going to push on themselves. And so think of it like a balloon. If you were to hold one balloon, it would look like this, but if I were to give you two balloons, they're going to move apart from each other if we hold it in the middle. And so that tells us what the electrons are going to do and therefore what the structure is going to be. So imagine if we have carbon dioxide like this, it's going to be the same, where if these pair of electrons, these pair of electrons, your hand is kind of holding it in the middle. And so what shape, three-dimensional shape, do we think it's going to have? It's going to have this kind of a shape. We call that linear. Linear is in a line. I know it doesn't look three-dimensional, but it will get there in just a second. What's going to be the bond angle between the two? We call that 180 degrees. And this is a linear model. So you can see now how VSEPR allows us to start kind of visualizing these in three dimensionals. Or in three dimensions. One quick note, if you're doing organic chemistry, lots of times they'll call this SP hybridized at this point. I'm not going to go into what that means in AP Chem. It's not important, but it is important that you understand the terminology. Let's go to three electrons now, three pair of electrons. So we got three balloons. It's going to organize itself like this. What's something that looks like that? Maybe nitrate. And so if we're looking at nitrate like this, it's going to have the nitrogen in the middle, those electrons around the outside. And so this is going to be that VSEPR model. It's going to be trigonal planar. So it's going to have these three electrons coming out, or these three atoms coming out. It's going to be a 120-degree angle between the two. But it's also going to be flat at this point. Again, quick organic chemistry note, we call this sp2 hybridized. So again, we haven't got to this third structure yet. We haven't got to this third dimension, but we're quickly going to get there. Let's say we're looking at something like ozone. Ozone, you might think is going to be linear, but if you look at this pair of electrons out here, what kind of a structure are we going to get from ozone? We're going to get a bent kind of a structure. And now let's get to four pair of electrons. With four pair of electrons, methane is that example I gave you at the beginning. What's that going to look like? Well, if you hold four balloons in your hand, it's going to have this tetrahedral shape. The bond angle is going to be 109.5, and it's going to really rise out of the paper itself. We call this sp3 hybridized, and that's kind of where it ends. In AP Chem, your knowledge of all these bond angles and geometry, know that we can also have more pairs of electrons, and as we do, we get to what's called, let's say we're looking at PCl4, that's going to be trigonal bipyramidal, and so they're going to branch off like this. What you really have is a trigonal planar here in the middle, and then you're going to have a linear structure right down here through the middle. Why do we call it pyramidal? If I were to connect those with lines, you can see how we kind of have two pyramids on top of each other. Octahedral is when we're going to have six pair of electrons coming off. Again, bond angle, you don't have to know it, but you do have to know that we call this an octahedral at this point. And so what are some extensions? What are going to be some things that we have to build on this VSEPR model? Well, one thing we're going to have to do is understand that not all the bonds are going to be the same. Single bonds like this are going to be different than double bonds like this, and that's because the orbitals are going to start to overlap. And so in a single bond, what we have is called a sigma bond. Sigma bond is where they're sharing those electrons between the nuclei. But as we start to add more electrons that are being shared, what we're using is an overlap of orbitals, and so we get what are called pi bonds. And so pi bonds, so this would be a sigma bond and then a pi bond, or I could say this is a sigma and this is a pi bond. Those pi bonds, as we add them, are going to be less powerful, but they're also going to kind of lock the molecule in itself, so you get formation of isomers. Also, sometimes the math doesn't add up. In other words, we're going to have an odd number of electrons. So how do we add these pairs if we're adding one single electron? So nitrogen dioxide is actually going to have a Lewis structure like this, but it's going to have one single electron out here. So we call that a free radical. And so there are extensions, and so we can build a better model. It's called the molecular orbital model, or orbital theory. It's based on quantum theory and mathematics. It's just a different model, and we can answer a lot of these questions, but it's probably a little too intense and a little too sophisticated for AP Chem. And so again, did you learn the following to use Lewis geometry and VSEPR models to predict geometry, hybridization, polarity? If you did great. Try one on your own. Let's say I give you water. Could you draw the Lewis structure? Could you draw the VSEPR model? Watch out for those electrons, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 16. It's on London dispersion forces, which were first identified by Fritz London. That's where they get their name, after this whole idea of quantum mechanics had been developed. Can you find him in this picture? He is right here. But before we move on and talk about it, think about the forces in this picture. Which are greater, the forces within the individual people holding their atoms together, or the forces between them holding them together in this photo? Well, clearly it's the forces within your body. And so this is the first video in a set of videos that talk about bonding between molecules and within molecules. And so if we think of them all as molecules and we move them apart a little bit, there are going to be the intermolecular forces. Those are going to be the forces between the molecules, between this molecule and this molecule, and between this molecule and that molecule. And these are generally going to be really, really low compared to the intramolecular within the molecule itself. And we'll talk more about those in later videos. But London dispersion forces are going to be attractive forces. These are intermolecular between molecules. And they're going to be found in all atoms and molecules. So everything is attracted through London dispersion force. It's really important. What really develops them are uneven electrons. As the electrons are distributed unevenly, they create what are called a temporary dipole. Those are going to be a molecule that has a charge. It has a positive and a negative charge. These are going to increase as we increase the contact area between the molecules. Also as we increase their polarizability, which is going to be the squashiness of a molecule. Generally, the more electrons you have, the higher this is going to be. And so as we increase molecular size, we're going to increase these dispersion forces. And finally, pi bonding, which is going to be where orbitals overlap. If we have more pi bonding, we're going to increase these. And so let's look at it. Why are London dispersion forces important? Well, they're in everything. And if it weren't for them, we'd never have noble gases in a liquid phase. And we know we can do that if we can cool it down. And so what holds helium together when it gets into this liquid phase? It's going to be these London dispersion forces. So right here I have two helium atoms, and so they're going to have two protons on the inside, two electrons on the outside. And so as we move them close together, watch what happens to their electrons. Let's watch that again. As they move close together, the electrons are going to migrate. What's doing that? Well, the electrons on the outside of one helium are going to be attracted, just Coulomb's law, to the protons on the inside of that other helium. There's also going to be repulsion between those electrons on the outside. And so what this really is creating are two what are called temporary dipoles. They have positive and negative ends. And so a London dispersion force is simply going to be the connection between those two. It's fairly simple. It's going to hold them together. Now it's just instantaneous, it's temporary, and then it's going to go away. But if we have enough of these atoms in an area and it's cool enough, then we can get that. So what's going to increase these London dispersion forces? Well, contact area is one thing. The more electrons we can have closer to each other, the more of these forces we're going to find. So if we look over here at N-pentane and neopentane, they're both going to be made of the same atoms. But these ones right here are going to be looking more like a column and these more like spheres. And as a result, these ones are going to have more surface area, more contact area, so we're going to have greater forces. And so the boiling point of N-pentane is going to be higher than that of neopentane based on these London dispersion forces. What else? The polarizability. And polarizability, remember, is the squashiness. The more electrons we have, the more forces we're going to have. And so this right here is a protein. Proteins are massive in size, and a lot of that three-dimensional shape comes from these London dispersion forces. Also, it's going to explain why as we go down in the periodic table, let's look at the halogens right here. Halogens are going to have the same valence electrons, but as we go to fluorine, chlorine, bromine, and iodine, we're actually going to go from gases, fluorine, chlorine, to liquid bromine, and then solid iodine. And that's all going to be based on these London dispersion forces. As the atoms get bigger, they have more electrons. We're going to have more of this uneven electrons. And then finally, pi bonding. That's going to have orbitals that overlap. It forms something called a pi bond. If we increase the number of pi bonds inside those molecules, we're going to increase these London dispersion forces. So again, what are they? They're attractive in nature, found in everything. It's uneven electrons create these temporary dipoles. Remember, what increases it, our list would be contact area or surface contact. Also the polarizability, which is going to be based on the molecule size, and pi bonding. Can you do that? Could you explain these trends? If you can remember those three things, you've got it, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 71. It's on free energy and the equilibrium constant. Over the last 20 videos, we've been talking about two things: thermodynamics and the importance of delta G, where we can think of delta G as the amount of free energy available in the products and the reactants, and a reaction occurring as we kind of move from reactants to products. And then we started talking about equilibrium and the importance of K, which is a measure of the concentration of products to reactants. As K is equal, so are the reactants and products. As it increases, we shift towards the right. As it decreases, we shift towards the left. But it's important that you understand that we can interchange these two things, delta G and K, and that they are inherently tied together. And so in any reaction, we can look at it using thermodynamic reasoning and the importance of changes in free energy or changes in delta G, and also looking at it as an equilibrium reaction where we've got K, this equilibrium constant, which tells us, are we shifting more towards the right or towards the left? And that there is a algebraic connection between these two, where delta G equals the negative RT, so that's going to be the gas constant because times the absolute temperature times the natural log of K. And so we can interact between the two. And if we figure out our delta G, which, I mean, you could use the appendix in the back of most chemistry books to figure it out, that tells us a lot about what's going to happen to K. And so let's say K is equal to 1. We have an equal amount of reactants and products. Well, if we plug that into this reaction, that means our delta G, or a change in delta G, is going to be equal to 0. What happens if our K value is greater than 1? In other words, it's shifted towards the right. We'd now have a delta G that's going to be a negative value. So we think of this as an exothermic reaction. It's spontaneous. It's moving towards the right. And then if we look at a K value much less than 1, then we're going to get a delta G of a positive value. So that's an endothermic reaction. It's consuming energy. It's non-spontaneous. And so it's really tying together these two big thoughts that we've been talking about for a long time. Now, generally in AP Chemistry, we've only talked about exothermic or endothermic, but you should also understand there's energy involved in this. And so we could think of this as an exergonic or giving off energy reaction or an endergonic reaction. Now, why is that important? Well, in biological systems, it's important to look at the amount of total energy that's either given off or being consumed, not necessarily the heat that's given off or consumed. And so if we look at this interaction right here between delta G and K, and let's look at a few reactions, reversible reactions. So in this one, the breakdown of water into its different ions, we would call a delta G value, if we measure that, of 79.9 kilojoules. Now let me show you what the K value is. It's going to be a really, really small value. What do we know about a positive delta G? That means it's an uphill reaction, non-spontaneous reaction. What do we know about a really small K value? That means it's going to be shifted more towards the left, or shifted more towards the reactants in this case. If we look at another reaction, in this case, we've got a delta G that's a negative value. What's that tell us about its K value? That's going to be a positive value. So this is a spontaneous reaction or a downhill reaction. And in this case, it's shifted way towards the right. So you should be able to predict, if I give you a delta G, what's going to be my K value? Is it going to be positive or negative? That'd be the first question. And is it going to be a really small or a really large value? So since our delta G is a positive value, we know that our K value is going to be really, really small just using this equation up here. And so you could plug in a gas constant and our absolute temperature, and that's going to be easily calculated. And so if we were to summarize it again, how are these two tied together? Delta G is negative, then we've got a K equal to a value greater than 1. That's going to favor the products, or it's going to move more towards the right. If it's equal to 0, K equals 1. And then if delta G is going to be a positive value, our K value is going to be much less than 1, or it's going to favor the reactants. And so why is this important? Well, if we're looking at biology, if we're looking at the chemistry of life, it really tells us how we can couple reactions together. And so if we look at this famous reaction up here, what we've got is glucose combining with oxygen, and we're making carbon dioxide and water. And so what is this? This is going to be cellular respiration. It's taking place in all the cells of your body right now. If we were to look it up in the appendices, we'd find our delta G value is going to be negative 2880 kilojoules. So we've got a delta G value that's a negative value. What does that mean? It's going to shift towards the right. So what would our K value be? It's going to be greater than 1. So that's going to favor our products. It's going to move towards the right. This is a spontaneous reaction if we can get it going, and we use enzymes inside the cells to do that. Now, what are we using that energy to do? Well, we've got another reaction here. We've got adenosine diphosphate, and if we add a phosphate to it, we make ATP. What do you use ATP to do? It's used in all the cells of your body. It's essentially cellular coinage that your cells use to do work. I mean, that's how you think, that's how you move, that's how you kind of do all the chemical reactions inside your body. And so what's going on inside our cells, more appropriately inside the mitochondria of our cells, is that we're coupling this exergonic reaction, or this reaction that gives off energy, with an endergonic reaction, one that consumes it. And so you could think of these as gears. As we're converting that sugar into carbon dioxide and water, we're using the energy that's released in that endergonic reaction, and we're tying that to, or exergonic reaction, we're tying it to an endergonic reaction. And so did you learn to relate delta G to K? In other words, what happens as we decrease our delta G, as we shift it more towards the right? What happens to our K and vice versa? I hope so. And not only do I hope that was helpful, this is the last video in this series, and so I hope the whole AP Chemistry series has been helpful. I hope you've been along with me, and thanks for watching. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 18 on intermolecular forces, which are simply the forces between molecules. And so when we were putting drops of water on this penny, we were able to get 43 drops on there because there are high intermolecular forces between the water molecules. And so intermolecular forces are important because they give us the properties of solids and liquids and gases. And so some of the properties would be the boiling or melting point, surface tension, capillary action, vapor pressure, and miscibility. And we'll talk about each of these. And in gases, there's not too many intermolecular forces because they're moving around really, really quickly. But when there are intermolecular forces, they explain the difference between an ideal gas, which can be explained using the ideal gas law, and real gases. And this usually occurs towards condensation. We can use a PV relationship to find it. And then finally, intermolecular forces are incredibly important in biology. In both enzymes and proteins, these forces between molecules are incredibly important. So let's make sure you know the difference between inter and intramolecular. Intermolecular are going to be the forces between molecules, so between this one and this one. Intramolecular are going to be within the molecule itself, and so we'll get to those when we start talking about covalent, ionic, and metallic bonding. But intermolecular forces are simply the forces between these molecules. And so let's take a look at them. Let's say we vary the strength. Let's say we make those forces weaker. What happens? They'll spread apart. What happens if we make them greater? They're going to come together. What happens if we make them even greater? They're going to come together and form a real nice structure, so something like a solid. And so what are some properties that are affected by intermolecular forces? Well, let's start with the melting point or the boiling point. And so melting point is when you go from a solid to a liquid. And so if there are greater forces, it's hard to get liquids to start to form. And boiling point is going to be these molecules actually jumping off into a gas. And so the greater those intermolecular forces are, the harder for it is to move off. Surface tension is going to be like a skin over a liquid. And so imagine down here that we're looking down at 3 drops of 3 different liquids. And those liquids are mercury, alcohol, and water. Could you match them appropriately? Well, mercury is going to have the greatest intermolecular force, and so those are going to be right here. And water is going to be next, and so it's going to form this nice bubble due to hydrogen bonding, and then alcohol is going to spread out. And so we can look at intermolecular forces. It's going to tell us how much of that skin on the surface is going to form. Capillary action is going to be movement of a liquid up a tube. And so if we're looking at water, not only is water attracted to itself, we call that cohesion, but it's also going to be attracted to the tube that it's in. We call that adhesion. And the thinner we make that tube, the more the water is going to move up. And that's how water gets up a tree. There are really tiny tubes called xylem that allow water to move up it. But if we were to look at something like mercury, it's attracted to itself, but it's not attracted to its surroundings. And so it's actually going to move down in a capillary tube. Next is vapor pressure, and vapor pressure is measured in a closed system. So if we put a liquid in a closed system, it's going to be the amount of pressure exerted by the gases. And so how are we going to get more gases there? They're going to jump from liquid to a gas stage. And so the higher that vapor pressure is, the more volatile that liquid is going to be. So alcohol, for example, is going to have high volatility, and that's because a lot of it is jumping out of this liquid phase into the gas phase because there are low intermolecular forces. Miscibility, you can think of that as like mixability. How easy is it for 2 different materials to mix together? Well, you know that water and gasoline don't mix well. The reason why is that water is going to be polar and this gasoline is not. But water does mix readily with hydrochloric acid, and that's because the hydrochloric acid molecule is going to be polar. And so these like charges are able to dissolve like charges, and vice versa. Also, this explains why water is really, really good at breaking down ionic compounds. And so this is salt, and salt is really high bonds in an ionic compound, but if you add water to it, it readily breaks apart. And the reason why is those chloride ions, or the chlorine ions, are going to have a negative charge, and the positive parts of the water are able to surround it. And if I add a sodium ion here, which is positive, the negative parts of the water are going to surround it, and that allows it to break down. When we get to gases, remember, we have ideal gases, which can be explained using the ideal gas law, where PV equals nRT. And then we have real gases. Now, an ideal gas is an imaginary model, and it assumes that there's no attraction between these molecules, and that there's an infinite amount of space for these molecules to move around. But as we start to cool down those gases towards a liquid phase, we start to get attraction, intermolecular attraction between these molecules. And also, we have a finite kind of a space, and so this law starts to fall apart. So if we were actually to graph it, PV over RT for an ideal gas, if we graph it, will always be 1. But if we were to vary the temperature for a real gas, let's try nitrogen, at 1,000 Kelvin, it would look like that. 500 it would look like that, and 200 it would look like that. Now the farther you are off that blue line, the farther you are off of an ideal gas. And so you can see that as we cool nitrogen down, as we get it closer towards that condensation point, that model of an ideal gas is falling apart. We could look at different gases at 313 K as well. Let's look at hydrogen versus nitrogen. You can see hydrogen is going to be more like an ideal gas, and that has to do that it's a smaller mass and is going to move more readily. It's also incredibly important, these intermolecular forces in biological systems. And so this is an enzyme. An enzyme is basically a catalyst that breaks down a molecule. In this case, this could be sucrose, which is sugar, and it's broken down by sucrase. These intermolecular forces are incredibly important. It almost has to fit in like a key inside a lock. And enzymes in almost everything in life that's important are made of proteins, and there are huge intermolecular forces within this giant macromolecule that hold it together and give it its characteristic space. And so did you learn the following 2 things? To explain observations regarding solubility of ionic compounds, remember something like water, since it's polar, can break apart those ions and kind of usher them away from the ionic compound. And then finally, can you explain terms like vapor pressure, viscosity in terms of strength and type of intermolecular forces? We went through this list, and it's all based on those attractions between the molecules, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 61. It's on kinetic reaction control. Or more appropriately, it's comparing that to thermodynamic reaction control. Lots of times in a process, a spontaneous process, there's a choice that's being made. And determining on which path we take, we may have different products. And so it's kind of confusing, and I wanted to start with an analogy. Imagine if I asked you to buy a car, but I only gave you two places that you could go. You could either go to kinetic used cars, or you could go to thermodyne new cars. And so you're going to have to make a choice. And depending on which choice you make, you're going to get a different car. If you go to a used car dealership, you might get a car that looks like this. And if you go to a new car dealership, you're going to have a car that looks like this. Now, there are going to be advantages of both. In other words, what's the advantage of buying a used car? It's going to be super cheap. It won't be as expensive, but you're going to get a different product. If you have enough money, it's better to get a new car because that new car is going to be more reliable. And so this choice is also being made in spontaneous processes. In other words, there's control. And so it could either be kinetic control, and that kinetic control lots of times is based on activation energy. It's the cost of that process. And then we also have thermodynamic control. What's governing that? That's going to be the change in free energy, or our delta G. How much difference in free energy is there between the reactants and the products in this downhill reaction? And so let's go back to the cars for just a moment. So if we start with that cheap car right here, what's the advantage of that cheap car? It's going to have a low cost, but it's also going to have a low reliability. If we have that more expensive car, it's going to cost us more money to begin with, but it's going to be more reliable over time. And so what's governing that choice is really cost. If we don't have the money to buy a new car, then we're simply not going to be able to buy it. But if we do have enough money, it's better to buy that new car because it's going to be more reliable over time. And so what's really governing this choice? It's going to be that initial cost. Money is determining the path. Now let's stop talking about cars and then apply this to chemistry for a moment. And so in a free energy diagram like this, we start with our reactants. And so let's say we have this one pathway where we have reactants and products, and then we have another pathway like this. What are we getting? We're getting different products of it. So what's going to govern the difference between these two pathways? Well, it's going to be the activation energy. It's how much energy we have to put in to get that reaction going, to achieve that transition state. If we don't have enough energy to reach this transition state, then we're going to have to take this lower pathway. Our products are going to have less stability. They're going to have less energy in them. So what's governing the other pathway? That's going to be our change in free energy. We would like to take that pathway if we could. We'd like to have more stable products, but we can't unless we achieve a high enough activation energy. So what's really determining the path? A lot of the time it's the temperature that we have. And so let me give you an example of that. Let's say we have this reaction right here. We have our reactants on the left side and we have products on the right side. But let's say this product is less stable than this product. Well, if we're looking at this chemical reaction at a really low temperature, you can see that we're getting really low amounts of that more stable molecule and high amounts of the less stable molecule. Well, what do you think is going to happen if we increase the temperature? So we're increasing it almost 100 degrees, a little over 100 degrees Celsius. What's going to happen? Well, we're able to create more of that more stable molecule. Why is that? We're taking that thermodynamic pathway. We're taking that new car dealership pathway. And so in that first process, again, there was kinetic control going on because we didn't have the energy. We didn't have the money to take that path. But if we do, it's more advantageous to take the thermodynamic path. And so again, can you explain why a thermodynamically favored reaction may produce varying amounts of products? Again, it determines on which pathway you're taking. If you're controlled by the kinetics, then you're going to take that lower pathway, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 9. It's on mass spectrometry, which is a way that we can separate atoms, isotopes, even fragments of molecules based on their mass. And so it's an incredibly effective machine. But before we get to the specifics of that, I want to talk a little bit about John Dalton. John Dalton was one of the pioneers of modern chemistry. And he was presenting at a conference in 1803 when he put forward his Dalton's atomic theory. And so let me go through that. And what I want you to think about is which of these have we changed over the last 200 plus years? He believed, number one, that elements are made of extremely small particles called atoms. He believed that atoms of a given element are identical in size, mass, and other properties. Atoms of different elements differ in size, mass, and other properties. He believed that atoms cannot be subdivided, created, or destroyed. He believed that atoms of different elements combine in simple whole number ratios to form chemical compounds. And then number 5, in chemical reactions, atoms are combined, separated, or rearranged. And so over the last 200 plus centuries, if we were to look at those 5 things he put forward, there's really only 2 errors that I can find. Number 1, are all elements or all atoms of the same element going to have the same exact mass? No, remember they're going to be isotopes. Those are going to be the same the same element, but they're going to vary in the number of neutrons that they have. And then the other one is that we can subdivide atoms. So when we're looking at fusion or fission, but those really lay outside of normal chemistry. And so he did an incredible job. And what we're really going to focus on in this video is number 2, identification of isotopes. And so mass spectrometry is a way that we can modify Dalton's atomic theory. And we did that through the identification of isotopes. And that's around the early part of the 1900s. Isotopes, remember, are going to be the same element, but they're going to have a different mass, and that's based on the number of neutrons that they have. And what we can do from that is we can eventually calculate the average atomic mass, and that's going to be on the periodic table. It's sometimes referred to as the atomic weight. Now, also mass spectrometry can be used to look at individual atoms, elements in a sample, and we can even break apart big macromolecules and look at the fragments that are found within that, or molecules within it. And so if we look at a basic mass spectroscope, what we're going to see are 3 parts. We're going to have an ionizer, a mass analyzer, and then a detector. And so let's look inside the ionizer. What are we going to find? Well, the first thing we're going to find is it's a total vacuum. In other words, this doesn't work unless we remove all of the gas particles that are found inside the mass spec. Next thing we're going to do is we're going to insert our sample in. That could be a solid, it could be a liquid, it could be a gas, but we're going to inject it into this ionizing tube, and then we're going to hit it with electrons. And so we're going to move electrons through the sample. And so there's a little cathode ray tube. It produces all these electrons. And what it's going to do is it's going to pull electrons away from the sample. And as it does that, it's going to create a number of positive ions. And so we're going to ionize that sample inside here. Remember, it's still the sample, it's just ionized. It's lost its electrons. And so now we move to the mass analyzer. That's really only going to have 2 parts in it. It's going to have an electrical field. You can see that's negative because we want to move the ions into the mass analyzer. And then we're going to have a magnet. And what that magnet is going to do is it's going to bend the path of the ions. And so as we're bending the path of the ions, it's just like driving around a corner. If you're really heavy, it's harder for you to make a corner. Let's say if you're in a big semi-truck. But if you're in a little motorcycle, it's easier to make it. And so this is where we're going to figure out the difference between the mass of those ions. And then finally, we have a detector. That detector is going to be made up of 2 things. We're going to have an electron multiplier, which is essentially a plate. As an electron hits it, it spawns more electrons, which hit the next plate, which spawns more electrons. And so we can really have a small amount of ions or anything hitting that plate, and we're going to get a signal. Now that signal has to be amplified, but eventually we can send that into a computer and we can look at the spectrum coming from those different masses. And so the first thing you have to do is you have to calibrate the machine. What does that mean? You're going to start sending ions through. Okay, so that ion didn't hit the detector. Why is that? It's because the magnet is turned up too high. And so we're going to have to lower the strength of that electromagnet. We run another ion. Okay, now the magnet's not quite strong enough. And so now we run another ion, another ion, another ion. Okay, so we've calibrated it, and so it seems like it's working well. Which of these would be heavier? Well, the ones that are heavier are going to be the ones that can't quite make the corner, and so they're going to end up out here, and then the lighter ions are going to end up right here. Now let's actually get to some sampling. And so this is what it's going to look like when we create a spectrum. We're going to have the different weights across the bottom, and then we're going to have the intensity. And so wherever the intensity is high, we're going to have peaks. That means we have a lot of ions that are with that specific atomic weight. And let's try chlorine. So we're going to put chlorine through here. Chlorine really only has 2 stable isotopes. It's going to have chlorine 35 and 37. And so let's watch and see what happens as we send this chlorine through the mass spec. Okay, so what did we find? Well, there's really only 2 types of ions, and so we're having 2 peaks. Which one is going to be the chlorine-37? Which one's going to be the heavier ion? Well, that's going to be this one right here because it wasn't bent as much using that magnet. If we look back at that, let's look at those ions flow again. So you can see the chlorine-37 doesn't quite make it around the corner. And which do we have more of? Well, we're going to have more of that those with an atomic mass of 35. Okay, so once we've got that, we can really figure out this average atomic mass. And so how do we figure that out? Well, I'm using values right here that I grabbed from Wikipedia. So here are going to be the two stable isotopes that we have of chlorine. Here's going to be their mass, their actual mass. So that's based on the number of protons, neutrons, and electrons inside it. And then this is going to be their abundance. In other words, it's around 75% of chlorine-35 and around 25% of chlorine-37. And that's why this peak is going to be 3 times the height of this peak if you're looking at a spectrum. So how do we figure that out? Well, that average atomic mass, sometimes referred to as the atomic weight, is simply going to be the mass times the abundance plus the mass times the abundance. And so in this case, since we only have 2 isotopes, we're just going to only have 2 values here. But if we had a lot of isotopes, we're just going to have more mass times abundance. We just add on like that. So let's throw in the values here. So we've got mass A, which is going to be 34.97. And we're going to take that times its abundance, which is around 75%. We then take the other isotope, which is chlorine-37, and times its abundance. And what we get is 35.45. And that's what's going to be on the periodic table. And so when you're looking at those values on the periodic table, what you're looking at is the average atomic mass. And they figured that out by looking at the natural abundance. Okay, now what's important is a mass spec can be used for other things. Not only for atoms and isotopes within individual, or isotopes within an individual element, but we could look at atoms within a molecule, and we can even look at fragments within macromolecules. And this right here is myoglobin, which is a massive protein, and what we can do is we can send it through a mass spec, and what we can figure out is all the amino acids that are found within it. And so remember, wherever the peaks are going to be a little bit higher, then we're going to have more of that amino acid. And so usually what they measure this is M to Z, which is like a mass to charge ratio. And so did you learn this? How to use data from mass spectrometry to identify elements and mass of individual atoms in an element? Remember, it all ends up on that curve. And if you can make the curve or not is going to be based on your mass. We can look at a spectrum from that to figure out their abundance, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 41. It's on multi-step reactions. Imagine I'm going to build a toy out of the parts that are sitting right here. So maybe I take a base and then I carefully attach a wheel to it. Can you figure out what I'm making? Add a few more wheels, a few more parts, maybe a window, and pretty soon I have a toy train. But I didn't just build that in one step. I had to build it step after step after step. And so chemical reactions occur along a same path. We have the reactants, we have the products, but it doesn't just magically appear. We have to go through step after step, and we have all these intermediates along the way. And so when you're looking at an overall reaction, remember, it's not the whole story. The whole story is each of those elementary steps added together. Now, each of those elementary steps are based on the collisions between particles, and so that collision theory is going to tell us a lot about the speed of which that reaction is occurring. And so adding all those up, we get what's called the reaction mechanism, or the overall steps of the reaction, and this can only be postulated. In other words, when you're looking at an overall reaction, we can make predictions about the stoichiometry, in other words, how much mass or atoms or moles we're going to have at the beginning and at the end. But if we're looking at the reaction mechanism, we can't do that. In other words, we can't predict what's going to happen. We can only measure it. And so the rate law can be measured experimentally, but each of those steps have to be figured out, and that's what chemistry does. So if we're to look at this overall reaction right here, I could make immediate predictions about the stoichiometry of this reaction. In other words, I know I have 1 mole of this on the left, I should get 1 mole of this on the right. I could figure out the mass on the left and the mass on the right, but when I look at that overall reaction, I know nothing about the rate law. It can be measured, but I can't make predictions about it. And the reason why is this is based on a reaction mechanism. In other words, this is not just one step. This is 2 steps, or scientists think that this is 2 steps. We have this first elementary step and then the second elementary step. And you can see there are things showing up here that don't even occur in that overall reaction. And so if we're looking at the reaction mechanism, it can only be postulated. Chemists can put forward an idea of what they think is going on, but we actually can't make predictions. However, if we break it down into its elementary reactions and we know that's what's going on, then we can make predictions about it. And so if we know this is the first elementary step, then we can take a look at that and we can figure out things like the rate law. If we know this is that first elementary step, we know that these 2 things are colliding together. We know that this is a bimolecular reaction. We could even model what's going on here, and so we could make predictions about the rate law. The rate law is simply going to be K, or the rate constant, and this is going to be a second order reaction because this is the concentration of each of these 2 reactants. And so let me give you an example of this. This is one of my favorite chemists. This is Melvin Calvin. He got a Nobel Prize for this work, and what he was trying to do is unlock what leaves do. In other words, leaves are able to take in carbon dioxide and make sugar. But it's not just one step, it's a series of steps that are going on. And until he figured it out, it was really a black box. We didn't know what was going on. And so what he did is he would stop the reactions at different points. He would figure out the intermediates of that. And then he came up with what we call now the Calvin cycle, named in his honor. And so remember, reactions don't occur just in one step. There's a series of elementary steps within that. We can make predictions about that. But once we get to the level of the elementary reaction, we can figure out what's going on. And I hope that was helpful. Hi, it's Paul Anderson, and this is Chemistry Essentials Video 6. It's on periodicity. In other words, it's going to be the patterns that we see in the periodic table. Now, what determines that is going to be electron configuration, and we can figure that out using the Aufbau principle, which is actually German, and it means the principle of building up. So we're building up from lower to higher energy levels. And so what we can find is these trends that start to emerge, but it's most important, instead of just memorizing them, that you really understand what's going on inside the atom that determines those trends. And so periodicity, remember, is going to be derived from the electron configuration, in other words, where the electrons are. And we can determine that by using the Aufbau principle. And if you were to watch the last video on electron configuration, I think that'd help a lot. But what's the meaning behind this? It all comes from Coulomb's law, which helps to explain electron configuration. And also helps to explain these trends. It explains changes in the ionization energy, changes in the atomic and ionic radii, how big the atom or ion is, electronegativity, and finally the ion charge. And so if you really understand Coulomb's law, you can kind of work your way through this on the periodic table. Why is this important? We can use the periodic table to make predictions, especially about things that we haven't even designed yet. And so if we look at the periodic table, this on the right side is going to show us which of these are going to be filled over time. But if you look at the periodic table, we'll find trends. And so here's hydrogen. What we really need to do is take helium and then put it over in this S block. It's going to make us, it's a little easier to understand. And so what we're going to have are energy shells, and then these would be subshells within that. And so one thing you should understand about the periodic table is that this F block should slide right in here. It'd be hard to write a convenient periodic table, but that's really how it should be set up. Generally, we just put it down below. And so what's guiding this or explaining the electron configuration, remember, is Coulomb's law. And so it's pretty simple. If we look at the protons on the inside of the nucleus, they have a positive charge. The electrons have a negative charge. And so Coulomb's law says we just multiply those. In other words, the bigger they are, the bigger the force between the two is going to be. But as we increase the radius, the distance between the nucleus and those electrons, then we're going to see a decrease in that force. The one thing that you have to add to that is that once we fill up one of these orbitals or subshells, it's going to shield the electrons on the outside from those on the inside. So let's get started and work through this list. What's going to happen to the ionization energy? Well, let's look at Coulomb's law. Ionization energy is the energy required to pull one of these electrons away. And so what's going to happen as we increase the size of atoms, we're going to increase the number of protons, and so we're going to make it harder for you to pull an electron away. And so we move across the periodic table, we're going to see an increase in ionization energy. What's going to happen as we go down the periodic table? Well, as we go down the periodic table, they're getting bigger and bigger and bigger, and so the radius is going to get larger. And so therefore, we're going to see a decrease in ionization energy. So you can think of ionization energy going up and to the right. Now, it's not as simple as this. What we're really looking at is within subshells, we're going to see that pattern because you'll see changes within here and orbitals as well. But it's just a general trend, and it comes from Coulomb's law. Let's look at atomic and ionic radii. Well, what happens as we increase the atomic number? We're increasing the number of protons. What is that going to do? It's going to pull it in. In other words, it's going to pull those electrons more closely to the center. And so it's actually going to be the opposite. It's going to increase as we go down, and it's going to increase as we go from the right to the left across the periodic table. And so you can see this graph of atomic radii is actually going to be the inverse of what we saw with ionization energy. What about electronegativity? Electronegativity is how much an electron, and it's bad to say this, but wants an electron. In other words, how much it would like to receive another electron. Well, remember, as we're going across a subshell, let's say we're going across this p block right here, as we go across, we're increasing the number of protons, and therefore we're increasing that pull of the nucleus on the electrons outside it. And so as we move from the left to the right, we're going to increase how much that atom wants an electron, at least until we get to the noble gases. And so electronegativity is going to follow ionization energy as well. What if we look at then ionic charge? Well, to look at ionic charge, we really have to look at how close an atom is to a noble gas. And so let's throw noble gases up here. Noble gases are going to have a full inner electron subshell. And so anything that moves you towards that is going to make you a more stable atom. And so remember, the only atoms that exist by themselves are going to be the noble gases up here. So a quick way to figure out ionic charge using Coulomb's law is to just look how close you are to a noble gas. And so let's look at the halogens, which are right here. How many electrons would halogens have to get in order for them to move to a noble gas? Well, just one electron. And so they're going to have, in general, a -1 charge. Let's move over. These would have -2, -3. Let's go way to the other side with the alkali metals. What about them? Well, it would be hard to go all the way across here to get to the noble gases. It's just easier to go around the back. In other words, they could lose the electron, and when you lose the electron, you have a +1 charge. And so we could kind of work it up in this direction as well. And so again, it's not hold fast. In other words, these are general trends, but they can all be predicted just by applying Coulomb's law. So it's hard to talk about the periodic table without talking about Dmitri Mendeleev, who's really the father of the periodic table. But you've probably never heard of Julius von Meyer, who was a German who was working on the periodic table at the same time and published his periodic table around the same time as Mendeleev. Now, why haven't you heard of Meyer? Well, Mendeleev made these huge predictions. In other words, here's his periodic table. And you see here that he had some question marks where they hadn't identified those atoms. What he did is he would predict them. And so he predicted germanium, and he called it ecosilicon. And here are all the predictions he made about the properties of this ecosilicon. And if we look at his predictions and then compare it to the actual values all the way down, you'll find that he was pretty much spot on. And that's why Mendeleev is given credit for the periodic table. Not only was he able to build it, put it together, but he also made these great predictions, and his predictions were spot on. And so that kind of lends to this next topic I wanted to talk about, which is material design. What we can do is we can take things off the periodic table. So let me grab some atoms. Let me grab some silicon and some oxygen, and so we make some silicon dioxide. And when we do that, we get a ceramic. A ceramic is going to be build up maybe stoneware or earthenware. So it's going to build up these tiles over here on the side. And so if silicon dioxide can make that, well, what about something below that? What about tin? If I were to grab that, I could say maybe those are going to form ceramics, and they will. They'll form glazes that are going to be on these ceramic tiles as well. And so what scientists can do is they can dance around the periodic table, and if you know some of these trends, you can make predictions about new materials. And so again, in summary, periodicity comes from the electron configuration, which is determined by the Aufbau principle, but what really explains it is Coulomb's law, which allows us to make these big predictions. Ionization, remember, goes up and to the right. Atomic radii increases down and to the left. Electronegativity up and to the right. And then ionic charge, remember, we find where the noble gases are, and then we look at how many electrons we have to gain or lose to get there. And then these are important in designing materials. So you should have learned to predict or justify trends in atomic properties. Where would I point you if you didn't get that? Remember looking at this chart and seeing how ionization and electronegativity change. If we were to look at justifying the arrangement based on reactivity, it all goes back to Coulomb's law. And remember, the bigger the charges are, the bigger the ionization energy, or the bigger the force holding the electrons in place is going to be. But there's also the shielding effect. And then remember, we can identify patterns to predict design. And the example of silicon and tin oxides are an example of that. So that's periodicity, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 27. It's on molecular, ionic, and net ionic equations. And so in chemistry, you should be able to observe something. So let's say watching of a Bunsen burner, figure out what are the chemicals that are combining in that reaction, write out a balanced chemical equation, and then depending on what kind of a reaction we're looking at, you may want to use a different type of equation. And so let's start with the combustion of methane. And so what comes out of a Bunsen burner is going to be methane gas. It's CH4, so 1 carbon and 4 hydrogen atoms. It's going to combine with oxygen, which is going to be 2 oxygen atoms in an oxygen molecule. And then we're going to get combustion. And so what is yielded in that reaction? We're going to make carbon dioxide and water. And so that's what this arrow stands for. Now, if you look at this, the thing that should jump out right away is I don't have enough hydrogens on the right side compared to how many I have on the left side. And so what I could do is I could add another water on the right side. I'm trying to balance it. And now when I look at it, well, I'm good on the hydrogens on either side, but now I've got too many oxygens on the right side, so I could add another oxygen molecule on the left side. Now we have a balanced chemical equation. We're just looking at the particulates here. And what does this mean? In combustion of methane, 1 mole of methane is going to combine with 2 moles of oxygen to make 1 mole of carbon dioxide and 2 moles of water. We have a balanced equation. And so in chemistry, you should be able to go from observing something, kind of writing out the particulates, going to an equation, and then starting to utilize that. And so when you have chemical change, remember what's happening is we're breaking bonds and forming new bonds. What we can do is we can write a chemical equation that represents that. It has to be balanced in order for it to be useful, especially when we're looking at stoichiometry. And so a general equation of that is going to be a molecular equation. That's the kind of chemical equation you've used your whole life. But there are 2 other equations that are important. One is a ionic, and sometimes we call it a complete ionic equation. This is most important when we're looking at ions dissolved in solution or in aqueous reactions. And then there's something called a net ionic reaction. What that allows us to do is really just look at the atoms that are important in that equation, and that'll also become important when we're looking at redox reaction. But all of these equations, we should be able to go back to that particulate and really understand what's going on in a chemical reaction. And remember, chemistry is a laboratory science, and so you should be able to observe something in the laboratory and then come up with one of these equations for it. Now, a great way to look at balancing equations is on PHET. And so what you can do is you can go there and you can actually set up balance scales of the atoms. So here we're looking at making ammonia. I can add 1 of each of these, 1 mole of each of these, and I can see that it's not balanced. On the left side, I have too many nitrogen. Now I can balance it with hydrogen. And you can see I get a smiley face because I've balanced the atoms on either side. And so remember, you can't change the molecule, but you can change the coefficient in front to balance it. Now we've got water. So I didn't have enough oxygen on the left, and now I balanced it with hydrogen on the right side. Or if we're looking at combusting methane, I add 1 of each, and then I find that I don't have enough hydrogen on the left side, so I can balance that, or on the right side, and then I can balance my oxygen out. What's fun about this is once you think you got it, you can go to a balancing game where it'll serve really different equations at you. And some are going to be really easy, some are going to be hard, and then you balance it. And when you think you got it right, then you can check it. And then if you're right, it'll give you the smiley face, and you can go on to the next one, and it's going to time you. And so it's a lot of fun. So balancing equations is important, and it's a step that you always want to do when you're looking at any equation. And so let's go back to this Bunsen burner again. So the first thing you're going to do is observe it. Next thing you're going to do is try to describe what happens. So methane is combusting in the presence of oxygen to create carbon dioxide and water vapor. We then write the reactants and the products, and that arrow stands for yields. Next thing we do is we balance it. So we can write coefficients in the front to make sure we have the right amount of atoms on either side. And then the one thing that we should also include on a nice equation is what state it's in. And so in this reaction, we have gases combining to create carbon dioxide gas and water vapor. And so now we've got a molecular equation. And now we can use it to do stoichiometry, for example, and to make measurements. But now let's go to an aqueous reaction. And so in this reaction, we're taking lead nitrate, which is clear, and we're adding it to a solution of potassium iodide, and it produces a yellow precipitate. And so what we're getting is a solid that comes out of that. And so I could observe that. I could know what those chemicals are, and then I'm going to write it out. And so we've got a solution of lead nitrate, solution of potassium iodide, and it's making a yellow precipitate of lead iodide that settles to the bottom. Next thing I want to do is I want to write out my reactants and products. Now, if you don't know how to go from the name of a chemical to its equation and vice versa, I'll put a link down here to a naming molecules or a naming compounds video that should help out. So the first thing I want to do is I want to write out all the reactants and products. So now we've got lead nitrate, potassium iodide, making lead iodide and potassium nitrate. Next thing I want to do is I want to make sure that I balance it. And so I can see right here that I don't have enough iodine on the left side, so I could add a 2 there. Now I've got too many nitrates on the left side, so now I can balance it like that. I also have to write the state that it's in. So remember, those first two were aqueous, but this lead iodide is going to be a solid. And now I've got a nice molecular equation. But again, this video is about two other equations. We've got ionic equations and then net ionic. And so how does that work? What is an ionic equation? Well, if you think about this lead nitrate right up here, it's not sitting in that solution as a connected molecule. Remember, it's going to break apart into its ions. It's going to have its lead ions and nitrate ions, and those are going to disassociate from one another. Those are going to separate from one another. And so when I'm writing out an ionic equation, what I have to do is I have to write out all the ions. And so let's do that one first. I'm going to have that lead ion, which has a 2+ charge, and then 2 of those nitrates, which have a 1- charge. Now, why am I writing a 2 here? Because we have 2 of those nitrates. And so you can see in an ionic equation, what I'm doing is I'm busting apart each of those ions. Let's go to the next one. So that potassium iodide, I'm going to break that apart into its 2 ions as well. You can see that I'm writing that this is in solution, so it's aqueous. Next, we get to the lead iodide. Now, remember that lead iodide is a solid. It's that yellow solid. And so I'm not going to bust that apart into its ions. I'm just going to write that as lead iodide as a solid. But then this potassium nitrate is going to break apart into its different ions, so I'm going to write it out like that. So I know that's a lot of work, but this is a complete ionic equation. Why is that important? It really allows us to look at what ions are in that reaction. And so if it's ever an aqueous reaction, lots of times we'll use this ionic equation. Sometimes they'll call it a complete ionic equation because it's showing all of the ions that we have present. Okay, what's the third type of equation? That's going to be the net ionic equation. So if we look back at this equation, you can see that we have 2 nitrate ions on the left side, and we also have 2 nitrate ions on the right side. And so they're really not being changed in this reaction. And so we call those spectator ions. They're really just watching. And so what you can do is you can cross out things on the left side that are also found on the right side, as long as they're in the exact same form. Can you find something else on the left side that's also on the right side? That's going to be those potassium ions. So I could cross those out as well. And so once I've crossed out all those spectator ions, I can write it out like this, and that's going to be my net ionic equation. So that's really, it's just showing what atoms are part of this chemical reaction that are actually forming these bonds. And this will become important when we're looking at redox reactions in the front. So now once you've got those equations, so this would be a molecular equation, then you should kind of be able to work back to those particulates. And so let's write out the ionic equation just using symbols, using those diagrams rather, using those molecules. And so we have lead and nitrate ions. This is what they're going to look like in solution. Remember, they're not connected. They're dissolved in the water. Next, we're going to have the potassium and the iodine. So those are going to be separated as well. This is going to be the iodine, or the big purple spheres, and the small purple spheres are going to be the potassium. And now we're going to have a reaction. What does it look like after that? Then we're going to have the nitrate and the potassium ions. Again, those are spectator. They didn't change. Then we've got the lead iodide. You can see that's that yellow solid. And so this is really what we're representing in an ionic equation. And then in a net ionic equation, what it's showing us is that we just have those lead and iodine ions that are combining together to form that lead iodide. And so that's going to be a real simple form of that. So did you learn to translate an observed chemical change into a balanced equation of the correct type? Remember, there are 3 types. Molecular is the one you're familiar with. Ionic is when we're breaking it apart to show all the different ions. Net ionic, however, is when we're just showing the atoms that are part of that chemical reaction, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 21. It's on metallic bonding. And it's important that you understand that you can't have one metallic bond. You have to have a number of atoms together sharing their electrons and therefore sharing their bonding. And so the way we look at metallic bonding is the electron sea model, where you have all of these electrons and they're shared by all the atoms. It creates a sea of electrons, and then the protons are kind of held on the inside of that. And so in metallic bonding, what we have are delocalized electrons, or electrons that have a freedom to move. And the way we visualize that is through this electron sea model. It accounts for a lot of the properties of metals, like their conductivity, malleability, ductility, low volatility. And sometimes we have to go to the shell model, however, to explain new phenomenon, and we'll get to that when we're looking at melting point. And all of that has to do with bonding. And so if we look at metallic bonding, or these shared bonds between all the metals, visualize it like this. We have the positive charges of the protons in the nucleus, and then we have electrons that are free to go. But they don't want to get too close to each other. They're going to repel each other. And so what they do is they simply drift around, and they're constantly in motion. And what you create is this sea of electrons that have a negative charge, and then the protons are going to be held on the inside of that. And that's the best way to visualize the metallic bonding. And remember, these are going to be transition metals. So these are going to be atoms that have a lot of unpaired electrons in their d orbital, and as a result, these electrons have a freedom to move. And as a result, we have all of these properties that come from metals. So number one, they're very good at conductivity. So that means conducting electricity and also conducting heat. And the reason why is that electricity, for example, is simply the flow of electrons. And so if we have free electrons, it's easy for them to flow through that metal. Likewise with heat, since those electrons and those atoms have a huge amount of freedom, we can move a lot of that energy through the material. They also are incredibly malleable, and what malleable means is that you can hit them and they're going to flatten out. And so if you're a blacksmith, you're using that property of heating up these atoms in the metallic bonds, and then as you hit it, you're able to slide them past one another. It's going to be smooth sliding. And that explains how we could get something like gold leaf, which is simply gold that we hit over and over and over again until it's razor thin. They also show ductility, and what ductility means is it's ductile, or that means that if we pull it, it's going to stretch rather than break. And so if we were to test the tensile strength of different materials, so what you do is you put them in a big vise like this, and then you simply pull on it. If something's ductile, what that means is as you pull on it, it's going to stretch out before it eventually breaks. If it's not, it's brittle, what it's going to do is simply break in half. And metals show this, and the reason they show that is that all of these atoms have freedom to move around each other. And so when you pull on it, it's going to stretch it out. They all Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 62. It's on reversible reactions. Most of the reactions we're familiar with, like the explosion of fireworks, goes from reactants to products. In other words, that gunpowder and the binder and the metals are converted into products, but it doesn't go back to being fireworks again. Or if we burn wood, we're converting that into products, carbon dioxide, water. We're releasing a lot of that energy as light and heat, but it doesn't go back to being reactants again. And so it took chemists a long time to identify the reversible reaction. It was first identified by Claude Berthollet, and what he was doing was looking at some lakes in Egypt, and he found something that normally is a reactant. He found some sodium carbonate. He knew that sodium carbonate and calcium chloride would combine to form salt and calcium carbonate, which is essentially limestone. But he didn't know that the reverse occurred. And so he found different levels of this and identified it as a reversible reaction. And we use an arrow that goes both directions to show that the reactants are being converted to products and the products back to reactants again. And so reactions can either be irreversible or reversible. In an irreversible reaction, the arrow goes from left to right, reactants become products, but in a reversible one, reactants become products, products become reactants, and it eventually hits something called an equilibrium state, where even though reactants are becoming products and products reactants, the sum amount is not changing. And so some examples I'll talk about are going to be physical. For example, when you evaporate water and then it condenses again, that's a reversible reaction. Or when you dissolve salt in water, remove the water, and it's salt again, that'd be a chemical reversible reaction. They're incredibly important in biology, so smell, for example, is a reversible reaction where molecules in the air are binding to olfactory receptors in your nose, and then they'll let go again. Or environmentally, as carbon moves from life to soil to atmosphere, that's going to be a reversible reaction as well. And so I want to start with a model. This is a PHET model. It's not a reversible reaction per se, but it shows how they work. And so on the left side, we've got some molecules. We'll call those A, and we'll color them green. And they're just going to randomly bounce around. When they move to the right side, they're going to become red, and we'll call those products. And you can see as long as the level is the same, we have about the same amount. But as I move it down on the right side, now there's more potential energy over there, and so it's moving from the left side to the right side. Now we have more products than we do reactants, but it goes both ways. Or if we move it down on the left side, now we're starting to get more reactants than products. Molecules are moving back and forth. It eventually stabilizes or it reaches an equilibrium state. And so a way to think about this, another analogy, is to think about it as a dance. Imagine that we have a dance. And the females and males before the dance are going to be like reactants, and as they choose partners, they're becoming products. But each time the song changes, they may switch to a different partner. And so as they do that, we're mixing. Reactants are becoming products, but sometimes those products are becoming reactants. And so if we label them, everybody before they started coupling up is a reactant, everybody after, it's going to be a product, but it doesn't just stay that way. It can reverse again. And so if I were to write this as an equation, we'd have our reactants on the left side, and then this double arrow means they can become products, but those products just as likely can become reactants again. Now again, let's add a real chemical reaction here. Now we've got nitrogen dioxide, which is forming this kind of a dance where it's forming together to make a product called dinitrogen tetraoxide. And so we can get the movement of this nitrogen dioxide into this product. That product can go back to becoming reactants again. So we would write the equation like this. We have simply 2 moles of this gas on the left side, 1 mole on the right side. And so let me give you some examples of this. A physical example of a reversible reaction could be evaporation of water. When we heat it up, we're breaking those hydrogen bonds and it's moving from a liquid to a gas. But if we cool it down, then we're simply going to have condensation again. So we've reversed that physical reaction. Or chemically, if we take salt and dissolve it in water, so if we add sodium chloride to water, what's going to happen to it? It's going to dissolve. And that's because the water molecules are ushering these ions of sodium and chloride away from each other. But if we remove that water, what's going to happen? We're going to precipitate that salt and it's going to come back again. In biology, it's incredibly important. So how do you smell? There are molecules out in the air, and as you smell, those move up into your nose. And at the top of your nose up here, you have this olfactory bulb. If we were to zoom into that a little bit, what happens is you have all of these modified neurons, we call those olfactory neurons, that are just waiting to receive a molecule. And as those molecules chemically bind to that olfactory sensor, you sense smell. That neural impulse is going to go to your brain and you can smell it. But if it didn't unbind, you would just have have that same smell forever. So it's important that this is a reversible reaction. Environmentally as well, where's most of the carbon on our planet? It's actually locked in the soil, but we can release that into the atmosphere through respiration, and we can move it back into living material through photosynthesis. And so carbon is incredibly important. Levels of carbon in the atmosphere are really important, but it's a reversible environmental reaction. And so did you learn to construct an explanation based on observations of different reversible processes? I hope so, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 30. It's on neutralization reactions, or we sometimes refer to these as acid-base reactions. And to really understand it, you have to understand one of the most abundant elements in the universe. 90% of atoms are actually hydrogen. Hydrogen is one proton and one electron. Remember, the proton has a positive charge, electron has a negative charge. And so if we take away that electron, what are we left with? A proton. And so you'll hear these used interchangeably. A hydrogen ion, which is going to have a positive charge, or a proton. Those mean essentially the same thing, and they're both incredibly important when we're talking about neutralization reactions. And so water is amphoteric, and what that means is it can either act as an acid or a base. And more specifically, it can act as a Bronsted-Lowry acid or a Bronsted-Lowry base. What does that mean? Well, a Bronsted-Lowry acid is going to donate a proton to a base. In other words, the acid always donates the proton to the base. And this is the best definition for what an acid and a base is. And so when this proton is transferred, we call that a neutralization reaction. And so this only occurs in aqueous reactions, and we also have to be able to identify what's the acid, what's the base. In other words, what is this conjugate acid-base pair? And also using this definition, you should be able to figure out the strength of acids and bases, or at least what that strength means. And so water is really interesting on a number of different levels, but one of the reasons it's interesting is if you have enough water around water, it'll actually start to transfer protons. In other words, there's going to be a negative charge here and a positive charge on the proton. So sometimes one of those protons will actually move over. And so what you create is hydronium ion, which has a positive charge, and hydroxyl ion, which is going to have a negative. And so using the Bronsted-Lowry definition of what an acid and a base is, what we're doing is we're taking the acid in this case and the base, and we're transferring a proton from the acid to the base. And so that's how we define what an acid or a base is. And what's interesting about water is it can serve both as an acid and a base. So where does this definition come from? Well, there were two scientists, Bronsted in Denmark and Lowry in England, and they both kind of identified this at the same time. So they give them both credit when they named it. And so what you're doing is you're taking an acid and a base and you're transferring that proton from the acid to the base. And so another way to write it would be the acid, which has the proton, and then we're transferring that proton, in this case, to the base. And so we're taking an acid and a base, combining those together. This is called neutralization, and we're making a conjugate base and a conjugate acid. Now this is a reversible reaction. In other words, it can run in both directions, and that's why we have the arrow pointing both ways. And so an example of this could be acetic acid with water. And so if we have acetic acid and water, what we can do is we can actually take that proton from the acetic acid, and then we can donate it to the water itself. In this case, then, acetic acid is the acid, and water would be the base. And so what's interesting about water is it can serve as both an acid and a base. And so take a moment for just a second and figure out, is water an acid here or a base? Is it an acid here or is it a base? And so you have to go back to that definition. All we say an acid is something that's donating a proton, and all we say a base is something that's receiving it. And so in this first reaction, we're taking hydrochloric acid and water. Have you figured out which one it is? Well, the acid is going to be the hydrochloric acid. The base is going to be the water. The water is receiving that proton, and so it's the base. And so what we're doing is we're losing that proton from the hydrochloric acid, and that's making a conjugate base, chloride. and we're gaining that electron, or excuse me, gaining that proton in the water, and we're making a conjugate acid. So if we look down here, we've got ammonia and water. In this case, the water's serving as an acid because it's donating the proton, and who's receiving it is going to be the ammonia. And so that's creating a conjugate acid and a conjugate base. And so when we're talking about strong acids or strong bases, what does that really mean? Well, let's look at something that's completely strong. That's hydrochloric acid. And so if we add hydrochloric acid to water, it's going to completely break apart. In other words, all the protons are going to break apart. All the chlorine ions are going to break apart. And so we call this a strong acid because the arrow you can see is all running in one direction. Now this proton doesn't just float around, it's going to quickly combine with water to make hydronium. You don't just have free protons inside there. But this would be a strong acid. If we look at something that's a medium acid, that would be acetic acid. So we're going to be transferring protons to the water, but we're also going to be moving those back to the acid itself. So this would be arrow in both directions. Or if we were to look at bicarbonate down here, bicarbonate, it's going to be more of that accepting of the proton, and so we call that a real weak acid. But we could also add the arrow on the other side. And so as we increase the strength of an acid, we're clearly decreasing the strength of a base and vice versa. And so that's the Bronsted-Lowry model of what an acid and a base is and how we can figure it out in a neutralization reaction. And so did you learn the following to identify what's the acid, what's the base, and figure out these pairs? Well, remember, just look for where the proton is going, where it's headed to, and that's going to tell you what's the acid, what's the base, and I hope that was helpful. Hi, it's Paul Anderson, and this is Chemistry Essentials video 007. And it's on the quantum mechanical model. In other words, it's going to be our current model of what an atom looks like. Before we had this quantum mechanical model, we had what was called a shell diagram. And so when you look at neon had 2 electrons in the first shell, and then it would have 8 electrons in the next shell. And we figured that out by looking at spectral data. And so what we've discovered since then is uncertainty in those electrons and a little bit more of the characteristics of electrons. And so this has kind of been replaced with the quantum mechanical model. Now the shell model works great at making predictions, and so does the quantum mechanical model. They're just different theoretical concepts of what an atom looks like. And so our shell model really is based on Coulomb's law, which talks about the interactions between protons and electrons. But there's a couple of things about electrons that we discovered. One was the uncertainty principle. In other words, when you're looking at an electron, the act of light bouncing off of that and coming back to you changes the momentum of the electron. So you can never know both the location and the momentum of an electron. There's uncertainty there, and so they live in these clouds of probability. And so since they don't follow specific orbits, we came up with this new term, which is an orbital, which is where they're going to spend their time. Another important thing about electrons is that they have spin. So they're going to either have a clockwise magnetic spin or a counterclockwise magnetic spin. And as a result of that, you can only have 2 in every orbital. And so we really had to throw out this idea of the shell, or at least modify it so it fit with the data. And so now we have this quantum mechanical model, and we can use complex equations and computers to develop software that predicts how atoms are really going to interact. So Coulomb's law, remember, predicted where electrons are going to be. You have these positive charges on the inside, and you have these negative charges of the electrons. And so the larger these charges get, the larger the force holding them together is going to be. But as they move away, as the radius increases, we're going to decrease that force. But there's 2 problems with that general shell model. Number one, they don't flow in these specific orbits, and that's because of Heisenberg's uncertainty principle. And then the other one is that spin means we can only have 2 electrons in every orbital. And so this idea of 8 in one shell is just not going to work. And so there are these orbitals. And if we start on the inside, the first one's going to be called the s orbital. And then we move to these things, which are polar. And so we call those the p orbitals. They don't come from polar, but that's how I remember it. Then we move into the d orbitals, and then we move into the f orbitals. I don't know if I have those, but essentially they're all of these clouds of probability where electrons sit. And so we have what are called quantum numbers, and the first 3 are going to determine what that orbital looks like. So the first one is going to be n, and that's going to be the size of the orbital. As n gets larger, then that area of which those electrons are going to be is going to get larger. We next have L, which is going to be the shape of that orbital. It could be an S, a P, a D, or an F. Then we move into the orientation, which is going to be M sub L. And so S can only have one orientation. P can have three orientations. And so it just goes 1, 3, 5, 7. And so when we're adding in the orbital diagram, as we're adding electrons to it, we're going to put a lot more electrons in the orbitals of the F subgroup than we are of, for example, the P. And then there's going to be the spin. And since those electrons have spin, it's counterclockwise or clockwise, we can only put 2 in every orbital. And so what we can do is we can develop Schrodinger's equation is an example of that, that's going to predict where these electrons are found. And by doing that, we can predict not only what an atom looks like, but how atoms are going to interact. And it's so complex that lots of times we need computers to do the math. And so did you learn how the quantum mechanical model can refine the classical shell model? Well, I would point you to these two things, uncertainty of the electrons and the spin. And it's not like we throw out the shell model, it's just that we're getting better and better models of what an atom looks like based on the data that we're getting. We'll talk about that in the next video, but I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 43. It's on reaction intermediates. One of the most important chemical reactions inside our cells is glycolysis, where we break a 6-carbon glucose molecule down into 2 3-carbon pyruvates. Where does that occur? Right outside the mitochondria, right outside here. But it doesn't occur in one step. In other words, there are lots of elementary steps along the way, and therefore lots of reaction intermediates along the way as well. We break that glucose into glucose 6-phosphate, fructose 6-phosphate, and so what we're doing is adding energy, releasing energy all along the way. But lots of times all we see is that initial reactant and then the final product, which is going to be all the way over here as our pyruvate. And so essentially in an overall chemical reaction, we're going from reactants to products, but it's not just in one step, it's elementary step after step. And finally we have this whole reaction mechanism. And so what do we call the things between the products and the reactants? The things that appear but then disappear, those are going to be the intermediates. And we can't necessarily see those, and so we have to figure those out through experimentation. And when I was coming up with a good analogy for this, the best one I could come up with is how a caterpillar becomes a butterfly. We get to see what goes in, we get to see the caterpillar, we get to see what emerges, but we don't really get to see what's going on. In other words, the formation of that chrysalis, we don't get to see, and all that metamorphosis going on, we don't get to see that. And so chemical reactions are essentially the same way. And so we have to use experimentation to figure out what's going on. And so let's look at an actual chemical reaction. So here's our chemical reaction here. That's our overall chemical reaction, but it's going to be made of 2 steps. And so we've got step 1 and step 2, and all of those together is going to be that overall equation. But if you look here, a good way to figure out what are going to be the intermediates is to just start canceling things out that aren't in our final equation. So if we look at this is overall equation, let's just go up here and start crossing out things that show up here. And so this is going to be one thing. So we see nitrogen dioxide. What else do we have? We have this carbon monoxide. So I'm going to go onto the reactant side and cross that out. We've also got this nitrogen monoxide. I'll cross that out. And then we've got one more to cross out, and we're going to cross it out like that. And so what we find is there's a lot of stuff in those elementary steps that don't necessarily show up in that overall reaction. And so if we were to write those, we find that some of those are in our initial reaction. So an example could be this nitrogen dioxide that's going to be right here. But we're also finding these things that just show up for a little bit and then disappear. We call those reaction intermediates. And so how do we figure all these out? Well, that's what a lot of chemistry is. It's figuring out through experimentation what all of these intermediates are. And so this whole pathway I talked about with glycolysis is called the EMP pathway. Where does it get its name? It gets its name from the 3 scientists that figured this out over years and years of study. And so again, did you learn that experimentation can be used to determine the presence of reaction intermediates, things that we don't necessarily see? They're not reactants, they're not products. If you did, then you learned what I wanted you to, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 70. It's on solubility. You've probably noticed that if we add salt to water, it will dissolve. But if we add more salt and more salt and more salt, eventually it doesn't dissolve anymore. And so what's going on? Well, if we look down at the atomic level, we're adding a salt grain, and that's made up of all these ionic bonds, sodium and chloride, and they're going to break apart into their aqueous ions. They're going to be ushered away by the water. That's going to increase the concentration of those ions in solution. And so if we increase the amount of ions, eventually no more ions can be added. And so that's going to push it back to this more solid form of salt. And so if we look at a solution, remember, we're dissolving a solute in a solvent. And so you can think of that solute as a solid if it's all chemically bonded together. And if we can break it apart into its ions, then it's dissolved in solution. And so if we think of on the left side of our equation, we have the solid form, and on the right side, we have it broken apart into its ions. And so really in a solution, we have a reversible reaction. It's going to have its own equilibrium constant, and we'll call that KSP, which is essentially the solubility product constant. And that's a way to measure the solubility of any kind of a salt. And so there are a few things that are going to affect the solubility. One of the big ones is going to be delta G. In other words, it's going to be the enthalpy, it's going to be the entropy of the system. Let's say that there are really intense bonds between these in the solid form. It's going to be hard for those to break apart into their ions. Likewise, as we change what is in the solvent, if we add more ions to it, it's harder for more ions to be added. We could also change the pH, and that's going to affect what can be dissolved as well. Now, there are a few things that dissolve readily in water that you should simply know. Those are going to be the ammonium ions, potassium ions, sodium ions, and then also the nitrate anion as well. And so if we look at sodium chloride breaking down in water as a reversible reaction, on the left side we're going to have the solid form, on the right side we're going to have the two ions that are in aqueous environment. Remember, we're breaking those apart. A wonderful simulation to look at this is the PHET on salts and solubility. And so I'll put a link down below, but basically I'm going to add a little bit of salt, and we're going to look at this at the atomic level. And so what's going to happen is the water's ushering those ions away. And so we're going to break it apart into its cation and its anion. Let's say I radically increase the number of ions. What's going to happen? Well, you can see that most of them are going to be in solution, but some are going to go back to that solid form. There's simply too many ions out there. And so we've pushed it more towards the right side of this reversible reaction. Now let's look at a different salt. So now we've got silver bromide. If I were to add 200 of the cations to this, we're going to see a different kind of an effect. What's happening is that they're all going back to that solid form. So if we were to look at this equation up here, it's shifting it back more towards the left. And so how do we measure, does a reaction go to the right or does it go to the left? Remember, that's going to be our equilibrium constant. And so if we look at the equilibrium constant of sodium chloride being dissolved in water, we could set it up like this, where it's going to be the concentration, remember, of the two products over the concentration of that reactant. Now we can get rid of that reactant since it's a solid, so our KSP value is going to be 37.3. What does that mean? Since it's much greater than 1, that's going to shift it way towards the right. We're going to have way more of those ions. If we compare that to the silver bromide, what's our KSP value here? It's going to be much less than 1. What does that mean? Our equation is going to be shifted way towards the left, and so we're going to have more of that solid form. And so the neat thing about this simulation is you can play around with the KSP values. Now I've got a theoretical salt with cations and anions, and I'm simply going to lower the KSP value. You can see as I lower it, it's starting to move back more towards the left. It's moving back more towards that solid form. So if you have a really low KSP value, it's going to be shifted towards the left. If I radically increase KSP, then it goes way back more towards the right, or in aqueous solution. And so that's what KSP affects, but you should be thinking, like, why does it affect that? What affects KSP? Well, it's mostly going to be delta G, so changes in enthalpy and changes in entropy. And so if we were to look at the solid form, remember there are going to be ionic bonds between all of these, and the greater those bonds are, it's harder to break them apart and then move it away into solution. And so also there are going to be interactions. Once it does get broken away, it's going to interact with the solvent itself. And let's say there are already a lot of ions in solution, it's harder to be added. And we could also change, for example, the pH of that solution increase or decrease the number of protons, and that's also going to change how it interacts with the solvent. Now, we basically just talked about enthalpy. Remember, entropy is going to be an important part of this as well, and that's why it's better to look at the whole delta G. And so what are some applications of this? Well, let's say we have seawater and fresh water, and we're going to try to dissolve salts in each of those. It's going to be different because in seawater, we're going to have all of these ions already present. Sodium, chloride, sulfate, magnesium, all of these are already there, and so it's hard for us to add more of those salts into solution. What's another application of this? Acid mine drainage. So how did this get so nasty? Well, there was probably a coal mine at some point that had a lot of sulfur in it, which combined with water and made sulfuric acid. And as it drained through this area, that decreased the pH, and so there's all of a sudden a lot of ions in solution, mostly iron hydroxide. What happens as it's now settled out is we're adding more fresh water to it. It's increasing the pH at this point. We can't hold those in solution, and now all of these ions, all this nasty iron is coming out of solution. Or we could look at acid rain. What's happening there is we're decreasing the pH, and that changes the amount of carbonate that we can actually dissolve. And so did you learn to predict the solubility of a salt or rank its solubility given the KSP values? Remember, the lower it is, the more likely it's be in the solid form or shifted more towards the left. The greater it is, the more it's shifting towards the right. Also, could you interpret data based on a KSP value? How is that going to behave? And then finally, can you look at what's going on inside the solid and inside the ions in relation to the solvent to predict our KSP values? I hope so, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 24. It's on metallic solids, like this big gold nugget that was found. And so it's shiny, conducts electricity. We've always been fascinated with metals, and we also can bend metals to our will. In other words, we can mix gold with silver, and we get something called electrum. And today we can mix gold with things like nickel, magnesium, palladium, and we can get white gold. And so we can form these alloys of metals. And so metallic solids are built on this electron C model, where all those electrons are free, able to move around, and that gives them lots of different properties. They're shiny, good conductors, they're ductile, they're malleable, and they can form these alloys. And that's all built on this idea that the electrons are free to move about. They also can form alloys. The alloys that they form still are going to show that electron C model, and so they're still going to have those same properties. The alloys can be broken down into interstitial alloys when we're actually filling holes in the middle itself with smaller atoms, or they could be substitutional. Substitutional is when we're going to replace one of the atoms in the metal with a different atom. An example could be brass. And so the chemistry of alloys can sometimes differ. And so when we were making stainless steel, for example, we can make steel that doesn't rust because of the different atoms that we're adding. And so remember, in metallic bonding, we shouldn't talk about just one metallic bond. And that's because all of these electrons are moving around, these free electrons. And as they do, they push on each other and they create this sea of electrons. And then the protons, the nuclei, are on the inside of that. Now they can still move around, and it gives them those cool properties. Number one, they're shiny. Why are metals shiny? It's because they have all these free electrons on their surface, and so as light hits it, it's able to absorb some of that and reflect a lot of that light. If we're looking at their conduction, they can conduct both electricity and heat, and the reason why is that they have high amounts of these free electrons, and the atoms have a certain amount of ability to move. They're ductile. When you pull them, they're going to stretch out like this. They're not going to break. They're not brittle. They also are malleable. We can hit them and we can smooth them out. And the reason why is you can think of it almost like one big atom with all these positive charges on the inside and electrons holding them where they are. And so these protons have the ability to move, or these nuclei have the ability to move, and also they can form alloys, and we've known this for years, that we can heat different metals and we can get different characteristics from that. And so electrum, remember, is an example of mixing gold with silver, but we can break these alloys into basically two different parts. We can have what are called interstitial alloys. Interstitial alloys, a great example would be steel. What we're doing when we're heating it up is we're allowing carbon to fill the holes inside that iron. And what it does is increase the density, and it's going to make it a better metal. Another type of metal are going to be substitutional alloys. Substitutional alloys is when we're taking in atoms that are about the same size. So if we take copper and we add zinc to it, then we can make brass. It's going to have different characteristics than those metals by themselves. Stainless steel is formed the same kind of a way. If we take stainless steel and we add atoms to it, we get a metal that looks like that. What type is that? Well, it's a combination. It's interstitial because we're going to have this carbon, but it's also going to be substitutional because we have chromium and nickel. And what that's going to do is allow it to not interact with oxygen. It's not going to allow it to rust, and so we can create a steel that doesn't rust as much over time. Did you learn to compare the properties and constituent elements in an alloy? Those atoms could either fit on the inside, interstitial alloys, or it could be substitutional. And then going back to metals, do you understand this whole electron model and how we can use that to predict the different properties of metals? Well, if you do, then you understand metallic solids, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 31. It's on redox reactions. And the word redox is a combination of both reduction and oxidation. And so these are reactions where we're actually transferring high energy electrons to more low energy electrons. And so that's providing us with energy. And so when you're burning gasoline, that is a redox reaction. Likewise, inside our body, cellular respiration, when we break down our food and get energy from it, is also a redox reaction. And so the first thing you should understand that in a redox reaction, we have two parts to it. We've got reduction and oxidation. Now the oxidation portion is going to be the losing of high energy electrons, and the reduction is going to be the gaining of those electrons. But when you're looking at a chemical equation, we don't put electrons in the equation, so oftentimes it's hard to figure out where these electrons are actually going. And so we use something called oxidation numbers to figure out where the electrons are going. We can then break it down into what are called half reactions that show the electrons, and then we can finally combine that back into a balanced chemical equation. Now these are important in the chemistry lab because we can use them as a different type of titration. We call that a redox titration. And again, these are really important because they allow us to produce energy, not only the energy that drives your car, but the energy that drives you. And so in a redox reaction, we're moving high energy electrons from the oxidized substance to the reduced substance. And it's really common to get these two terms messed up. And so the mnemonic that I use is called oil rig. And what does that mean? Well, the O in oil rig stands for oxidation, and oxidation is losing electrons. So what is reduction? The R stands for reduction is gaining electrons. And so just like you maybe learned SOHCAHTOA in your geometry class, you should learn oil rig in your chemistry class. It's a good way to remember where the electrons are flowing. And so let me give you a real simple example of a redox reaction. Let's say we have hydrogen gas and fluorine gas, and they combine together to create hydrogen fluoride. That would be a redox reaction. And so did you see what was being oxidized? So where were the electrons being lost from? It was from the hydrogen. And so we would say in this redox reaction of hydrogen plus fluorine to make hydrogen fluoride, the hydrogen is being oxidized and the fluorine is being reduced. It's gaining these high energy electrons. And so we could write this out as half reactions. In other words, we've got the hydrogen making hydrogen ions plus these electrons that it is losing. And then we have the fluorine, which is gaining those electrons. And so this would be the oxidation portion of the redox, and this should be the reduction portion of that. But you should have been watching carefully. How did I decide that the hydrogen was losing the electrons and the fluorine was gaining the electrons? And so how would you figure that out? Well, we use something called oxidation numbers to figure out where they're going. And there's some simple rules that allow you to allow you to figure out the oxidation numbers. One thing you should know is that when writing the charge, let's say a charge of a -2 charge, a charge generally we write the number first, 2, and then we would write the minus. But when you're writing oxidation numbers, you're going to write either the plus or the minus before the number. And so the first rule is really, really simple. If we ever have elements that are free or free elements, the oxidation number is always going to be 0. So if we have hydrogen gas by itself, what's going to be our oxidation number? It's simply going to be 0. Let's say we have magnesium solid. What's going to be the oxidation number of the magnesium? It's going to be 0. Let's say we have sulfur, remember, which will form into these big 8 atom molecules. What's going to be the oxidation number? Again, it's going to be 0. So rule number is really simple. If they're by themselves, it's always going to be 0. If we've got ions, then it's going to match the charge. And so if we're looking at sodium chloride, you can see this is an aqueous solution. What's going to be the charge? Well, the sodium is an alkali metal, so it's going to have a +1 charge. And the chlorine is a halogen, so it's going to be a -1 charge. And so those are going to match. One thing you'll start to notice is that these are going to add up to 0. Let's say we're looking at potassium. What's going to be the charge? It's going to be +1. Let's say we look at magnesium chloride. Well, the chlorine is going to have a -1 charge. And since we have 2 of those, what's my magnesium charge going to be? It's going to be a +2. All right, let's move to the next one. These deal with oxygen and hydrogen. Oxygen is always going to be a -2 oxidation state, unless it's in a peroxide, and it'd be a -1. And hydrogen is always going to be a +1 charge if it's bonded with a nonmetal, and it's going to be a minus charge if it's bonded with a metal. Last thing that I mentioned this just a second ago, that in a neutral compound, all of them are going to sum up to 0. But if it was an ion, they'd sum up to the charge of the ion. So let's start applying that. If we look at water right here, what's going to be the charge of the hydrogen? It's going to be +1. And we could see that in a couple of ways. Number one, since it's bonded to a nonmetal, it's going to be +1. What's going to be the charge of the oxygen? It's going to be -2. And since we have 2 of these, they're going to sum up to 0. Let's look at this next one. How do we work through this? Well, if we look at the sodium, it's going to be a +1 charge. Again, that's going to be in the first column of the periodic table. Where could we go next? Let's look at the oxygen. The oxygen, remember, is always going to be a -2. So we could write that in as a -2. Okay, so what's our charge at this point? We got 2 of these sodium, so we're at +2 on this left side. Our oxygen, since it's -2 and we have 3 of those, it's going to be 6 minus or -6 on the right side. So what is the sulfur going to be? It has to be +4 because we're going to sum up to 0. Let's look at this ion over here. And this ion here, let's just label what the oxygen is going to be. The oxygen is going to be -2. We know that oxygen's always -2. And so what's going to be the sulfur in this case? Well, since this is -2 and we have 4 of them, that'd be -8. Since the ion has a charge of 2-, we know that the sulfur has to be +6. And so you can see that the sulfur is actually going to change depending on what compound it's in. So do you think you have those rules? I know it seems complex, but it's really powerful when we're looking at redox reactions. So let's look at a redox reaction. Let's say we take some magnesium solid and we just put it in hydrochloric acid. What's going to happen? Well, you're going to start to see bubbles show up. And so those bubbles are going to be hydrogen gas. And this is a redox reaction. And so we're producing hydrogen gas on the right side of the equation. And so what we can do is we can go through this reaction and we can start writing down the oxidation numbers. And so let's start with the magnesium. Magnesium is all by itself, so what's its charge going to be? It's going to be 0. Now if we look at the hydrochloric acid, we could start with the chlorine ion since it's an aqueous solution. And so that's going to be a -1. What's our hydrogen going to be? It's going to be a +1. So now we got our oxidation states here. Let's go over to magnesium chloride. So this is also an aqueous solution. So we could start with the chloride. That's going to be -1. Since we have 2 of those, what's our magnesium going to be? It has to be +2. Now let's go over to hydrogen on this side. Hydrogen on this side is simply going to be 0 because it's all by itself. Okay, so now what we can see is if we look through chlorine, for example, on the left side is -1, on the right side is -1. And so that's neither going to be oxidized or reduced. But if we look at magnesium here, it has an oxidation state of 0 on the left side. What is it on the right side? +2. So since it's gotten more positive, it's lost 2 electrons. And so if you're losing electrons, what is that? That is simply oxidation. So magnesium is being oxidized. In other words, it's losing 2 electrons. Where did those electrons go? Well, let's look at hydrogen. It's +1 on the left side, and it's 0 on the right side. And so since it's gone down in value, that means that it's gained electrons. But you might say, well, it's gained 1 electron. But again, you could look at the coefficient out here. Since there's 2 of these, we've actually gained 2 electrons. And so that would be the reduction portion of this equation. So now we could write the half equations for this redox reaction. The first one's going to be the oxidation. We have magnesium as a solid, and it's losing those 2 electrons. And then if we look at the hydrogen, the reduction portion is going to be this. The hydrochloric acid is being reduced. In other words, it's gaining those electrons that are lost from the magnesium itself. And so let me give you a practice problem. Right here we've got manganese plus lead nitrate is going to make manganese nitrate plus lead solid. And so what you should do is write out the equation, figure out the oxidation numbers of all the atoms in this equation, then figure out what is being oxidized and what is being reduced, and then try to write out those half reactions. And if you think you have it right, you could try to post some of your answers in the comments down below. And so what are some applications of this? The first one would be titrations. Remember, titrations are always used in stoichiometry. We're trying to figure the amount of an unknown. And so a great example of a redox titration would be the Winkler method. And the Winkler method is used to figure out how much oxygen is in water. And in biology, that's really important. The amount of oxygen in water tells us how healthy the water is. In other words, what organisms can live in the water, how much of that oxygen is dissolved and they can actually use. And so what you can do is a series of reactions. So a series of reactions where we're converting that oxygen into a precipitate, manganese hydroxide. We then convert it into iodine, and then we can use thiosulfate to actually do a titration. And what we're doing is we're reducing the iodine. And so remember, in a typical acid-base titration, what we're doing is changing the pH. Here, what we're doing is changing or doing a redox reaction when we're actually transferring electrons. And we use starch in this as well. And when we get a change in those electrons, what we get is a color change. And so we can figure out the amount of the iodine, and then we can work backwards to figure out the amount of oxygen. What would not be another application of redox? Remember, it's in energy production. And so this big molecule right here is going to be a triglyceride. That's a fat. That's going to be the fat that you find in your food. It has a high amount of energy because there's going to be energy in the electrons of the hydrogen around the carbon. But if we were to look at something like this is isooctane that's going to be found in gasoline. It also has a high amount of energy, and that energy is going to be found in the hydrogen atoms that are around the carbon. And so what happens in a redox reaction is we can actually transfer those electrons to oxygen, and we can release energy in that transfer. And so did you learn the following? Could you identify what's the oxidized substance and what's the reduced substance? Remember, the oxidized substance is the one that's losing the electrons, and the reduced substance is gaining it. And then finally, do you have some kind of an application? A great example would be a titration, like the Winkler method we said in determining the amount of oxygen. That's redox reactions, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 13, which is on solids and liquids. And we have solids and liquids right here, water in a both liquid and solid phase. And so when we're looking at solids and liquids, it's almost easier to compare them. So we're going to use a Venn diagram. So we've got solids and liquids. How are they alike? Well, they're both made of matter. They both have a specific molar volume. In other words, they're close enough where their molar volumes are going to be about the same. And they're all going to be made of particles. So is all matter. But what's different between liquids and solids is the intermolecular forces are going to be slightly different between a solid and a liquid. And so if we look at solids, they're going to be highly ordered. And what that means is that their atoms are going to be locked into a specific matrix. They can vibrate. In fact, they have to vibrate over time. But as a result, they really are two different types, amorphous and crystalline solids. If we're looking at liquids, they're more disordered, and they can show what's called translation, where they can move around each other. And as a result, they're going to be take the shape of whatever container they're in. And then there are going to be properties based on these intermolecular forces like surface tension, viscosity, and volume of mixing that we talk about with liquids that we don't have to talk about when we're talking about solids. And so how do we look at these two and how they move from one into another? Well, we can look at a heating curve, or if you just turn that around, a cooling curve, and it's going to show us this transition between the two. And so if we're looking at phases of matter, it's first best to come up with some kind of a representation of what they look like. And so we're going to use a simulation here from PHET at Colorado EDU. And so what we've got here is a bunch of water in a solid phase. And so you can see that they're locked in position, and as we move it to liquid, Now they can translate, they can move around each other. Now this is not a great model of a liquid, it should kind of flow down to the bottom, but at least we're seeing what's going on at the particle phase. And then as we look at a gas, as we increase the energy again, now they're moving all over the place. And we'll talk about gases in the next video. And so what we're going to do is we're going to take some of that energy away. We're going to take some of that heat away. And as we cool it down, you can see here that we're measuring this in Kelvin. As we cool it down, it turns into a liquid, and now it's into a solid. You can see even at a solid phase, though still we're seeing vibrations within there. But as we approach absolute zero, all molecular motion is eventually going to come to a stop when we reach that point. Okay, so when we're looking at solids, solids are going to have a specific matrix. In other words, all of the atoms, molecules are going to be put together in a specific shape. If it's amorphous, there's not going to be a repeating pattern to this. And so this is amorphous right here. So you can see it's made of silicon and oxygen, but they're going to be put together in all different shapes. And as a result, we get what's called amorphous quartz, or sometimes we call this glassy quartz. And so it's going to be really brittle, really easy to break. And so some solids like rubber, for example, is going to be an amorphous solid. Doesn't mean that it's not a solid, it's just not going to be as organized. And if we look at crystalline structure, like that in this crystalline quartz, it's going to be the same atoms you can see, but they're arranged in a repeating pattern, and now we get these beautiful crystals right here. It's going to be harder, so a diamond, for example, is going to be something that would be in a crystalline solid. As we move into liquids, what they can show is something called translation. So that means that, let's say we have these water molecules right here, they're not locked in those positions. In other words, they can translate about each other. And as a result, liquids are going to take the shape of their container. Now, depending on the forces between those water molecules, we're going to have different properties. One of the first ones is going to be viscosity. Viscosity is how easily a liquid is able to flow. And so right here, we've got a picture of pitch. Pitch is going to have really high viscosity. That means it really is going to flow at a real slow rate. It's still going to take the shape of the container you can see down here. And so something that would have, for example, a real low viscosity might be water. It's going to easily flow. Alcohol might be one that has a low viscosity. Another property is going to be surface tension. Surface tension is going to be based on the intermolecular forces in a liquid. And so these different molecules are going to be attracted to one another, and they're also going to be attracted to one another at the surface. And so surface tension is going to be almost this layer of chemical attraction over the surface of a liquid. And so a water strider like this is able to float on top of that surface tension. If we were to break the surface tension, one way to do that would be to add something like soap. It's going to break those intermolecular forces, and trust me, that water strider is going to quickly sink to the bottom of the lake. And then the last thing is called the volume of mixing, and this is it's best easily understood if we use a demonstration. This is one that I use in my class. Imagine I were to take some pure water, so we have distilled water, and I were to put it in a graduated cylinder, and I were to be real precise and measure out exactly 250 milliliters of water. I were then to take some ethyl alcohol, so ethanol, and I were to measure out exactly 250 milliliters of that as well. So let's say I'm very precise, I have 250 mils of each. What do you think is going to happen if we combine those two amounts together in another graduated cylinder? Well, when you do this, if you have a large enough amount, you're not going to get 500 milliliters. And so that's weird. It seems like it disappeared, but really what's going on is the water and the alcohol are able to fit within each other. There's going to be room within there. And so that's based on those intermolecular forces as well. If we were to combine water and water, we get 500 mils, but because we have less attraction in those alcohol molecules, the water molecules can kind of get in there. And so how do we look at that transition from solid to liquid and back again? We use something called a heating curve. And so what we have down here is heat. So we're adding heat in this direction. And then we've got the temperature on the side. And the heating curve I'm going to show you is the heating curve for water. And so if we look at the heating curve for water, it's going to look something like that. And so what happens below 0 degrees Celsius? Well, that's going to be a solid. It's going to be ice. What happens as we go above it? It's going to turn into water. And then above 100 degrees Celsius, it's going to turn into vapor. But why is it a flat line here? It seems like we're just losing energy. In other words, we're adding energy the whole way across. Why isn't the temperature increasing here? Well, what's happening is as we add energy to ice, as we reach that point, what we have right here is both ice and water. So we see a transition from a solid to a liquid. And so that energy is going into that molecular motion of that solid becoming a liquid. Likewise, where's the energy going here? It's going into the energy of those vapor molecules as they jump off. And so as you heat water, it's going to increase to around 100 degrees Celsius depending on your elevation, but at that point it eventually jumps into a vapor. And so we could look at a heating curve to see the transition between both solid and liquid, and then our next video, which is going to be on gases, if we flip this thing around, then we've got just a cooling curve. And then, did you learn this, that we can use a particulate model? And so we use that model, that PHET model, to explain the difference between solid and liquid. Remember, that big point is when we move to a liquid, they show translation. They can move around each other, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 29. It's on synthesis and decomposition reactions. If I were to ask you which of the two reactions you see on the left is a decomposition reaction, the tendency is to choose the rusting railroad car. And the reason why is it looks like it's breaking down. But if you think about it, what is rust? Rust is a combination of iron and oxygen, and so this is actually a synthesis reaction. And so if we ever take atoms and molecules and combine them together to make a new compound, then we've got a synthesis reaction. So what's an example of a decomposition? The breakdown of water into oxygen and hydrogen gas is going to be an example of that. And so if we take atoms or molecules and we combine them together to form a new compound, we call that a synthesis reaction. We're making something. Likewise, if we take a compound and break it down into atoms or molecules, we call that a decomposition reaction. Lots of times that'll generate a little bit of heat. And we can use both of these reactions in the chemistry lab to do simple stoichiometry and practice our lab techniques. And so synthesis reaction are when we're taking atoms and molecules and combining them together. So let me give you a couple of examples. Let's say we take magnesium, get it a little bit hot, and then allow it to combine with oxygen. It's going to make magnesium oxide. And so when it's done, you're going to have a new solid that's creating. We're taking a solid and a gas, and we're making a new solid out of it. Another example of a synthesis reaction could be the carbonation of water. And so this is me adding a little bit of carbon dioxide to my soda stream at home. And what's going to happen inside there is that the carbon dioxide is going to combine with the water and it's going to make carbonic acid. So that carbonic acid is going to lower the pH to around 4 and it's going to change the taste of that carbonated beverage. What's decomposition then? It's when we're taking a compound and breaking it down. So here's an example. If we take sodium azide and break it down into sodium metal and nitrogen gas, that'd be a decomposition reaction. So if we have one reactant and two products, it's a good idea that this is probably a decomposition reaction. Where's an example of this actual reaction? Well, this was used in early airbags. And so what you can do is you can put some sodium azide inside the bag right here. It's totally stable, but if you add a little bit of heat to it, so there's an igniter inside there, it's going to quickly break into sodium and nitrogen gas. And that nitrogen gas is going to fill up the bag really quickly. Now you could imagine a bunch of nitrogen in there is not a good thing. That's highly reactive as well. And so they also put chemicals in here that react with the sodium. Another example could be right here. I'm taking hydrogen peroxide and then I'm simply adding a catalyst to it. I'm adding an enzyme that's found in yeast. And so the yeast isn't part of the chemical reaction. It just serves as a catalyst. And so what I can do is I can add hydrogen peroxide to it, seal it up, and I can give it a little bit of a shake. And what it's going to do is it's going to break down into water, and then it's going to break down into oxygen. And that oxygen is going to fill up the bag. Now, if you feel the bottom of the bag, it's going to get warmer and warmer. And the reason why is that we're releasing energy as we break those bonds and form new bonds to the point where it can eventually explode. And so sometimes you have to let a little bit of that gas go. Scared me. So did you learn the difference between a synthesis and a decomposition reaction? Hopefully. In this one, when we're burning magnesium or combining it with oxygen, that's going to be a synthesis reaction. And could you do simple stoichiometry on that? Well, one way to do it would be to weigh the magnesium to start. We could put it in a crucible, heat it up, and then we could weigh it when it's done. We could figure out the mass of the products and we could work backwards to figure out how much oxygen is actually being added, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 28. It's on stoichiometry, which is really just measuring atoms. In other words, in a reaction, we're measuring the atoms we have before the reaction and after. And because of the conservation of mass, we have to make sure those are the same. And so it's a really powerful tool. Chemistry teachers love stoichiometry, and students not so much. And so let's think of it as musical chairs. As you're playing musical chairs, you're walking around the circle. And so you're kind of bonded to the floor, but when the music stops, you have to quickly find a chair. And when you do that, it's like a chemical reaction. You're breaking your bonds with the floor, forming new bonds with that chair. And if there's not enough chairs, then you're kind of out. In other words, chairs could be the limiting reactant in this reaction. And so sometimes we don't have enough chairs, and sometimes we don't have enough people. And so reactions are going to be the same way. And so basically, stoichiometry allows us to measure chemical reactions, but in order to do it, we have to have a balanced chemical equation. And so the coefficients in that equation are going to show us the number of moles, and so it's the mole proportion. So just this one idea is so powerful. If you understand it, you can answer so many different problems. But if you don't get it, then the following 5 things, figuring out expected product, limiting reactants, percent yield, molar mass of gases, and titrations are going to be really confusing. But the one thing that ties them all together is this idea that the coefficients in an equation represent the number of moles. And so as you watch this video, look for the commonalities. What's going to be the one thing that ties all 5 of these together? First thing, let's say we're trying to figure out the expected products. And so in this reaction, in the burning of methane in a Bunsen burner, we're combining methane gas with oxygen to make carbon dioxide and water. And so let's say you're given this problem. Given a certain amount of mass of methane, could you figure out how much water is produced? Well, the secret is going to look like this. We can go from the number of grams to the number of moles. We can then go through a mole conversion and then go back to grams again. And so you're going to see this over and over and over in each of these problem sets. And so the first thing you have to do is make sure that that equation is balanced. And so once it's balanced, then we're ready to go. That should always be your first step when you're doing stoichiometry. Make sure that equation is balanced. Then we start with what we know, and I always write that over 1 because it's easier to do these factor label methods. And so we've got 24.6 grams of methane. First thing you want to do is convert that to moles. How do we do that? We're going to use the atomic mass of methane. Remember, it's going to be the carbon, which is 12, and the hydrogen, which is around 1. And so this is going to be the formula mass of methane. And so now we've converted it to moles of methane. Next thing we want to do is we want to bridge the gap. We want to go from the methane over to the water. And so we're going to use a mole conversion to do that. So this 1 mole of methane is going to correspond to 2 moles of water. And so this is the secret of stoichiometry. We can use the numbers in front, these coefficients, and that's going to allow us to bridge the gap. So we've already converted it to moles of water. Now we can just go back to grams again. So we're going to use that mole conversion. In other words, water is going to have an atomic mass of 18.02 grams. So now we've gone to grams of water, and so we can quickly solve the problem. And so again, it's really easy to predict what we're going to get in a reaction just using the equation in the periodic table. Now, what's a limiting reactant or a limiting reagent? That's going to be something in an equation that we don't have enough of. And so right here, what would be the limiting reactant in this game of musical chairs? It would be the number of people. In other words, once they correspond, we're going to have a lot extra of these chairs. And so let's look at this reaction. Let's say that this is a real simplified model. So we've got 1 methane, and then we've got 5 of these water molecules. This is before the reaction, and this is after the reaction. What was the limiting reactant? Well, the limiting reactant was methane. If we would have had more methane, we could have had more product, but since we only had 1 carbon, we could only make 1 carbon dioxide out of it. And so limiting reactants are another thing that we can measure using stoichiometry. So let's say you're presented with this problem. In this equation, you have 10 grams of methane, 10 grams of oxygen. Which of those would be the limiting reactant? Well, how do you solve this problem? What we're going to have to do is kind of work it out using these 2 different alternatives. And so here it is. It's familiar again. We're going to go from grams to moles to moles to grams. So we're going to start with what we know, 10 grams of methane and 10 grams of oxygen. And then we're simply going to compare it to one of the products on the right side. And so what we can do is convert that to moles of methane and oxygen. So we've converted that. And now what we're going to do is we're going to compare it to one of the products on the right side. For this one, I've just chosen to compare it to carbon dioxide. And so we're going to bridge the gap between the moles of oxygen and methane to moles of carbon dioxide. And so why do we have a 2 here? Because we have a coefficient of 2 on the left side. And we only have a 1 on this side because we have a coefficient of 1 on this side. So now we can bridge the gap to carbon dioxide. We can then convert those back to grams again. And so this is the expected products we would get using these 2 different reactants to start with. And so in other words, if we have 10 grams of methane, we could make 27.4 grams of carbon dioxide, but we're not going to, because the limiting reactant is the oxygen. That's only going to provide us with 6.88 grams of carbon dioxide. And so oxygen would be the limiting reactant in this reaction. Now, what we're looking at here is a predicted yield, how much you think you could get. Now, do you think in a reaction you're ever going to get that amount? No. It's never going to go all the way to completion like that. We're going to not have a lot of those atoms. Think of all those billions and billions of atoms that are trying to combine together. And so this is simply a predicted yield. And so what we can use is that predicted yield and then the actual yield to figure out the percent yield. In other words, this is how much we could get theoretically. This is how much we did get. And so we can use this formula, actual yield divided by percent yield, predicted yield, and that can give us the percent yield. And so we got 90% of what we could have got, and we're never going to approach 100%, but we can get pretty close to it. Now let's go to molar masses of gases. Let's say we start with 20 liters of methane. Okay, so that'd be 10 2-liter bottles filled with methane gas. How many liters of water could we get from that at STP? Now, what does STP stand for? It's just standard temperature and pressure. So we're moving into the gas laws here. And so you might think, here we go, grams to moles, moles to grams. But what's our problem? We don't have grams at this point. They're giving us liters to start with. And so you might think I'm stuck, but it's really easy to go from liters to moles, especially at STP. And so how do we do that? We start with 20 liters of methane in this case. We're now going to convert that to moles. And so again, using the gas law, we know that 1 mole of any gas is going to be 22.4 liters of that gas. It doesn't matter what the gas is. And so now we can convert immediately to moles. Once we go to moles of methane, we could go convert that to moles of water. Again, we have 1 on this side and 2 on the side of the water because the coefficient is 2. So now we've converted it to moles of water, and now we could go back to liters again. Now we're going to use that same moles to liter conversion, and that's going to give us 40 liters of water that we could get out of that reaction. And so again, we're using the same thing. We're going to moles, and once we get moles, we use our equation, and then we go to the other side. I hope that makes sense so far. And now let's go to titration. Titration is something I remember doing in chemistry that I was totally confused with, but it's really simple. Let's say we have this reaction. We're combining sodium hydroxide with oxalic acid. And so we're doing a titration. So what you do is we're going to put the base up here. You're going to run that base through, and then we're going to note what the volume is when it actually turns, when we hit that equivalence point. And so why is that occurring? Well, basically what's happening is when we get to this equivalence point, we have run out of this oxalic acid. In other words, that's the limiting reactant at that point. And so if we just record the amount of sodium hydroxide we have to add, we could figure out kind of backwards how much of this oxalic acid we're going to have. And so how do you do that? We start with the known milliliters. We can convert that to liters. Once we have the liters, we can convert that to moles because we're looking at a simple 1 molar solution. We could then go from the moles to the moles of comparing the two together. So we've got the moles of the oxalic acid, 1 here, and sodium hydroxide is 2. We can then go from there to grams, and then we could figure out how much oxalic acid we had to start with. So once we get to the moles, we can use these coefficients, and then we can compare anything in that equation together. And so did you learn to use stoichiometry calculations to predict results of a reaction? Remember, that was that simple expected yield that we got. And then did you use it to relate stoichiometry relationships, including limiting reactants? Remember, that's if we don't have enough of it. And then going to completion. Are we going all the way to the end of that reaction? And I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 26. It's on molecular solids. In other words, solids that are made of interconnected molecules. And so this could be ice in a snowflake, it could be dry ice, it could be methane as a solid, it could be sugar, fullerenes, which are these big complex molecules made of carbon, or it could be sulfur, which are made of these 8 atoms connected together and then held together with other forces. And so molecular solids could either be nonmetals, could be diatomic elements, or it could be compounds. An example of a nonmetal might just be sulfur itself. Again, it connects together in these 8 atom molecules, which are then held together. It could be diatomic molecules like solid hydrochloric acid. It could be ice, which is simply a compound, or sugar, which is a compound as well, held together. And so the structure of these molecular solids are going to determine their properties. And so they're going to have real strong intramolecular. So those are going to be the forces within the molecule itself. And as a result, these things don't have a lot of free electrons, and so they're going to act as insulators. They're going to have really, however, weak intermolecular forces, and as a result, they're going to have a low melting point. Now, molecular solids can form polymers, and we use these quite a bit, commercially and biologically, and we'll talk about those right at the end. And so a molecular solid could be dry ice, or it could just be ice. And if we look at it, there are going to be a few properties. So if we're looking at dry ice, which is simply solid carbon dioxide, it's going to have 1 carbon and 2 oxygen atoms that are covalently bonded together. And so it's going to have real intense, hard intramolecular bonds that are holding it together. However, there are going to be weak forces around the outside. So there are going to be dipole forces. There are going to be London dispersion forces. There are going to be, for example, in ice, there's going to be hydrogen bonding between other molecules. And so those are relatively weak. And so as a result of these high intramolecular forces, these are insulators. They hold on to all of those extra electrons, and so electricity doesn't flow through them. But since they have real weak intermolecular forces, they're going to have a very low melting point. And so clearly ice is not going to remain ice even at room temperature, and that's because of these weak intermolecular forces. And so all of these molecules can string together. And so let's look at a real simple molecule called ethylene. So you see here that it's going to be made of 2 carbon and 4 hydrogen molecules. But if we string ethylene together, we can make a polymer of it, and that's called polyethylene. And that's going to be one of the types of plastics that we use. And so there are commercial uses of one of these molecular solids. Now, as we make them larger and connect them, they're going to get more structure. Another example of a molecule that's important in life is the amino acid. So amino acid by itself, we're going to have about 20 of them that all living things use. But we can string that together to make a polypeptide, which becomes a protein. And instead of making a plastic bag, that makes us. It makes life. So you really are made of these polymers of amino acids. And so molecular solids are real simple. Could you create a model of a molecular solid? Remember, it's going to have really hard intramolecular and weak intermolecular forces. And then can you use that to determine their properties? Remember, the hard intramolecular mean they're going to be insulators, don't conduct electricity. Weak intermolecular mean that they're going to have a low melting point, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 36. It's on temperature, which is the average kinetic energy of molecules. In this video right here, I've got some water that's at room temperature, and I'm going to add some warm water to it. And as we add that, we'll see the thermometer is going up. Why? Well, we're speeding up the molecules, and as we speed up those molecules, they push more on each other, and they're actually expanding, or they're moving away from each other. And we can use that in a thermometer to measure the overall temperature. And so temperature, remember, is the average kinetic energy of the molecules. And it's going to be a proportional relationship between the temperature and the average kinetic energy using what's called the Kelvin cycle. And so in the Kelvin cycle, if there's no molecular motion, then there's no temperature. There's no Kelvin. And so 0 Kelvin is going to be absolute zero, no molecular motion. And so the distribution of those molecules at different temperatures can be described using the Maxwell-Boltzmann distribution. And so let's get to that. In this video, what I've done is I've taken some water that's going to be 15 degrees. So I added some ice to it. It's kind of cold. And then next to that, I've got water that's at 65 degrees Celsius. So it's going to be pretty hot. I'm going to add a drop of food coloring to each, and we're going to watch what happens. So you can see that the food coloring is spreading apart more at the 65 degrees. I speed up the video right here, so it's about 4 times. And so we can see that in the cold, it's really not moving apart very much at all, but in the warm, we're seeing this huge amount of movement of those molecules, and we can even see some little convection currents going on. And so why does that occur? Well, everything is in motion. Everything is in molecular motion. And so in this diagram right here, we've got these particles. You could think of them representing the water molecules, and then we have this particle, this large one, which you could think of represents one large food coloring molecule. And so if we run those in molecular motion, we'll find that they're all moving around really, really quickly. And as they do that, they're bumping on that particle. The faster they're bumping on the particle, the faster the particle is going to move. And this path that it takes is random. We call it Brownian motion. But if you look at all those particles right there, you'll find that some are going slow, and some are going fast, and some are going really fast. But they're not all going the same speed. And so when we're looking at temperature, what we're looking at is the average speed of all those particles. And so Lord Kelvin developed this scale. It's called the Kelvin scale. And what it does is it measures the temperature, overall temperature. And so using this scale, 0 Kelvin is going to be absolute 0, where there's no molecular motion. What you'll find is if we're looking at Celsius and the Kelvin, the marks are going to be the same. Celsius was set up where 0 is going to be freezing, 100 is going to be boiling, and so you can see how they kind of correspond in this right here. And so we could even calculate absolute 0 in the chemistry lab. How would you do that? If we take a balloon and we simply measure its volume at different temperatures. So if we measure it at 0 degrees, put it in a freezer, for example, and then we warm it up and measure its volume, and then we cool it down and measure its volume, what we could do is we could just extend that line, and what we'll find is that that's going to have 0 volume right at absolute 0. In other words, all the molecules are not moving at all, so we've approached that absolute 0. And so the Maxwell-Boltzmann distribution really talks to the overall motion of all these different particles based on temperature. And so if we look at all these particles moving around or bouncing off one another, they're all going to have an average kinetic energy, but they're each going to have individual kinetic energies or speeds of their own. And so if we were to plot that out, it would look something like this. So the average is going to be right here, but there are going to be a lot of particles that have a slower than average speed and a lot that have a higher than average speed. And so if we were to increase the temperature, what's that going to do to the Maxwell-Boltzmann distribution? It's going to look more like that. In other words, we're going to have more particles that are going to have higher amounts of speed, therefore a higher amount of temperature. And we'll talk about heat and heat transfer in the next video. But for now, did you learn to relate the temperature to the particle of the motions? The higher the temperature, the higher the motions. I hope you did, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 3. It's on the mole. The mole is an incredibly important term, but remember, it's just a number. It's Avogadro's number. Why is it important? Well, it allows us to deal with the massive number of atoms that are found in matter. This is one of my favorite demonstrations. You take a 5-gallon jug, put a little bit of alcohol in it, like ethanol, and when you light it, you get this huge woof and this huge combustion of the ethanol. If we were to write out the formula, it looks like this. Why am I talking about this when I'm talking with moles? Well, remember those coefficients that you write in front of the compounds in an equation like this represent the number of moles. In other words, how many massive number of atoms are interacting. And so it's really important when we deal with chemistry to understand what the mole is. And the mole is simply Avogadro's number. It's a number. It's 6.02 times 10 to the 23rd. Where does that number come from? It's derived from the number of atoms in 12 grams of carbon-12, but it just gives us a usable amount of material that we can work with in the lab. So if we're ever looking at a reaction like this, the coefficients, remember, are going to represent the moles. But it also serves as a bridge, most importantly, a bridge between the mass of an object and the number of particles that are found within that object. And so where does the name come from? Avogadro was an Italian chemist, worked many years ago in the early 1800s. And so he came up with Avogadro's law. Basically, as we increase the volume of a gas, he proposed that we were increasing directly the number of particles that are found within that. Didn't matter what the gas was. Now, he died before they actually came up and quantified this idea of the mole, but we still give him credit for that early work. And so 1 mole is 6.02 times 10 to the 23rd. But it's just a quantity. It's like if I have 1 egg, we call that an egg. But if I have 12 eggs, we call that a dozen. And so a mole is just a number. We could have a mole of anything. But it's most important when we're dealing with chemicals. To give you an idea of how massive this number is, imagine if I had a mole of marbles. So just regular marbles like this, and I were to start covering the earth. Well, I could cover the earth in marbles, and that covering of the earth would be 3 miles thick. And so there's a huge amount of numbers in Avogadro's number. And so when you're dealing with even small amounts of a compound, small amounts of an element, you have to understand that you have that many atoms that are found within there, massive amounts. Again, it forms a bridge. It forms a bridge between the mass of an object and the number of particles that are found there. And so it's really important at that kind of a bridge point. And so let's talk briefly about what an atomic mass unit is. And so let's say we take carbon dioxide, for example. It's going to be found in the air. You breathe it out. Its atomic mass unit is going to be the mass of each of the individual atoms. And so we have 1 carbon, so we could look on the periodic table, and the atomic mass of that is 12.01. And then we're going to add 2 oxygens. Each of those are 16, and on the periodic table we could find it here. And so its atomic mass unit of carbon dioxide is going to be 44.01. And so what is an atomic mass unit? It's the mass of 1 nucleon. So that could be the mass of a proton or a neutron. Now, why is that important? 1 mole of carbon dioxide then is going to weigh 44.01 grams. Let's say we're looking at nitrous oxide. Could you figure out the atomic mass unit of that? You could pause the video and try to figure this out. Well, you'd have to find the nitrogen, you'd have to find the oxygen, and we'd simply add that up. So it'd be 30.01. But if we had a mole of carbon dioxide, that'd be 30.01 grams. And so it forms this bridge between the mass of an object and then the number of particles that are found within that. And this is where sometimes people get confused about the mole when they're trying to make these mole conversions. And so let's say I had 9.01 grams of water. It's about almost 10 milliliters of water. And so that'd be about 2 teaspoonfuls of water. And let's say I wanted to figure out how many molecules of water are found inside there. Let me show you how the mole can act as a bridge. So we have 9.01 grams of water. The mole is going to act to convert that into the number of particles. So first we use this mole conversion. Remember, 1 mole of anything is going to be the atomic mass of that in grams of water. So where am I getting the 18.02? I'm adding the 1 oxygen, 16, plus the 2 hydrogens. And so 1 mole of water is going to be 18.02 grams. And so what I could do is I can cancel those grams. So now I've converted it to moles of water. Now we use Avogadro's number. And so I'm going to take 1 mole of water is equal to a number of molecules of water. So 1 mole is equal to Avogadro's number of that. I can now cross off my moles, and now I can solve for the number of molecules of water. And what I get, the math is easy here since I'm taking this dividing by 18.02, we get 3.01 times 10 to the 23rd. And so, I mean, wrap your head around that for just a second. 2 teaspoonfuls of water, the number of water molecules that are found in there would cover the earth in marbles if we converted those molecules to marbles 1.5 miles thick. And so now let me give you one for you. Let's say we had 5.272 grams of glucose, C6H12O6. Could you convert that to molecules of glucose? And so here are the atomic masses here. I'll put the answer in the video description down below so you can check and make sure you're doing it right. Remember that mole serves that bridge. It's also incredibly important in chemical reactions. This is one of my favorite reactions. This is a thermite reaction. We're getting a combination of iron oxide with aluminum. And so since it has the oxygen source inside it, this would burn underwater if you wanted to. Okay, so what did we learn in summary? Could you pause the video and fill out what's in the blanks? Let me do that for you. So a mole is Avogadro's number. Do you remember what that is? It's going to be 6.02 times 10 to the 23rd. It's going to form a bridge between mass and the number of particles. And then we use it to quantify chemical reactions. And so when we're looking at those coefficients in the front of any kind of a chemical reaction, it's going to tell us the number of moles. And so what should you have learned? Did you learn this? That the mole allows us to connect particles, moles, mass, volumes all together. both qualitatively in the form of, for example, a chemical reaction where we're writing that out, and quantitatively, actually calculating the number of particles in material. So that's the mole. It's just a number, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 37. It's on the rate constant. Before you watch this video, make sure you've watched the video, it's 37, on the rate law. If you don't know what a first, second, zero order reaction is, make sure you watch that video so you know what I'm talking about. But here's our rate law right here. So in our rate law, the m and the n, and there can be more exponents than that, is going to tell us the reaction order. In other words, is A proceeding at a second order reaction and B at a zero order reaction? So that's going to be in the exponent. In here we're going to get the concentration, so this would be the concentration of reactant A and B. But remember, if we have a really big reaction, we could have more of these reactants. And then finally we have reaction rate, which is going to be how fast this reaction is proceeding. So if we get rid of all those things, what we're left with is K. And so what is K? It's going to be this rate constant. And so the first thing you should understand about that rate constant is that it's not constant. It's dependent upon things like temperature and the presence of a catalyst, but really you want to understand what rate constant is and how it can be calculated. And so if we look at the rate law is going to contain a constant, we'll call that K, and that K is measurable. In other words, we can gather a bunch of experimental data, we can look at it, and we can work backwards to figure out what K is. A really easy way to do that in AP Chemistry is to measure the reaction rate over time and then use that to figure out K. There's going to be huge variability in K. In every reaction we're going to have different Ks, and you can't figure out what it is just looking at the equation, so we have to measure that. Why is there so much variation? There's so much variation in our chemical reactions, or the mechanisms of that, and we'll talk about that in the next video. Also, you should understand that K is not constant. It's going to be dependent upon things like temperature and the presence of a catalyst. And then finally, if we're looking at the order of reaction, especially in a first order reaction, there's a cool relationship between the half-life and K. In other words, they're going to be both independent of concentration, so it's really easy to figure out. Once we have the rate, we can figure out the half-life. And so here's a simple relationship between the two. And a great example of the half-life then is going to be radioactive decay. And I think visually when I show it to you, it'll make sense. And so the first thing you should understand is that K is going to have wide variability. This is somebody's research paper, and before they get to the actual chemistry, they had to publish all of the rate constants that they'd figured out in all of their experiments. And if you look at all these numbers, they're incredibly variable. And the reason we have so much variation in K is that we have so much variation in reactions. We can't simply look at the reaction itself and figure out what K is going to be. We have to experimentally measure that in the laboratory. Also, the rate constant is not constant, so temperature clearly is going to affect the rate constant. And also things like catalysts. We'll talk more about that in later videos, but catalysts can speed up a reaction. And so the catalyst found in, this is a cutout of a catalytic converter in a car, and what those are really doing are speeding up the reaction and getting rid of some of the really nasty stuff that is produced in an internal combustion engine. And so if we look at the rate constant, and now we're talking about a first order reaction, right here we have radioactive decay. And so let's look at this. On the left side, we have fewer molecules that we do on the right side, but let's just watch it occur in a first order reaction. And so as this reaction goes, you can see a lot of the reactants are being consumed right at the beginning, but eventually it kind of drops off that rate at which they're being consumed. And so let's watch that again. So if we look at it again, a lot of reactants are being consumed at the beginning, but then it's kind of falling off as we go. And so if we were to look at the ones over here on the left, let's go back. How many did we have at the beginning? We have 16. And now let me kind of move it forward and let's try to find the half-life. So we had 16 there, and now we've got 8. And so we've got half of them during that given period of time. But now if we watch during the next period of time, now we're going from 8 down to 4, and then from 4 down to 2. And you can see that it's taking about 1 half-life each time. Now, why is it not exactly 1, 2, and 3 up here? It's because we have a very small sample size. If I were to count all of these on the left, it'd be more specific. Okay, so let's get to what that looks like graphically. And so what is half-life? Half-life is T sub 1/2. It's going to be the amount of time it takes for half of the reactants to be consumed. And so this is what a curve of radioactive decay would look like. And so if I draw that graphically, this box is showing that 50% of the reactants that we had right here are being consumed. And if we look down on the bottom, let's say this takes 1 year. Now this doesn't always have to be 1 year. It could be thousands or millions of years for the half-life. But if we look at that step, and then we look at the next half-life, now we're going from 50 down to 25. And so what we're doing is consuming half of the reactants that we had left. You can see that as we do it again, that each of these half-lives is going to be constant. And so in a first-order reaction, all of the half-lives are going to be constant. And so K and half-life have these cool relationships. First thing is that both of them are independent of the concentration. The K is going to remain constant and the half-life is going to remain constant. And also we can use K, once we've calculated it, to figure out half-life, or vice versa. There's a direct inversely proportional relationship between these two. And so it's easier to kind of now look at a zero order and then a second order reaction. So what would be the half-life of this one? Well, again, we're going to consume half of it. And so this would be during a given period of time in a zero order reaction. Look how long the half-life is. But now we're going to go to a smaller half-life and then even a smaller let. And so even then a smaller yet. And so in a zero order reaction, you can see that the half-life is getting smaller. Or if we look at a second order reaction, let's look at that first half-life. It's really, really short. Next one's longer, next one's even longer yet. And so you can tell just looking at a graph and figuring out the half-life, is this a zero order, second order, or if it's exactly the same in each one, then it's going to be a half-life or a first order reaction. And so can you connect the half-life of a reaction to the rate constant in a first order reaction? Again, they're both going to be constant. We can use this equation to figure it out, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 65. It's on the equilibrium constant. A chemical weapon that was used in World War I and killed a number of people is phosgene. Phosgene is created through a reversible reaction where you take carbon monoxide and chlorine gas, you mix them together, and you get this phosgene. And this is a World War II poster warning people that this chemical might be coming. It gives off a smell kind of like hay, and since it's colorless, that was an important way for you to know that this chemical might be coming. And so in any kind of a chemical reaction like this, it's reversible. The reactants are converted into products and the products are converted back into reactants. But it's important that we know, do we have more reactants or do we have more products? And so we use our K value or equilibrium constant to figure that out. In this chemical reaction at standard temperature and pressure, we're going to have a really large K. What does that mean? This reaction is going to move towards the right. That means that we're going to have way more phosgene than we're going to have any of these reactants. And so in a reversible reaction, reactants are converted into products and back again. And over time, it eventually reaches an equilibrium. Now, what is K? K is simply a way to measure when we reach equilibrium. Do we have way more reactants or do we have way more products that are being produced? And so I've got this model right here that shows us how reversible reactions work. So there are going to be a bunch of molecules over here. We'll call those reactants, and they'll be green when they're on this side of the chamber, and they'll be red when they move over to the right side. This is a PHET simulation. Over to the right, I've created a K-ometer, which is going to measure our K value. So K is going to be the number of products divided by the reactants. At this case, we only have reactants on the left side, and so we have a very large number here, 100. And how many products do we have? 0. And so what's our K value going to be? It's simply going to be 0. So let me start this and see what happens to our K value. And so molecules are moving now from the reactant to the product side, from the product to the reactant side, but we basically have the same level on both sides, and so our K value is 1. Now as I tip it towards the right, we're getting more products, and so that is going to become a larger number up here, and so our value goes up to 3. We have about 3 times as many products. Likewise, when we pull it in the other direction, now we have way more reactants, and since our reactants in this case value is going to be around 75, products around 25, our K value is going to be around 1/3. Now this model oversimplifies a little bit because we only have products and reactants in this simulation. In a chemical reaction, you're going to have lots of products and lots of reactants. And so if we've got a reversible reaction like this, where this represents our reactants and this represents our products, this is the general equation for K. But if we were to figure it out for a more complex kind of a equation, this is the general way that we write out K, where K represents the concentration of one of our products, so that's going to be C, raised to the power of the number of moles that we have of that chemical. Likewise, it's the concentration of D raised to the power, and that power is going to be the moles of this product as well. Likewise, we're going to put the reactants on the bottom. It's simply the concentration raised to the mole. So what am I talking about? Let me show you an example of that. If this is our equation right here, this is going to be our equilibrium constant. And so what do we have? Well, here's going to be our products on the top. So it's going to be the concentration of water right here raised to the 2 power, because we have 2 moles out in front of that. Likewise, we've got nitrogen gas raised to the 1 power because we only have 1 mole of that. We're then going to put our reactants in the bottom. Likewise, both of these are raised to the 2nd power because each of those have 2 moles. Now, if I were to give you that reversible phosgene reaction, could you write the equilibrium constant for that? What's our K value going to be equal to? It's simply going to equal to this. Well, each of these are raised to the 1 power because we have only 1 mole of each of these. So this would be our K value. Now, we can calculate K in the lab, and so at standard temperature and pressure, our phosgene is going to be this. This is going to be that value I showed you at the beginning, 4.57 times 10 to the 9th. What does that mean? We're going to have way more of this product than we do the reactant at that given point. In other words, you could write this number over 1 on the bottom, and it's going to show you how many of them are going to be the phosgene. Now, if we were to change the temperature, we can actually change that K value. If I change that temperature to 200 degrees Celsius, so if I change it and make it a really high temperature, you can see that our K value is going to be much lower. What does that mean? It's going to be shifted back towards the left, and we're going to have way more of those reactants than we do products. Likewise, if we were to take this equation right here, where we've got nitrogen and oxygen, and we're converting that into nitrogen oxide, what would that look like? Our K value is going to be simply this. It's going to be raised to the 2nd power because we have 2 moles of this gas. What is our K value for this equation? It's going to be a really, really small value. What does that mean? That we're going to have way, way more reactants concentration-wise than products, and so it's going to be shifted way over here towards the left side. Now, what if I were to increase temperature at this point? Let's say I were to have a strike of lightning, that's actually going to raise our K value and it's going to push it over towards the right side. Now we know that in the atmosphere we have nitrogen gas and we have oxygen gas, but if we had a K value that was really, really large at standard temperature and pressure, all of this would quickly be converted into nitrogen oxide, but we know that doesn't occur. It only occurs when you have a huge amount of energy, a huge amount of lightning. And so again, in summary, if our K value is ever greater than 1, that equation is going to move from the reactants to the product side. We're going to have way more products than we do reactants. If it's ever less than 1, then we're going to have the reverse is true. We're going to have way more reactants than we do products. And so did you learn to use the values of K to predict which chemicals we're going to have when it reaches equilibrium? I hope so, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 15, which is on solutions. We generally think of solutions as being liquids, like this beverage right here, but remember solutions could also be made of gases, like air, and then we could also have solids that are solutions. So steel is an example of that. We have carbon atoms inside these iron atoms. And so a solution, remember, is going to be made of 2 things, solvent and solutes. Solutes are going to be dissolved within the solvent. And generally, we're going to have more of the solvent than the solute. They should be homogeneous in nature. That means they're going to be smooth throughout the whole. We can't see different parts or different concentrations in various areas. This is based on scale. Obviously, if we look at the molecular level, nothing is going to be smooth. And so what we usually use is the human eye. If it looks homogeneous to the human eye, we're going to call it a solution. That's one of the indicators. It could be made of liquids, solids, and gases. And if we have a liquid solution, we could have solids and gases dissolved within it. And so generally we're talking about liquids when we're talking about solutions. So what are some properties? Does it scatter light? We'd have to put a big no there. If it scatters light, it's not going to be a solution. How do we separate the solute? How do we get it out of this solution? Could we run it through a filter? No, we can't filter it. It's going to run right through a filter. And so we have to have another way to get those solutes out. One way would be through a process called chromatography. And what we're looking at is the different intermolecular forces between the solutes, and we're using that to separate them. And then we could also use distillation. That also is looking at intermolecular forces, but we're looking at differences in vapor pressure to separate them. And so those are two ways that we can separate the solutes from a solvent. When they form, that formation of a solution could either be exothermic, so it's releasing heat, or endothermic, where it's consuming heat. And that's all based on intermolecular forces as well. And then finally, the composition of a solution, we're going to measure that in molarity, which is going to be the moles of the solute in the liters of the solution. And in chemistry, you should be able to prepare a basic molar solution. And so remember, solutions could be solids, liquids, gases. It has to hit these three things. It has to be homogeneous to the naked eye. It can't scatter light. And then finally, it cannot be filtered. And if it hits all of those, it's probably going to be a solution. We can't filter it, remember, so how are we going to separate the different parts of it? Well, one of these two processes, either chromatography and distillation. Both of them use intermolecular forces, so the forces between the solutes and the forces between the solute and the solvent itself. So basic chromatography is just using these interactions. But if we were to heat them up, eventually some of them are going to move from a liquid into a gas phase. And so that's going to increase the vapor pressure. And so distillation is going to use differences in this vapor pressure to separate. So for example, this might be alcohol. It has a high vapor pressure. That means it easily is going to evaporate, and so we could use that to separate it. So chromatography comes in two different types. We could either have paper chromatography or column chromatography. In paper chromatography, what we do is we take our solution. So a great example we use in a biology class is we'll mash up leaves, we filter the material inside the leaf, and then we want to separate it into the different pigments that are found within the leaf. And so what we'll do is put that in some kind of a solution. We'll generally dissolve it in some kind of an alcohol. And then we just have paper, and we'll put the paper inside that solution. And what happens over time is it's going to migrate up. We're going to have a front that migrates up. And eventually what we can do is separate that all into its different solutes. Some of these would be like chlorophyll. And so how does that work? Well, it's based on intermolecular connections. And so it's based on how well these solutes adhere to the solvent that they're dissolved in, because if they really love the solvent, they're going to be pulled all the way to the top. And also, how much do they adhere to the paper? And so it's the sum of all these connections that allow us to separate them apart. Column chromatography is going to work in a little bit different way. What we'll use is a big column. So it's going to be a big glass column, and it's going to have a exit point at the bottom. We're going to put some absorbent inside there. Usually that's going to be like a silica gel, and then we'll put some aluminum oxide inside it. So we have the absorbent in there. And then we're simply going to dump our solution up at the top. And timing is important when we're doing column chromatography. What's going to happen in here is that we have two different solutes dissolved in that one solution. So as we let it run, they're going to move down the column at different rates. Why is that? Well, let's say A is not adhering to the absorbent as much as the red is. The blue is not going to adhere to the absorbent as much as the red is, and so it's quickly going to move through there. And so what we can do is we can collect that first solute, and then we can move it over and we can connect the second solute. We're still looking at these intermolecular forces, we're just doing it in a slightly different way. Distillation works in a different way. Distillation, what we're looking at is differences in vapor pressure. And we've been distilling for a long time, humans have. So example, we could take wine and we could put wine in here. And what's going to happen is the alcohol is going to evaporate. So it's going to evaporate, turn into a gas phase. We have condensers up here. And then it's going to turn it into a liquid phase over here. And so since they're going to have different vapor pressures, ones that are more volatile, ones that have a higher vapor pressure that are going to evaporate more quickly are going to separate off. Where do we use this distillation process? Aside from making brandy out of wine, we'd use it in oil refining, for example, to get the different parts out of crude oil. Ionic compounds are important in solutions as well. And so in this simulation, what I'm going to do is I'm going to take some salt and add it to water. And so as we add salt to water, first of all, water by itself doesn't conduct electricity. And so what we'll do is shake a little bit of salt in there, and then we could use a conductivity measure to figure out, okay, now we're transmitting a little bit of energy. Let's say we add a little bit of salt to it. What's going to happen to the conductivity? It's going to increase. You can also see on the upper right that we're increasing the concentration of that salt, but now let's evaporate some of that water. So as the water evaporates, look at the concentration, it's increasing, and then right at the end we just have a layer of salt at the bottom. Let's look at the microscopic level. So sodium chloride, remember, is an ionic compound, and so as we add that to salt, it's going to separate into its both sodium and chloride ions. And so they're each going to dissolve in the water. As we remove the water again, what happens? The concentration increases, and then bang, we're back to this ionic compound again. What's going on at the molecular level? Well, let's watch. If we add the sodium chloride to the water, it's going to break apart into its ions. The sodium, which are positive, are going to be attracted to the negative ends of the water. You can see the negative ends of the water are going to be adjacent to the sodium, and then the positive parts of the water are going to be adjacent to the chloride ions. And so it's really easy to take something like water, which is a clear dipole, and we could absorb ions with it. Formation of those solids is going to either take in energy or release energy. And so what we can look at is the formation of a solid. These are going to be the enthalpies of that solution. Some are positive, some are negative. And so if we were to look at these ones, ammonium nitrate, if we add that to water, it's going to be an endothermic process. That means it's going to take in energy. And so we could use that, ammonium nitrate and water, to make these instant cold packs. What we're doing is just combining them together. It's taking in heat from the surroundings, and it feels really, really cold. A lot of these are going to be exothermic. So when we mix them with water, it's going to release energy. And all of this has to do with intermolecular forces. An example of this could be hydrochloric acid. Hydrochloric acid, when you mix it with water, is going to create a huge amount of heat. If you were to have a huge amount of hydrochloric acid and just dump a little water in there, you'd have this massive reaction, huge amount of heat. And that's why in the chemistry lab, we always add acid, small amounts of acid to the water, because it's going to generate heat, and that water is able to mediate some of that change. Remember, we measure the concentration of a solution using molarity, which is going to be the moles of solute in liters of total solution. And let's say you're doing a lab and they say prepare a 0.5 molar sodium chloride solution or salt solution. How would you do that? Well, they're already telling you how many moles you're going to put into the solution. They're saying 0.5 moles of sodium chloride. So we have to convert that to a mass, something that we can actually deal with. So we're going to use this conversion to convert that to grams. Where are we getting this 58.44? We're using the atomic weight of both sodium and chlorine. We're then going to make that conversion, and that's going to be 29.22 grams. So what would we do in an Erlenmeyer flask? We could add a certain amount of water, then we're going to add our salt to it, we're going to make sure it dissolves, and then we're going to bring that volume up to 1 liter to make that 0.5 molar sodium chloride solution. So did you learn the following? To separate solutes, we could use chromatography, both paper and column, and that's going to be based on intermolecular forces. Did you figure out how to use representations, show the interactions between them? Remember, if we look at that molecular level, we were able to show how water is able to dissolve these these ions. Were we able to use representations to link molarity to particle view? And so we were able to do that and also kind of calculate a certain molar solution. And then finally, could we design something like a distillation process where we could separate solutes? Yeah, we just have to look at their different vapor pressures to pull them apart. Those are solutions, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 63. It's on the reaction quotient. One of my favorite games when I was a little kid was hide and seek. But lots of times at the end, you'd have one person who's still hidden, and the person who's searching for him can't find him. And so we would always play a game called hotter or colder. As they get closer, you would say you're getting warmer, you're getting hotter, and as you're moving away, you're getting colder. And that'd be an easy way for them to find that last person. And so in a reversible reaction, we have something similar. And so we identify K as the equilibrium constant, which is going to be a ratio of products to reactants in a reversible reaction. But that only occurs when we reach equilibrium, when we find what we're looking for. But in science, we have a reaction quotient, Q, which is going to be the same thing. It's calculated in the same way. but it's where we are before we actually reach equilibrium. So it allows us to see how far we are away. It's like playing hotter or colder. And so in a reversible reaction, the reactants become products, products become reactants, and over time they eventually reach equilibrium. And when we reach equilibrium, we can calculate the equilibrium constant, which is simply K equal to the concentration of products divided by the concentration of the reactants. But along that pathway, we could also calculate Q, which is going to be the concentration of products to reactants at any given time. And over time, Q is going to approach and eventually become K once we reach equilibrium. And so a model kind of works like this. Imagine if we have a free energy diagram and this ball is going to roll back and forth, but let's say it eventually stops right here. At the bottom is going to be K, and where it's at now would be Q. So we know that it's going to move towards the left. If we let it roll a little bit more, it eventually pauses. Now we have a new Q. Now we know that it's going to move right, and eventually it's going to reach K, or that equilibrium. And so if we use an energy diagram like this, K is going to be right here, and Q is going to be anyway along that path. And so here I've got a model, which is essentially a reversible reaction model. On the left side, we've got a bunch of molecules. We'll call them A, and as they bounce over to the right side, they become B. And so what I'm doing is simply keeping track of the number of reactants and products. Reactants are going to be green and products are going to be red, and I'm keeping track of that every 50 seconds. And you can see that it varies at the beginning. At the beginning, you can see here that we had 100 reactants and 0 products, but right now, as we get 350 seconds in, it's starting to stabilize. And so I could gather data in a model kind of like that. Now I'm going to take this data and I'm going to graph it, and we're going to have a graph that looks like this. So at the beginning, we have all reactants and 0 products, but you can see over time it's eventually reaching this equilibrium. And so let's say that at the end we reach equilibrium. And again, this is simply a model, but how would we calculate that equilibrium constant? It's simply going to be the concentration of products divided by the concentration of reactants. And so if I were to calculate that, our products is 65 and our reactants is 35. And so let's say K is 1.9. And so at the end, when it reaches equilibrium, we'll say that our K value is going to be 1.9. Well, what's Q? Q is going to be values along the way before we reach equilibrium. And so what's going to be our Q at that first point? It's going to be 0. How did I calculate that? I simply took the number of products, which is 0, divided by the reactants, which is 100, and that's going to give me a Q value of 0. Now if I go to the next one, so if I go to 50, how am I going to figure that out? It's going to be my products, which are 0.42 divided by 0.58, and so that's going to be 0.72. And now let's watch what happens to our Q value as we move closer and closer to equilibrium. You can see it stabilizes here, but I simply don't have enough products. It's lower than that. Now I overshoot it and my Q value goes a little bit too high, and then it eventually approaches it and it eventually becomes K. Q and K are exactly the same thing. And so this is a model, but it shows you what's going on in a chemical reaction. K is what we have at the end is Q, and Q is what we have along the way. And so if we were to summarize a little bit, in a reversible reaction, if my Q value is less than my K value, the reaction has to move to the right. And what does that mean, move to the right? I have to convert more of my reactants into products. What happens if my Q value is greater than my K value? Then I have to move to the left. And what do I have when my Q value equals my K value? I'm at equilibrium, or they're going to be the same ratio. Now, it's sometimes hard to remember this, and so if you put it on a number line, it helps you quite a bit. If I put my Q and my K values on a number line like this, so K is where I want to be and Q is where I am, which way am I going to have to move along this number line? I'm going to have to move from the right to the left. So I'm going to have to move left. I'm going to have to convert more of my products into reactants so I can eventually reach K. Now this only works in a homogeneous kind of a state. In other words, if we were to look at liquids, and solids, or gases to solids, or gases to liquids, this reaction quotient is not going to work. Now if we apply it to an actual chemical reaction, I've got this reversible reaction up here, 2 moles of these makes 1 mole of this and 2 moles of this. I can use what's called an ice table to look at the initial concentrations and then my final concentrations at equilibrium. Why do they call it an ice table? Well, you can see here that I have my initial concentrations, my equilibrium at the end, and then I have my change, or I have my ICE, and this is going to be measured in molarity. And so if we were to calculate calculate what my Q value is right here. Here's my Q value right here. Well, you can see that since I have no products at this point, my Q is going to be equal to 0. Now, how do I figure out my K value? If I'm given my concentrations at equilibrium, I could calculate K. Now, I'm going to show you how to do that in the next video on equilibrium, but let's just say it is 650. And again, watch the next video on equilibrium if you don't know how to do that. So which way is this reaction going to move? Is it going to move to the right? Is it going to move towards the left? Well, you can see if I put them on a number line, if I put K on a number line and Q on a number line, I have to move to the right, which should make total sense. I have to convert these reactants to products if I'm ever going to approach equilibrium. So it's going to move towards the right. And so if I were to show you what those values are going to be, so how did I get these values? If I take this number, subtract that, I'm going to get this value right here. You should start to see a pattern in that change row. And so if I look at it, all of these values are going to be the same molarity change. Well, why is that the same molarity change? It's because we have the same moles up here. If we look at this one, it's 0.019. Why is that? There's going to only be 1 mole right there. And so stoichiometry is incredibly important. We have to make sure that that change matches the stoichiometry of our equation. And so did you learn to determine the effect of chemical reaction manipulation on Q and K values? I hope so, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 58. It's on spontaneous processes. Those are processes that occur without external energy. And so I'm going to knock over this tower right here. And as I do that, that is a spontaneous process. Now, it's not going to occur until I add a little bit of energy. You can see that that block right in the middle on the bottom, I have to pull that out of the way. But as I do that, that's going to be a spontaneous process as it falls down. And that's going to just move in one direction. It's not magically going to move in the other direction. And so in the other direction, that would be a non-spontaneous reaction. It's not going to occur. It's statistically impossible for that to occur. And so as I talk about spontaneous reactions, I'm going to treat the words enthalpy and internal energy the same. There are slight differences, but we're just going to treat them as synonyms. And so in processes, we can either have spontaneous or non-spontaneous processes. We can know that it's a spontaneous process right away if we ever see a decrease in enthalpy and an increase in entropy. Now, if you don't know what these two things are, I'll put links to videos about both enthalpy and entropy. But if we ever see a decrease in that amount of internal energy and an increase in that randomness or that dispersal of that matter, we know that it's a spontaneous reaction. And any spontaneous process is going to favor the products or the things that are created in that process. If it's non-spontaneous, we can know right away if we see an increase in enthalpy and a decrease in entropy. We know that that's going to favor the reactants and it's going to be non-spontaneous. And so how do you know if we're favoring the products or the reactants? We can use something called the equilibrium constant to figure that out. And I get a little model that shows you that. If we ever see an equilibrium constant greater than 1, we know that that's going to favor the products and it's going to be spontaneous. If it's ever less than that, less than 1, we're going to see a non-spontaneous reaction. Now, the thing that's tricky about a spontaneous reaction is that it just doesn't occur magically. Sometimes it can occur over millions of years. And so you probably know that graphite can be turned into a diamond, but it takes a huge amount of energy and it takes a huge amount of pressure. And so that's going to be a non-spontaneous process. It just doesn't occur on its own without external energy. It takes a huge amount of energy. But if that's in one direction, in the opposite direction, we're going to have a spontaneous reaction. But you know that a diamond just doesn't break down into graphite. It takes millions of years for that to occur. And so spontaneous process is probably a bad term. It's better to use a thermodynamically favored process. That just is too much of a mouthful. And so if we're looking at a spontaneous process, one of the first clues is to look at the enthalpy, which is the amount of internal energy. And if we ever have a change in enthalpy that is negative, we know that that is probably going to be spontaneous reaction. So if we were to look at a thermite reaction, it's exothermic, it's giving off that energy. That means our reactants have more energy than our products. If we were to look at the rusting of iron like you do in the hand warmers, we have a negative enthalpy change, and so that's a clue that this is going to be a spontaneous reaction. But sometimes we'll have reactions that occur on their own, but they, instead of giving off energy, are actually consuming that. And so if we look at this cold pack right here, that means that our delta H is actually going to be a positive value. So it's going to be an increase. And so we can't just look at enthalpy itself. We have to add entropy to the equation. So imagine if I had these two spheres. On the left side, we've got gas. On the right side, we have a vacuum, and I were just to open it up, what's going to happen to those molecules? Well, they're going to move from the left to the right side. Is there any change in temperature? No. And so what we're seeing there is a change in entropy. And so if you're looking at a spontaneous process, you don't want to only look at the change in enthalpy, you want to change in that entropy as well. And so to figure out if we're favoring products or reactants, we can use a term called the equilibrium constant, which really works with reversible equations, but this will work right here. So if we imagine we have reactants and products, the equilibrium constant is simply the concentration of products divided by the concentration of reactants. And so let's look at this first scenario. And this is a PHET simulation. I'm going to put some molecules over here on the left side. And so they're going to spread out, and then they're going to be acted on by gravity. They're going to bounce back and forth. I started with 100 of those molecules on the left side. They're randomly dancing back and forth. And so as they move to the right side, we're changing color. And so we can represent those as products. So if we look at how many I have on the left side and the right side, on the left side I have 51, on the right side I have 49. If I were to divide my products by my reactants, 50 over 50, we would say that my K value is right around 1. And so we're going to be at equilibrium. In other words, we're not favoring either reactants or the products. Now, if we look at this next simulation right here, I'm going to change it a little bit. I'm going to put the ones on the left side, give them a little bit more gravitational potential energy, and let's start that going. And so again, those molecules are bouncing around. You can see that the energy on the reactant side is actually higher than the energy on the product side. And so that's pushing those molecules over to the right side, or it's favoring those products. If we speed it up and let it run for a while, you can see now that I have 76 molecules on the right, 24 on the left. So if I were to put 75 over about 25, my K value is going to be around 3, and so that means it's going to be greater than 1. So we're favoring products in this case, and so that's going to be a spontaneous reaction in this case, or a spontaneous process pushing it to the right. What have we done? We've seen a decrease in the enthalpy, or decrease in the energy. And if you look at it carefully, you can actually see an increase in entropy as well. Let's go in the opposite direction. Now I've given less energy on the left side. If we let this run for a little bit, it's hard for them to get up to the right side. It's hard for them to become products. And so let me speed this up a little bit, and we'll watch it change over time. You actually see less entropy in this model right here, less change because it takes more energy to move to the right side. If we were to figure out the K value, now our products are at 20, our reactants are going to be at 80. So if I were to figure out my K value, it's around 0.25, and so it's going to be less than 1. So if my K value is less than 1, that tells me that this is probably a non-spontaneous reaction. And so in a spontaneous reaction, you know it's spontaneous right away if you see these two things. If you see a decrease in enthalpy, or decrease in that internal energy, and you see an increase in entropy, it's non-spontaneous if we see the opposite of that. In other words, if we see a increase in enthalpy, in other words, if we're looking at an endothermic reaction, and we see a decrease in entropy. So if we were to kind of organize that a little bit, in the upper left, what we're seeing here is an increase in entropy and a decrease in enthalpy. So this right here would be a exothermic reaction where it's becoming more random over time. We know right away that that's going to be spontaneous. If we look in the lower right, what are we seeing here? We're seeing an increase in enthalpy. This is an endothermic reaction, and we're seeing a decrease in entropy. We know right away this is not spontaneous. Now, what about these other two? Well, you're going to have to watch the next video on Gibbs free energy to figure out how we do that. And so did you learn to predict whether a process is spontaneous using delta H and delta S? I hope so, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 36. It's on the rate law. Now, in the last video, we talked about reactions and how the speed of reactions can vary. And so if we look at this reaction right here, the breakdown of ammonia into hydrogen and nitrogen gas, it's going to proceed along a straight line. In other words, if we have a high concentration of ammonia or a low concentration of ammonia, the amount that's being consumed is going to remain consistent. In other words, the rate of this reaction is the same. But if we look at something like this, nitrogen dioxide, and we look at its rate as it's broken down into nitric oxide and oxygen, it's going to follow a different curve. In other words, when there's a lot of nitrogen dioxide, it's going to proceed really, really quickly. And then when there's not much, it's not going to proceed as quickly. And if we look at those two equations, they almost look identical. And so there's no way to tell, just looking at a balanced equation of a reaction, how fast it's going to proceed. And that's an important thing to understand as we move forward with the rate law. And so the rate law really refers to the amount of reactants that are being consumed. And so we don't have to concern ourselves with what products are being made. And here's the equation for the rate law. And so if we break it down, rate, the speed of the reaction, is equal to K. K is going to be the rate constant. We'll talk about that in the next video. And that's going to be times the concentration of the reactant, how much A we have, raised to the M power. And that power is going to tell us the reaction order. Now, the three ones I'll talk about are 0, first, and second order reactions. And so what does that mean if we have a 0th order? It means that we're putting a 0 right here. In other words, it's the concentration of A raised to the 0 power. In a first, we're going to put a 1 there, and in a second order, we're going to put a 2 there. And so what does a 0th order look like? Well, if you raise anything to the 0 power, it's simply 1. And so you can think of this turning into a 1, and so rate is equal to K. In other words, rate is going to be equal to that constant, or the rate constant. If we look at a first order reaction, then this is raised to the 1 power, and so it's going to be the rate constant times the concentration of A. So what are we going to get? We're going to get this curve where it's going really, really quickly at the beginning and then slower as we get more. And then if it's raised to the second power, it's going to be a second order. So it's going to be K times the concentration of A raised to the second power. And you can see that that reaction is actually going to go faster the more we have. And so we'll go through each of those, and I'll give you examples of them as well. Now, the thing that you have to remember is that we have to determine these experimentally. We can't just look at the equation and figure out the rate law for that reaction. What if we have more than one reactant? Then the rate law is still going to apply. And so it's going to be simply this. Rate is equal to K, the rate constant, times the concentration of A raised to the M power and B raised to the N power. And so each of these can proceed along a different reaction order. And so if we want to figure out the overall order, we're simply going to add those values up. And so I'll show you how we can use data to figure out what order it's going to be after we've calculated the data. And so in a 0th order reaction, here's an example I gave you at the beginning. We're breaking down ammonia into hydrogen gas and nitrogen gas. And so rate is equal to K. In other words, it doesn't matter how much ammonia we have, it's still going to proceed at the same rate. Now, if we were to look at the data, it would look like this. Imagine 3 experiments where we vary the concentration of A. We would find that the rate is going to be identical. And so if you have a rate that stays the same, if you're looking at simply data, you know that's a 0 order. How could we figure that out based on this graph? Well, to figure out the rate, all you do is figure out the slope of that line. And so if we figure the slope of the line here and then tangent here, we would find that those triangles are exactly the same. And so if we were to graph the rate over time relationship, we'd find it's simply going to be a straight line. It stays the same. If we look at a first order reaction, this is the breakdown of hydrogen peroxide. Remember, rate is equal to K, that constant times the concentration of A. And so this is what our graph is going to look like. If we look at a couple of experiments where we have varying, again, the concentration of A, what we'll find is that there's a direct relationship between these two. As we double the concentration, we're doubling the rate. And you can see here that we're doubling the concentration, we're doubling the rate as well. So a great example of a first order is radioactive decay. Now, if we were to calculate the slope, we're going to have a steep slope at the beginning and a not so steep slope as we move farther out. So if I were actually to graph the rate over time, it's going to be a straight line, but it's going to be a straight line that's descending over time. Now, another way to figure this out is simply to take the data and then take the natural log of the concentration, and we're also going to get a straight line. What's cool about that is the slope of that line is going to tell us K, or that constant. If we look at a second order reaction, it's going to go even faster. So rate is the concentration raised to the second power. And so if we were to look at a graph, what does that look like? Well, in this first experiment from point 1 to point 2, you'll see that it looks like it's doubling. And so don't be tricked by that. What we're really doing is squaring it. So 2 squared is 4, 4 squared now is 16. So if we double it again from point 2 to point 4, we see that we're squaring that rate. And so what would that look like if we were to graph it? You actually get a curved line of the rate. And so you're taking the slope of a curved line, getting another curved line. What does that imply? That it's going really, really fast. The faster we have that rate. And so that doesn't, how do we find a slope of this curved line without using a lot of calculus? It doesn't work. And so what we'll do is if we take over time, the inverse of the concentration of that will actually get a straight line, which related to K. Now let's say we're looking at overall reaction order. Like I'd said, if we had more than one reactant, each of those may proceed along a different order. And so let's look at this data. This is a real common question in AP Chem. So if we look at the concentration of A, you can see right here it's held steady. And since we're holding it steady, we can just look at B and see what's happening to B. Well, you can see that we're increasing the concentration of B, but the rate is not changing. And so I know that B is going to proceed along a zero order reaction. Now let's see where we're keeping B the same. So B is the same here and here. And so if we look then at A from here to here, A, we're doubling the concentration in experiment 1 to experiment 3. Let's look at what's happening to the rate. The rate is proceeding as a square. And so rate is equal to K times A raised to the 2 power. So that's a second order. B is a zero order reaction. Since this is essentially 1, this would be our overall order. And so all we're doing is simply adding those reaction orders and we're getting the overall reaction order. Now let me give you a problem. Say this is the problem you have to figure out. Could you figure out the overall reaction order? Pause the video. Give it a try, and then you could put your answer down below in the video description. Let's say we gather a bunch of data, and we don't want to look at specific points. We want to actually calculate which order it is really, really quickly. A super simple way to do that is, let's say this is the concentration of our reactants. What we could do is simply graph the concentration versus time. In other words, this would be on the x-axis, this would be on the y. We could then graph the natural log of the concentration versus time, and then we could do the inverse of the concentration versus time. Now it's really easy to calculate this using a spreadsheet. We graph them, whichever one gives us a straight line, that's going to tell us what order it is, either a 0, a first, or a second. An example of that in the chemistry lab, you could do the breakdown of crystal violet. Crystal violet is going to be purple, but when we mix it with hydroxide, it's going to make a clear form of a chemical. And so what we could is use a spectrophotometer. Spectrophotometer measures the amount of absorbance. In other words, how much of that light is being absorbed by the material. And we could simply graph it. We could graph the absorbance versus time, then the natural log of the absorbance versus time, and then the inverse of absorbance versus time. And what that absorbance is really telling us is how much of that crystal violet is here. The more that's there, the more it's being absorbed. And so we could figure out which of these lines is going to be a straight line, and that's going to actually tell us K. And so did you learn to analyze concentration versus time data to figure out, is this a 0, first, or second order? Now we can go much higher than that. We can have fractional orders, but we're just getting started on rate law, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 59. It's on using Gibbs free energy, which is essentially energy that's available to do work. So if I were to push this sphere right here, it's going to move down and it's going to move back. Where's the energy coming from? Well, that would be gravitational potential energy being converted to kinetic energy. Eventually it comes to rest at the bottom. But if we think of this as an analogy, it really explains what's going on in a chemical or physical process. What we have is reactants and we have products. Those reactants are moving towards products, spontaneously some are moving back, and eventually it reaches equilibrium. What's happened to our Gibbs free energy? It's gone to 0. And so if we look at Gibbs free energy, it's a really good indicator of if we have a spontaneous reaction or a non-spontaneous reaction. So if Gibbs free energy is ever negative or less than 0, then we know that we have a spontaneous reaction. We have a scenario that looks like that, where we have energy and that energy can be released. If we have a delta G greater than 0, then we have a scenario that looks something like this. We have have an uphill reaction. It's not going to occur spontaneously. In other words, we're going to have to put a little bit of energy in for it to work. And then finally, we can have equilibrium in the middle. Now, in the last video, we learned that the two things that really contribute to Gibbs free energy is enthalpy and entropy. In other words, those two things together can help us determine if it's a spontaneous reaction or a non-spontaneous reaction. But it doesn't answer every question. And in this video, I'm going to try to answer every question. What's missing is our temperature. In other words, T is going to be incredibly important. And so if we're trying to figure out if it's a spontaneous process or not, one of the biggest things is enthalpy, or the amount of internal energy. And so if we have a delta H that's negative, that's a good indication that we're going to have a spontaneous reaction. So in a thermite reaction, our reactants have more energy than our products. It's a downhill reaction, and so we'd expect this to occur spontaneously. Likewise, if we were to rust iron, same thing. We're going to have more energy before than we do after. That energy is going to be released. That energy is going to be released into the surroundings. But sometimes you'll have exceptions to that rule. So like a cold pack, if you think about that, it occurs spontaneously, but in fact, it's actually consuming energy. And so we're going to have a delta H that's going to be a positive value. And so we can't just stick with enthalpy by itself. We have to add entropy to that. So if I had these two spheres and I had gas on the left side and I just open it up, we're going to see that gas move from left to the right. So we're going to have this irreversible process. And so what's going on there, we're not changing the energy. What's really going on is entropy. And so these two things together, enthalpy and entropy, are very important in helping us figure out if this is a spontaneous process or not. So we could put it on a grid like this. And so if we ever have a decrease in enthalpy, so that's going to be an exothermic reaction, or one that increases entropy, we know immediately that's going to be a spontaneous reaction. Likewise, if we have the opposite of that, if we have an increase in enthalpy and a decrease in entropy, we know that's going to be non-spontaneous. Now, the nice thing about that is the reverse of that we can automatically figure out is going to be spontaneous. But what's going to be in these other two spots? What's going to happen, for example, when we have an endothermic process, but we're actually increasing entropy, or vice versa? And so a good place to look at that is just the movement of ice to water. So if we're looking at ice and water, if we were to look at the molecules of ice, there's going to be a huge amount of order there. And a lot of that has to do with these hydrogen bonds. If we look in liquid water, it's going to be moving around. And so if we were to move from ice to water, what's that process? That's simply melting. That's going to be an increase in delta H. What does that mean? That's going to be an endothermic process. It's taking energy from its surroundings. So we're going to have a delta H that's positive. What's happening to our entropy? Our entropy is increasing. In other words, our matter is becoming more dispersed. So where would that be over here? We have an increase in enthalpy, and we have also an increase in entropy. And so let's go in the opposite. Let's say that we're actually freezing that water. What's going on there? We have an exothermic reaction. So we have a decrease in enthalpy, and we also have a decrease in entropy. And so this is going to be this block right here. And so in other words, if we could figure out this one slide, it would help us unlock what's in these other two grids right here. And so what do you know? Well, you know that if we take ice and we have it in an area where our temperature is greater than 0 degrees Celsius, this is going to be a spontaneous reaction. In other words, if you ever take ice and put it in an area where it's warmer than 0 degrees Celsius, we know that ice is spontaneously going to melt. Likewise, if we take that water and put it in an area where it's less than 0 degrees Celsius, then it's going to freeze. And we also know that if it's exactly at 0, we're not going to see any change. It's going to be non-spontaneous in either direction. So we've really answered this question right here. So if we were to look at that melting, if we ever have an increase in enthalpy, so this is a endothermic reaction, and an increase in entropy, that will be spontaneous as long as we have a high enough temperature. Likewise, if we have a decrease in enthalpy, so it's an exothermic reaction, and a decrease in entropy, then that's going to be spontaneous, but only at low temperatures. And so now we can finally come to Gibbs free energy, that equation, and hopefully it makes sense at this point. So if we're to look at Josiah Willard Gibbs' equation, this is going to be delta G on the left side. Remember, if it's ever less than 0, we know this is a spontaneous reaction or process. If it's ever greater than 0, we know that it's non-spontaneous. And so it totally makes sense, this grid right here. If you have a decrease in this number, that's a negative value. And if you have an increase in entropy, so our delta S is going up, since we're subtracting it, That's going to give us a negative value. Likewise, if we go down to this non-spontaneous right here, what do we have? We have a delta H, which is going to be a positive value. That's going to make this value go up. And then our delta S, since it's negative, we're subtracting a negative, so that's going to be a positive. And so hopefully these two make sense. But now this should unlock this grid right up here. So what happens if we increase our enthalpy? Well, if we're increasing our enthalpy, you would start to think, well, this is going to increase our delta G. But if we have a high temperature, that's going to make our entropy more important since we're subtracting that value. And so we can get away with a low enthalpy or a positive enthalpy if we have a really high temperature and an increase in entropy. Likewise, same thing down here. In this case, if we can have a decrease in this enthalpy, but our entropy, even though it is going down, we have a really low temperature, it's not going to swing us as much. Now, this also unlocks that whole idea of a cold pack. What's going on there? Well, we have an endothermic reaction. Again, it's taking energy from its surroundings. Our delta H is a positive value. And so why are we getting a spontaneous reaction? Since we have a delta H, it's going to be a positive value. Well, we're moving from ammonium nitrate into ions of ammonium and ions of nitrate. And since we're doing that, we're increasing our entropy. And so since our delta H value is going to be so big, then we're going to have a spontaneous reaction. We're going to have an overall delta G that's going to be a negative value. And so again, Gibbs free energy and that equation is really powerful because it tells us exactly what's going to happen in that process. If it's less than 0, it's going to be spontaneous. It's greater than 0, it's going to be non-spontaneous. If it's equal to 0, we're at equilibrium, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 35. It's on the rate of reactions, or the speed of reactions. Now, some reactions we might think of as incredibly slow. In other words, the rusting of this train car is going to take years and years to occur, to fully complete that reaction, if it ever is completed. But if we wanted to speed that up, we could do it by increasing the surface area of that iron. And we do that in a hand warmer. A hand warmer is essentially a bunch of iron that has been shredded to increase surface area. And so when you pull it out of a bag, it's going to combine with the oxygen and it's going to create a certain amount of heat. And that happens really, really quickly. And so again, the rate of reaction is going to be different for the reactants and the products, but we also have a certain amount of control over that. And so in a chemical reaction, the rate is simply the number of reactants that are converted to products in a given time. And so let's say the red and the blue represent reactants, and we combine those together to make products. The more quickly that we can do that, the faster our reaction rate is going to be. And there are a number of things that are going to affect that. The concentration, in other words, the more reactants we have, the more quickly they're going to find each other and the faster that reaction is going to occur. And also the pressure, in other words, if we decrease the size of that vessel that they're in, then we're going to have more of those reactions going on. Also, it's going to be the phase that it's in. Clearly, if it's in a gas, in an enclosed container, we might have faster reactions than we would if it's a liquid. And then finally, environmental factors. Things such as temperature and surface area are going to affect the rate of the reaction as well. And so if we're looking at two reactions, the rusting of metal and the combustion of wood in this case, both of those are going to have reactants, and I've marked those as A, and products, and I've marked those in C. And so the rate of reaction is going to be represented in this formula right here. And it's really simple. It's not that complex. It's either going to be the negative change in the concentration of A. In other words, we're going to have a decrease in the amount of reactants over a given amount of time. Remember, delta is just going to be the change. Or we could measure it as the amount of products that are being created over time, because those are essentially going to be the same thing. The more reactants we have being consumed over a given period of time, the faster that reaction is going to be. And likewise with the products. And so how do we measure the reactants? Let's say I have a reaction that I want to measure the reaction rate. How do I actually know how many reactants are in there? Well, a great example of something you could do is to use Beer's law. And so in this reaction right here, what I'm doing is creating a copper sulfate solution. I'm shining light through it. And what I can do is I can vary the amount of concentration, and you can see that the amount of light that is being transmitted is going to decrease as we have more of the concentration. I could then start collecting some sample data. So let me change it from 50 to 75 to 100 millimoles. In other words, let me increase the amount of that copper sulfate solution. Generally, what you would do is start with a stock solution and then dilute it over time, and you can see that the amount of transmittance is changing over time. Now, if I wanted to graph that, let me graph the data that I've just collected. Now, right here, I've got the concentration on the x-axis, and then the transmittance. In other words, the amount of light that's allowed through that sample, and we'll generally use something like a calorimeter or a spectrophotometer to measure that. And now I've got my standard curve, and so you can see that as I increase the concentration, that transmittance is dropping off, and it's kind of approaching a limit. So what could I do is I could take a sample and I could measure the reactants. I could then stop it at different times, and I could figure out how much of it is actually being consumed. Once I know that, my millimoles, I could figure out the time it's taking, and I can figure out the rate of the reaction. Now, it's important that you understand what's going on at the molecular level. And so this nice little PHET simulation will help out. And so in this one, the yellow and the other two are going to represent the reactants, and there's products, and reactants and products. In other words, it's converting from reactants to products and back again. Now, this is working perfectly because they're lined up perfectly. In other words, every time they hit, there's a perfect reaction. But let me angle that initial shot. Now the reactant doesn't hit the other reactant perfectly, and so we can't convert it to those products. And so it's really important that we're lining them up. And so let me now get a number of those reactions. That was a little bit boring. So let me add a number of different reactants. We're going to call those reactants A. And now let me add a number of different reactants like this. And so you can see by increasing the concentration of those reactants, it's more likely for them to hit each other. But again, we're not getting that reaction occurring because we don't have a high enough energy. So now let me increase the temperature, and you can see that now we're starting to have reactions occur. And if I were to keep track of the amount of those reactants converting into products over time, then I have a pretty good idea of what's going on with the rate of reaction. So what things could affect this? Well, temperature. As we increase the temperature, the molecules are going faster, so they're more likely to run into each other, more likely to have that reaction. If there's more of them, a higher concentration, or if we squeeze them together, if we have a higher pressure, that's going to increase the rate of the reaction as well. And then finally, surface area is incredibly important. All of these are broken down to the level of the atom, but let's say we just had a big tablet filled with A, and it hadn't been broken down, just like that big train car at the beginning. It's going to take a long time for us to break down, and the reactions could only occur on the surface, and that would be a slow rate of reaction. And so did you learn to interpret the results of an experiment regarding temperature? Could you start by figuring out the amount of reactants and then measuring it over time? If you could, you know how to calculate the rate of reaction, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 69. It's on pH and buffers. The proteins in our blood have a problem. They have to have a specific pH, and if it changes radically out of this range between 7.35 and 7.45, they start to denature, and they can't do the job that they're intended to do, which is to carry oxygen and carbon dioxide. Thankfully, we can use a buffering system. So what happens is the carbonic acid that's created when we add carbon dioxide to the water is a weak acid, and it has a conjugate base. And so that creates what's called a buffer solution. What does that mean? If we add more protons to it, it'll simply push it towards the left. And if we add more hydroxide to it, it'll push it more towards the right. And so it keeps our pH fairly stable. And that's how buffer solutions work. So pH, remember, is based on the protein availability. It's the concentration of that proton in solution. And so we want to keep that as stable as we can. And so we use a buffer solution to do it, which is essentially a weak acid and its conjugate base. And so what's going to affect the the pH of that reversible reaction? Well, the first thing is the pKa, which is going to be the equilibrium constant. And so if we can keep that equal to our pH or around our pH, that's going to keep our pH stable. And also we could look at the concentration of the acid, that weak acid to its conjugate base. If we can keep those values equal as well, that's going to increase the buffer capacity. And we'll look at that algebraically in just a second. But big picture, what are we doing here? Well, we've got a weak acid and a reversible reaction that forms this hydronium ion and then its conjugate base. And so in a good buffer solution, we want the weak acid and the conjugate base to be equal in values. And so what happens, let's say we add hydronium to that. Let's say we add a strong acid to that. Well, Le Chatelier's principle tells us if we add more of it on this side, it's simply going to push it in the other direction. So it's going to push it more towards that weak acid side. But since those values are equal, it's not going to change it that much, and our pH value is not going to change very much as well. If we look at adding a base now, if we add a hydroxide to it, what is it going to do? It's simply going to push it more towards the right. And so what happens is we can add strong acids and we can add strong bases, and it's going to keep that pH around a stable set point. And so let's look at this as an equilibrium equation. And so if we look at our equilibrium constant, if we were to write it out, how do we do that again? It's simply going to be the concentration of our two products over the concentration of our reactant. And so if we do a little bit of manipulation algebraically, what we can do is isolate the concentration of those hydronium ions on the left side. What is that? Remember, if we take the negative log of that, that's going to be our pH, and we want to keep that as stable as we can. So if it's a good buffer solution, how do we keep it as stable as we can? Well, if we keep our Ka value equal to our concentration of our hydronium ion, or if we keep our pH equal to our pKa value, that's going to create a good buffer. If one of those is much larger than the other one, changes in one will change the other. Also, we want to look at equal concentrations of that weak acid and its conjugate base. And so if we can keep those equal to 1, we can have large changes in that. Tenfold changes in that will only change the pH value a total of 1. And so we want to keep those values of the weak acid and conjugate base equal to each other. And also we can use our pKa values, which is, remember, looking at the concentration of reactants and products, and we can figure out what's going on in the reaction. So if our pH value is less than our pKa, that means we have more of this weak acid. And if it's greater than our pKa, that means that we have more of the base. And so if you think of it like this, if pH goes down, we've got more of the acid, and if pH goes up, then we've got more of the base over on this side. And so what are some good applications of that? Well, an acid-base indicator is a great example of that. So if we're looking at bromthiamyl blue, so what color is that going to be? If we're in a neutral solution, it's going to be right at 7. So our pH and our pKa values are essentially equal to each other. And so what happens if our pH value goes down? Well, that's going to shift it more towards the left. And so we're going to have more of this form of bromthiamyl blue, which is going to give us that yellow color. What happens if we go to the right? That's going to give us more of this blue color in relation to that neutral. And so we can see changes in the color of that indicator, and what that's telling us is changes in the pH. This is also important biologically. Remember, proteins are made up of an amino acid, and each of those amino acids are going to have a different side chain, which is going to be, if we look at every one of these amino acids, the top part is identical, but each of the side chains that drop off the bottom is going to be different. And so each of these have a different pKa value. And so if we change the pH of the overall protein, so this is the myoglobin, for example, it's going to change the behavior of each of those side chains in the amino acid inside it. And so did you learn that when we're creating a good buffer solution, we want to keep our pH and pKa values equal to each other? And did you learn that changes in the pH related to the pKa tells us if we're moving more towards the left, more of the acid or more of the base? And then could you design a good buffer solution? Remember, what we've simply got is a weak acid on the left side and its conjugate base on the right side. I hope so, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials video 42. It's on the rate limiting step. And I'm going to start with an analogy. Imagine if we have a road and cars are moving from point A to point B to point C, but nothing is slowing them down. Well, this analogy, I'm later going to talk about chemical reactions when we're going from reactants to intermediates and then finally to products. And there's nothing that's slowing down this reaction. But let's say I want to collect money from these cars as they drive down the road, and so I'm going to add an easy pass. And if you don't know what that is, basically cars have a microchip in their car. As they drive underneath this, it's going to count them so they can charge them for using that road. And so if we start the cars again, we're going to find that this easy pass makes it easy. In other words, the cars can ride right underneath it and it's not going to slow them down. In other words, the movement from B to C is fast. But let's say I now want to install a toll booth, and this one works by having cars slow down and then throwing their money in. Now the cars have to stop at toll 1, and so that's going to slow down their overall speed down this road. And so the toll booth then becomes the rate limiting step. And so in an overall reaction, remember, it's not just one step, it's step after step after step. And overall, that's called the reaction mechanism. And we can't just look at an overall equation and figure out the rate law of that reaction. In other words, we have to look at the speed of each of those elementary steps. Some are really fast, some are incredibly slow. And so we could look at those and figure out what's the rate limiting step. In other words, what's the toll booth? What's slowing down this whole reaction? If we know what that is, then we can figure out the rate law. And so going back to that analogy of the road, we really have two steps. Cars driving from point A to point B, and then cars driving from point B to point C. And so if we look at what's slowing them down or what's determining their rate, it's either the toll booth or the easy pass. And so if we look at that overall reaction, driving from point A to point C, since that first step is the time limiting step, it's slowing it down, that's going to be the limiting step of this whole reaction. So if we were to write the rate law for that, it's going to be based on how long does it take them to get through the toll times the concentration of the cars. Now let's get to chemistry. Let's say we're looking at this reaction. Right here we have nitrogen dioxide and carbon monoxide, and that's becoming nitrogen monoxide and carbon dioxide. Now this progresses along two steps, and so if we lay those out, here's step 1 and step 2, and we can see that they each have a different rate constant. But that first step is going to be the slow part of the reaction, and the second is going to be the fast. And so if we look at that overall reaction, again, these are going to be the reactants. So we've got nitrogen dioxide and then the carbon monoxide, and then these are going to be the products, the nitrogen monoxide and the carbon dioxide. And so if we look at that, what's slowing us down is that step 1. And so what's slowing down that whole equation? It's going to be step 1. And so it's going to be this K1, or this slow rate of reaction that's slowing down the overall reaction. So if we were to write the rate equation then, how are we going to do that? Well, our rate equation is equal to K. That's going to be our slow rate constant. And then what's going to be our reactants? It's simply going to be the nitrogen dioxide reacting with itself. And so that's going to be our overall rate reaction. Now, one thing that you want to make sure that your rate reaction is correct is that we can have no intermediates here. Now, what is an intermediate? If you look right here, we have nitrogen trioxide. That's not either a reactant or a product. In other words, that is an intermediate, and we can't include that in a rate reaction. And that's going to be important as we look at this next reaction. So in the next one, same kind of a thing. We've got two steps in this overall reaction. So here is step 1, and here is step 2. Now, if you look at step 1, we're finding something interesting, that this is a reversible reaction. Not only are we going in this direction, but we could also go in the other direction. Now, we can see that this is the fast part of that reaction, and then we have the slow part. So now we have essentially the easy pass first, and then we have the toll booth after that. So if we look at the overall equation, which of these is going to be the rate limiting or the time limiting step? It's going to be step 2 now. And so what's going to be the overall slowing of it down? It's going to be K2, or it's going to be that second rate constant. Now, if we write the rate reaction, we might just write it like this. So we've got K2 right here. Now we've got step 2, which is dinitrogen dioxide with oxygen gas. And you might say, I'm done. But remember, we can't include intermediates in that rate law. And so we're not quite there yet. In other words, that couldn't be the rate law. And that's not going to help us when we're looking at a reaction because we don't see the intermediates. We only see the reactants and we see the products. And so how are we going to get around this problem? Well, let's put this right here in red. This, in other words, is the thing that we want to get rid of in this equation. And so the first thing we're going to do is write this out. And so where did I get this equation? Well, this is going to be the rate constant of that first reaction, again, from the nitrogen monoxide to the dinitrogen dioxide. And this is going to be the reversible. In other words, this is going to be going back. And so we assume that the rate forward is going to be equal to the rate backwards. And so this is a reversible reaction. How could you think about that with our road again? Think of it as cars that can't get through the second toll, and so they're just driving back and forth between part A and point B. And so once we've got that, then we can solve for what is in here. In other words, we can solve for what's in here. How do we do that? We're going to divide both sides by k to the negative 1, and now we can isolate that. So we've isolated this on one side. That's the thing that we want to get rid of. And again, we've divided this side by k sub negative 1, and I can just move that up into my general equation. I can substitute it. And so here's going to be the overall rate law of this equation. And so I'm good now because I've got right here, I've got one of my reactants. Right here, I've got one of my other reactants, and this is going to be the overall rate of this reaction. So it seems a little bit confusing, but again, all we're doing is just doing some simplification, and then we're substituting that in so we can have a rate law that we can actually use. So did you learn that the rate of the reaction is set by the slowest elementary reaction, and we can use that to figure out our rate law? Well, if you did, you learned what I wanted you to, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 40. It's on the reaction path. If I want to move this object here from point A to point B, it's going to travel along a path, and it looks like it's a pretty straight path from A to B. But if we were to look at the reaction path, in other words, the path from reactants to products, it's not going to be so straight. In other words, it's going to follow along a curved energy profile. In other words, that object has a certain amount of energy at the top, we put energy in, and we're able to get some of that energy back. And so if we're looking at a chemical reaction, this could be the reactants on this side and the products on this side, but we have to put a certain amount of energy into that system in order for that reaction to occur. And so let's say we have these two molecules, A bonded to B and C bonded to D, and then we're going to create these products down here, A now bonded to C and B bonded to D. We have to put some energy into the system. It's just not going to spontaneously occur, and so we have to add energy till we reach what's called the activation energy. And so in an elementary reaction or in a one-step reaction, we have to break bonds and then we have to form new bonds. And a good way to look at how that works as far as energy goes is to use what's called an energy profile. This is the amount of energy or potential energy those chemicals had before the reaction. This is after. And these ones right here are going to be in what's called a transition state. They're transitioning from reactants to products. And what we really have to do is start to weaken those bonds. And one way that we can do that is to change the temperature. And so according to the Arrhenius equation, the constant or the rate constant in an equation is based on the temperature. The higher the temperature, the faster the molecules are moving, and the faster we're more likely to hit this activation energy, or the amount of energy required to reach that transition state. And so what we can use is the rate constant and the temperature to actually calculate that activation energy. And so in review, what is activation energy? Well, when we have a reaction, this is the reactants and this is the products potential chemical energy, but the activation energy is going to be the amount of energy that we have to put into that system. And so you think of it now like reactants and products. Here are two molecules we have to begin, reactants. Here are products that we have at the end. And so that transition state is going to be weakening of these bonds right here, so we can break those bonds apart, and then we can form those new bonds in those products. And so Svante Arrhenius studied this. He's a Swedish chemist, really brilliant guy. Also came up with the idea of the greenhouse effect and panspermia, how life could spread through the universe. And so it's a really brilliant guy. But what he came up with is looked at the rate equation. And so this is that rate equation we've talked about. This is the rate of the reaction. This is the rate constant. A is going to be the concentration of the reactants, and then M is going to tell us about the order of that reaction. But if we look at all of these things here, which one is really going to be affected by temperature? It's K. And so there is a temperature dependence built into K. And so the Arrhenius equation looks like this, and it basically describes the temperature dependence of K, or that rate constant. It's pretty scary, and so if we make it colorful, then maybe it's not quite as scary. If we break through the parts of this equation, K again stands for the rate constant, A is the frequency factor, and that's basically built on the amount of energy particles have in their proper orientation. We've got the activation energy, we've got the gas constant, and finally we've got the temperature. Now, where would you be asked to apply this in a chemistry class? Well, what we can do is we can measure two of these things. In other words, if we measure the rate constant and we measure the temperature in a reaction, then we can calculate activation energy using the Arrhenius equation. And so this equation by itself is not necessarily helpful in the chem lab. But what we can do is we can take the natural log of the whole equation. And if we do that, the natural log of K is equal to this. Now this looks a lot like that y-intercept form. And so this is natural log stands for y. This is going to be our slope. This is x and this is b. And so let me show you how you could apply that. So in a lab, this is the temperature on the side, and this is K. This is going to be that rate constant. So this has to be calculated or measured in an experiment. And so what I can do is I can graph that data. Now what I'm going to do is graph it not temperature on the x-axis, but the inverse of temperature on the x-axis. And I'm not going to graph K on the y-axis. What I'm going to graph is the natural log of K. But if I do that and I have my data like this, what I can do is I can calculate the slope of that line. Now that slope of that line is going to be what's in red here. And so the slope is going to be equal to negative activation energy divided by the rate constant. And so we can measure this on the slope over here. We know what the gas constant is, and so what we can figure out is the activation energy. In other words, the amount of energy that we have to put into that system in order for that reaction to occur. And so did you learn to explain the difference between successful and unsuccessful reactions in terms of energy and orientation? If you did, then you learned what I hoped you would, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 11. It's on symbolic representations. When you look at a candle burning, what you're seeing are processes at work. You're seeing both physical changes, in other words, the wax is melting to become a liquid, and then it's becoming a gas, and then you're also seeing chemical changes as that wax combines with oxygen in the air. You're seeing combustion. And so what we can do in chemistry is use symbolic representations of that to show conservation in mass. And so processes can be physical or chemical. But in chemistry, we can use representations to look at those changes. They could be symbolic representations, or they could be particulate drawings. But in both of those cases, we're going to see a conservation of matter. In other words, matter can neither be created nor destroyed. And so we can use that to calculate reactants based on products, or products based on reactants. And also we can look at macroscopic changes. We can look at movement of particles around. An example of that would be the carbon cycle. And so if we're looking at the physical versus chemical changes, an example of a physical change could just be boiling of water. In other words, we're changing water into a different phase, from a liquid into a gas phase. But a chemical change is going to require the breaking and forming of new bonds. And so an example of that could be the combustion of hydrogen found in the Hindenburg explosion. In other words, the hydrogen and the oxygen are combining to make water. And so we don't have hydrogen gas anymore. And so let's look at water to start with. And so what would be a symbolic representation of this phase change in water? We could look at water that's a liquid, and so the L means liquid. We're going to add a little bit of energy to that, and then we're going to create water that is a gas. And so what are these bubbles in boiling water? It's simply water that's changed phase from a liquid to a gas. What would a particulate representation or a particulate drawing look like of that same process? We'd have water molecules here. They're now a liquid. We're adding a little bit of heat to it, and now they're a gas. And so both of those are essentially saying the same things. It's just a model so we can wrap our head around it. Let's look at hydrogen combustion. What would be a symbolic representation of that? We'd have hydrogen gas with oxygen gas. You can see that these are both gases, and then we're forming water that's a liquid, and we're releasing a huge amount of energy from that. Now, a few things you should remember. The 2 here, the subscript, means that's the number of atoms of hydrogen that we have in one hydrogen molecule. And then the 2 out front, that coefficient, is going to tell us how many molecules that we have of that. If we were to have a particulate drawing, here would be our hydrogen. So we have 1, 2. In this drawing, we have 4 hydrogen molecules. So the H2 means we have 2 of the hydrogen. And then we'd have 4 of these molecules combining with 2 molecules of oxygen. And in this case, we'd have 4 molecules of water. And so the conservation of matter is incredibly important. It was first developed by Antoine Lavoisier. Here he is with his wife, Marie-Anne, and she worked in his lab and was really important in helping him make all these amazing discoveries. And if we were to say, what is he most famous for? He's most famous for moving chemistry from a qualitative, in other words, let's look at the color that's created or smoke is created, to more of a quantitative science. In other words, he was always measuring the masses, and he would use these big spheres, glass spheres, so he could collect all the material that was created. And so if we look at all of these both symbolic representations and particulate drawings, the mass before the physical or chemical change is going to equal that after. And so we can actually use this to solve some simple problems. Let's say the Hindenburg carried 1.77 times 10 to the 4th kilograms of hydrogen, and this combined with 1.42 times 10 to the 5th kilograms of oxygen. How much water would be formed in that? Well, this is a really simple kind of a problem. We'd first draw out a symbolic representation. We've got the amount of hydrogen and the amount of oxygen. And so since mass can neither be created nor destroyed, the mass that we have before the reaction is going to equal the mass we have after. So if I were to solve this, I'd write out the 2 masses we have before. You can see that they're going to be written in scientific notation, but these don't quite match up. So I may change this so that they match it up. And then it makes it a little easier to add those. So we'd make 1.60 times 10 to the 5th kilograms of water. Now, most of that water wasn't liquid. It was probably liquid that was just spread over a large area. If we were to quantify that in that Hindenburg explosion, 176 tons of water were made during that explosion. And so another thing that you should understand is as matter cycles, as it becomes one molecule and moves into another molecule, it's also going to be conserved. And so an example of this could be a biogeochemical cycle. So an example could be carbon. And so the carbon that's found in the atmosphere eventually becomes carbon in plants, becomes carbon in food, and then becomes the carbon inside you. And as you die, we release that carbon into the atmosphere. But it's not like we are creating or destroying matter. It's the same mass that's moving throughout that cycle. And so again, in review, we can use representations, both symbolic and particulate drawings, to show this conservation of mass. The problems are very simple, but we can also use it to measure large macroscopic movement. And so did you learn this? To express the conservation of mass qualitatively and quantitatively? Qualitatively, we could do that through one of these particulate drawings or in some kind of a chemical equation, but if we want to do it quantitatively, we actually have to measure the mass before and relate that to the mass after, or vice versa, and I hope that was helpful. Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 54, which is on intermolecular potential energy. This is a famous macromolecule right here. It's DNA, and every bond that you see is a covalent bond where you're sharing electrons between atoms. But it's a double helix, and what that really means is it's a double molecule. There are 2 molecules, and in the middle, they're held together with intermolecular forces. Those are going to be hydrogen bonds, or dipole-dipole forces, which are going to hold those 2 chains together. And so really, it's easy to pull DNA apart and for it to zip right back together again. And so we really want to make sure you understand the difference between an intermolecular and intramolecular. An intermolecular is going to be between adjacent molecules, between the yellow and the yellow. And so that would be, for example, between water and another water molecule. What are the intramolecular? Those are going to be the bonds. Those are going to be those covalent or ionic bonds that are actually between the atoms within the molecule itself. And so we're not dealing with bonds in this video. We're dealing with those forces between molecules. And those forces are based on what those molecules are. We can have an attraction between a dipole and a dipole. We can have an attraction between a dipole and an induced dipole, and then also between induced dipoles. And between each of these, there's going to be potential energy in those intermolecular forces, and it's going to take energy to pull those apart. And so an example of a dipole-dipole would be a hydrogen bond. And so what we're doing there is we're taking hydrogen atoms of one molecule, and they're being attracted to oxygen, nitrogen, and fluorine atoms of another molecule. And those are both dipoles, and so what we're getting is an attraction between those two. Those aren't of the same molecule, they're just holding those two molecules together. If we look at between two induced dipoles, that could be, for example, between argon, which normally doesn't have a charge, but can get a charge if we hold something like hydrochloric acid right next to it. And then finally, we could have two induced dipoles. An example of the forces between those are going to be dispersion forces. What are induced dipoles? They're everything. So there's a force between everything, and those are called dispersion forces. And they're based, or the strength of them, is based on the number of electrons that you have. The more electrons, the more dispersion forces we can have, and also the surface area in contact between those two molecules. So again, in review, what is a dipole? It's simply a molecule that has uneven distribution of electrons. And so if we look at water as an example, the oxygen loves those electrons. It's highly electronegative, so it's pulling it towards it. And so there's going to be a slightly negative charge on this side and a positive charge on the other side of the water molecule. It's a dipole. If we look at hydrochloric acid, the same thing here. The electrons are going to be pulled toward the chlorine atom, and so it's going to have a negative charge right here and a positive charge on the other side. Now, these two negatives are going to push on each other, and so what would a dipole-dipole bond look like? It's going to be looking like this, or rather a force is going to look like that. And it's going to hold those two molecules together, but again, it's not a bond between the two. Hydrogen bond is a great example of a dipole-dipole force. If we were to take water molecules like this, you can see that all of their oxygens are going to have negative charges. And so that's not how it's going to line up. In a hydrogen bond, the way it would line up would be like this. And so we now have an attraction between this hydrogen and this oxygen. This would be a hydrogen bond right here. There'd be another hydrogen bond right here, another hydrogen bond right here, another hydrogen bond right here. Now, a point of confusion, remember, is that it's not in the same molecule. It's going to be between a hydrogen of one molecule and then either nitrogen, oxygen, or fluorine of another molecule. Now, this is a huge amount of energy that's held in this, and let me give you an example of that. What we're looking at now is the boiling point of 4 different molecules. And so we'll start right here with hydrogen telluride. That's H2TE. And if we look at its molecular mass, it's over here, and then its temperature of boiling point is going to be a little less than 0 degrees. And so if I go to the next one up in that group, we've got hydrogen selenide. And so we can see here that we have a decrease in the molecular mass, and we also have a decrease in the boiling point. If we go to the next one, hydrogen sulfide, you can see that there's a really well-established pattern right here. As we move to smaller atoms, we're getting less molecular mass, and we're also getting a lower boiling point. So what's going to be the next one? If we go through this pattern, it's going to be H2O, so that's going to be water. Could you predict where that's going to be? Well, you might think it's going to be something like this, but it actually is way up here. Why is that? Because there's all these hydrogen bonds between the water molecules, and so it really takes a lot of energy to break those apart and to boil that water. Thankfully, that's why we're filled with water, so our temperature doesn't change that much. So what's a dipole-induced dipole force? Well, if we have hydrochloric acid and argon mixed together, what we'll find is that this argon doesn't have a charge. But if we pull it close to a dipole, what it'll do is it'll actually pull those electrons towards it. And so what you get is an induced dipole. And so this is a force that's holding them together. Since there are more electrons on this side, it has a partial negative charge right here. Now, how are we going to measure the strength of that bond? It's based on 2 things. It's based on the strength of that dipole, and it's also based on the polarizability, in other words, the number of electrons and how those electrons can be pulled of that induced dipole. And sometimes we'll have molecules that can both form induced dipoles. So right here we have helium gas. As it moves close to another helium atom, you can see that there's an attraction between the electron and the protons of the adjacent atom. And there's also going to be repulsion between these electrons. And so what we're creating is a temporary dipole for just a fraction in time, but it's still going to hold those things together. And so all molecules have these induced dipole to induced dipole forces. All molecules have this attraction between them. What's going to increase that attraction? It's simply going to be the number of electrons that we have and the surface area. And so this is a picture of a gecko that's climbing up glass, and if you look at their foot, we're going to find that there are folds, and then if you zoom in on those folds, there's folds on the folds on the folds. And so how are they magically able to walk up a wall like this? It's those attractions, those dispersion forces between them and the wall. And so they've increased the surface area, increased the number of electrons, and so we can have enough of an attraction to actually hold them up. And so did you learn to make claims or predictions regarding these intermolecular forces? Again, it's based on what's holding them together. Is it dipole-dipole, dipole-induced dipole, or just induced dipoles? These are all intermolecular forces, and I hope that was helpful.